Hello everybody, welcome to the Intermediate and Advanced Rust course. In this video, I'm going to discuss more features of Rust that can help us understand the ways to use Rust in more detail. This video is actually a continuation of the previous video about introductory Rust programming. And for this video, we still refer to the two major references. The first one is the Rust book, and the other one is the Rust by example web page. Now let's talk about the generic data types in Rust first. Actually, we have already seen the use of generic data types in the introductory Rust course. Option T here, result T and E here, and vector T here are all using the generic data types. The T and E here are actually the generic data type symbols. So one letter can represent one particular type. And generic data types can represent the concrete types. So when I put a piece of concrete data into T or E, when I use the option, result, or vector, the generic data type would become a concrete data type. And we can also write functions, methods, or other user-defined types using generics, so that these constructs are applicable to the concrete data types when they are called. So we will see some examples to understand the meaning of this sentence. First, I can say that the generics can be used in functions. So how can we do so? We can make a function that has a generic type in the parameter list, and then I can return that particular data type. So let's see this program. I have a function called lastElement, which accepts a certain array whose type is a generic data type called T. So the generic data type can mean any other types, for example, the integers, float, or strings, and so on. And when this function accepts a generic data type in the form of an array, I have to also indicate the generic data type called T after the function name. So this T would refer to that T in the parameter list. So I have to make sure that the data type, which is a generic one, will appear in both the parameter list and after the function name, okay? And this function would try to return a pointer to a generic data type, okay? And I just want to show the final element of the list passed into the lastElement function, and I want to show the address of it only, okay? And in the main function, I just show a number of arrays. The first one is an array of integers, the second one is an array of float, and the third one is an array of string slices, okay? So we have different data types, but when I put the different arrays into the lastElement function, this function is able to recognize all the data types because the generic data type has played the role of accepting any type of the data from the array that is passed to the function, okay? And of course, I just need to pass the address of the array because the function just accepts the address of the array. So let us try to play with this program. So let me try to play with it. Okay, I can see that I can pick up all the last elements of all the arrays involved in the function, okay? The meaning is like this. When the data type is integer for the first array, the concrete type becomes the integer, so T would become the integer type. And for the second call of the function, the data type would be float, 64, okay? And for the third function call, the address of the string slice would be input, and I can pick up the string slices as the concrete type used in the third function call. And you can see that I can pick up all the last elements from all the arrays, okay? So that is the meaning of using a generic type. By using a generic type, all the possible data types can be accepted, okay? And we can also see another example of generics in structs. The fields of a struct can be in terms of generic types, and we can give a concrete type to the fields when we make an instance from that struct. The following code would require us to see that all the fields would have the same type, with t being the type placeholder when we make an instance. Okay, so I'm going to explain the paragraphs with the following code. Suppose I have a certain code for recording the rainfalls in 3 places, and you can see that in the struct declaration, all the fields would have the same generic type t. And of course, I have to specify that same generic data type at the end of the struct name. Okay, so t here would correspond to all the t's in these fields. Okay, and when I make an instance of the rainfalls, I just input 3 float numbers into the fields so that all the fields would have the same data type, which is the float type, or float 64 by default in Rust. Okay, so when I use the derive debug instruction, I'm able to use the dot notation to get the fields of the instance. Okay, so when I put integers into the instance, of course I would have t being the integer, okay, rather than the float. Okay, so let me try to play with the program. Okay, you can see that all the rainfall values can be printed out, and the concrete type becomes the float 64 for this struct. Okay, t would be inferred as the float numbers. Okay, so the inferred data type is f64 as told by the Rust analyzer. Okay, of course, we can allow multiple generic types on the same struct declaration. So for example, if I have t and u to be used in the struct, I can put t and u separately in the fields so that the fields can contain different data types. So if I have t and u respectively, some of the fields can be integers and some of the fields can be float numbers. Okay. And let us see another situation. Generics can be used in enums. Actually, we already saw option enum, result enum, and t and e here are already 2 generic types that can be inferred by the Rust analyzer. So t and e here are the generic types, and option and result are 2 enums in Rust. That's why I can say that generics are already used in some enums. Okay. And the fourth point is that the generics can be used in methods. We can really implement a method that accepts generic data types by using the implementation block format. And of course, the implementation block has to really specify the generic type placeholder. Okay. So in the following example, I want to make a method that implements 2 generic types called x1 and y1 respectively, and the return value would make use of all the generic types obtained from the 2 distinct struct instances. So I'm going to make 2 struct instances, and I'm going to play with those 2 instances to have actually 4 generic types. So I have a struct called data pair, and we can see that we have x and y here. It means that the data 1 has 1 generic type, and data 2 can be in a different generic type. That's why x and y can be different. And of course, I want to make another struct so that I can have 4 generic types, A, B, C, D respectively. Data 1 here would refer to one of the generic types. Data 2 would refer to another generic type, and so on. So for the joint collection struct, I have 4 fields, and each field would refer to a different generic type. Okay. So for the first struct data pair, I want to implement a method on it. So when I use the data pair here, I want to say that I want to implement a certain method by specifying x1 and y1 as well, so that the declaration here would be the same as the declaration there. So for the implementation, it also follows the generic types used by the data pair struct, okay? And this function is going to join the pairs. So I want to accept another 2 new generic types. And this function needs to input another data pair instance. So the data pair would have x2 and y2 for their generic types. That's why the function would also need to follow the same generic types for the data pair struct, okay? And the function would just return a joint collection instance having 4 distinct generic types, x1, x2, y1, and y2. And that's why I can use the generic type from one instance of data pair and from another instance of the data pair struct to make a joint collection instance, okay? So let us see the main function to really run the code. So I make 2 pairs. One is called pair 1 and the other one is called pair 2. And you can see that for pair 1 and pair 2, all the data type will be different for the fields, okay? This is a character, this is a float number, this is an integer, that is a string, okay? And I want to tell pair 1 instance to do the join pairs method by operating on pair 2 instance, okay? So pair 1 would have the generic types x1 and y1, which will be inferred by the REST analyzer as character and float respectively. And for pair 2 that is passed to the join pairs method, x2 and y2 will be inferred for us as integer and a string, okay? So let us see the result if I want to print the collection 1 content. Okay, you can see that when I say allow unused, I'm able to get rid of some of the warnings that actually won't affect our result. So you can see that when I do the joint collection struct here, you can say that data1 of self would be put in the data1 of the joint collection, other .data1 will be put into data2 of the joint collection, so on and so forth. So you can see that there are actually 4 different data types that can be inferred by the REST analyzer. And we can see that the use of the generics here is quite useful, because when I say x1, y1, and x2, y2, I can help REST to indicate that all the 4 pieces of data in the fields of the joint collection struct can be different. Okay, that's why I can show all the different data types in the joint collection by using the generics, okay? And how about the performance of using generics? Actually, the running speed is not pretty slower even in the generic type situation that we discussed. During the compilation process, the inferred types are already put in the code automatically. That means we can say that the monomorphization has taken place. It will just result in the static dispatch, which means that the compiler already knows the method we call at compile time. That means for the methods that we are going to call, the methods already know the data type that we have passed to the methods. So it seems like the running speed would not increase very seriously, okay? And another topic in this video is about traits. What is a trait? A trait is really a collection of methods defined on an unknown type called self. The type here is unknown because sometimes we have to wait until the code really tells me the type to use the trait later on, okay? So after defining a trait can be implemented on any data type. That's why it is usually of unknown data type when we define a trait, because we still need to wait for the data type to implement the trait. And the trait can be regarded as a toolbox that can be used by a lot of types. So we can see the meaning of this sentence later on when we play with the trait. So how about implementing a trait? A trait can provide a default implementation that does the same thing even though it is implemented in different structs or enums. And we can also override the default implementation of the trait. And a trait can just declare functions. And a trait is implemented on different structs by providing the definition of the functions. So it is a bit abstract. Let us see the following example. Suppose I have a trait called exercises. So I have to create two functions. One is called take rest and the other one is called react. So when we do exercises, we need to take rest and we need to react according to some situations. So I don't really implement the react function or method for now because we have an ampersand self here. It is really a method. I mean the react function is really a method. And for the take rest function, it is really a method because you can see ampersand self is passed as the parameter. Okay, so you can see that we have a default implementation for the take rest method. So regardless of the structs or enums to play with the trait, I can already provide a default implementation to show some string here. I tell the athlete to just stop and drink water. This is the meaning of taking a rest for a default person. Okay, I don't know the particular type of the athlete for now, but I can still tell that athlete to stop and drink water. Okay, so here I will have two structs. One is called tennis player and the other one is called basketball player. So the tennis player has a field and the basketball player has another field. And then I can tell the tennis player to really do exercises. That's why I implement the trait exercises on the tennis player. Okay, and when I want the tennis player to implement the exercises trait, I really need to do something like defining the react method because the default implementation in the trait doesn't exist for the react method. So when the tennis player really wants to use the react method, we have to really provide an implementation block for tennis player. Okay, and this is the way for the tennis player to react. So when the tennis player is right-handed, he or she has to strike with right hand, otherwise he or she has to strike with left hand. And how about the basketball player? In order for him or her to do exercises, I have to really define the react method for a basketball player. Okay, and the implementation is shown here. I just tell the basketball player to do the best move more often, and the best move is already shown in the struct field. Okay, and of course I can just override the default implementation of the take rest method. So I don't say stop and drink water. I can just tell the basketball player to warm down first. Okay, this is the way for a basketball player to take rest rather than just drinking water. And you can see the main function here. I have a tennis player called Peter, and I have set up the instance, and I've also told the instance to execute the react method. And I also tell the tennis player called Peter to really take a rest. Okay, same for John, but John is a basketball player. His way to react and to take rests can be different from those for Peter. So let us see the result of this piece of code. So let me play with it. Okay, you can see that for the first print line here, it comes from the react function for Peter, which is a tennis player. So for a tennis player, the react method is just doing a strike with the right hand because Peter is really a right-handed player, okay, according to the struct fields for Peter, okay. And for Peter, he is a tennis player, and for tennis player, he uses the default way to take a rest. So I just tell Peter to stop and drink water, okay. And for John, which is a basketball player, his way to react is to do the shooting, okay. Just shoot more often. So I tell John to shoot more often, being the reaction for him, okay. And if John wants to take a rest, he can follow the overridden implementation shown here. Warm down first, okay. So warm down first becomes the way for John, which is a basketball player, to take a rest, okay. So you can see that the implementation can override the default one shown in the trait declaration, okay. And actually, a trait can be used as a parameter. In calling a function, we can pass a data type that implements the given trait as the parameter. And we can really specify the trait bound to indicate the trait on which a generic data type needs to implement. If a generic data type doesn't implement the trait, the function call would fail. So let's see this example. I have a trait called printable, and I have a method to be defined when I really use this trait, okay. And I have a person struct, and that person struct would implement the printable trait. So a person here would do the printable trait, and of course for the printable trait there is a print method. It means that a person would do the print method, okay. The print method is just going to say the age together with the name, okay. And I have a function called print something, and this function would just have a trait bound, okay. This is called a trait bound, shown here, okay. So this trait bound tells us that the thing to be put into the item here would need to implement the printable trait. That means the address of a generic type T has to really implement the printable trait. So T and T here would refer to the same type that can really implement the printable trait. Okay, so the print something function here is to call the print method in the type that implements the printable trait. So for our case here, the type is a person type, okay. So let us go to the main function. You can see that I have created a person struct instance, and for this instance, I need to do the print something method. So when I pass the address of the person to the function has to make sure that this particular instance is really able to implement the printable trait. Of course, it is possible because the person instance comes from the person struct, and the person struct already implements the printable trait, okay. So when I pass the person here to the print something function, this function can work. So let us see the result of this code snippet. And let me play with the program. Okay, you can see that I can print the name and the age of the person. Okay, the person is defined here. Okay, and when I put this person struct into the print something function, this function can work for me because the person instance here is coming from the person struct, which implements the printable trait. So the condition here is allowed. That means the trait bound is satisfied when I call the print something function, okay. And in calling the function, I just tell the item, which is the person instance, to use the print method, okay. That's why the person's information can be printed out, okay. The shorter way of the code doesn't need to tell all the trait bounds explicitly. So the print something function here can be just as short as this one: item, ampersand impl printable. Then this statement is able to replace the longer one shown here. So we don't need to tell the trait bound explicitly, as long as we say that the item needs to implement the printable trait. So this is another way to use the function here. Okay. Another way is to really use the plus operator to join the two traits on which an item needs to implement. So let us see an example right here. I have defined a trait called printable, and I have also declared a trait called printable, and I've also declared another trait called describe more. And for the printable trait, I have a method called print, and for the describe more trait, I have a method called elaborate. And I have to implement the printable trait on the person structure. So this trait will be used by the person struct. That's why I have an implementation block for the person. Okay. And for the describe more trait, I want the person struct to implement the describe more trait. That's why the person struct has to implement the two traits one by one. Okay. So you can see that the print something function here has to accept a person that can implement the printable trait and which can also implement the describe more trait at the same time. So this T here is a generic type that can implement both traits. Okay, that's why I have to use an addition sign to combine the two traits. Okay, and you can see that the main program has a person coming out, and that person can work on the print something function because the person here is actually able to implement both the printable trait and the describe more trait. Okay, so let me try to play with the program. Okay, you can see that the name can be printed out and the age can be printed out. That is coming from the print method by implementing the printable trait. And this person is also able to do the elaboration by himself because the person is also able to implement the describe more trait. Okay, that's why you can see that the person is really able to say that he likes jogging as well because the hobby of him is really jogging, shown here. Okay, so when I use the plus operator to connect the two traits, the data type has to implement both of these traits in order to execute the print something function correctly. Okay, and the shorthand form of the print something function can be like this one. I don't need to say this long by saying that T has to implement both the printable and the describe more traits. I can use this shorter form, say, and implement printable plus describe more. Okay, so this is also another way of setting up the print something function, which may be a bit shorter than before. Okay. In order to make the trait bounds a bit clearer, we can even use the where clause. That can help us really specify the trait bounds. So the trait bound T has two traits. This manner makes the trait bounds clearer to show up. So you see I can use the where clause, and after that I say T would need to implement the printable trait as well as the describe more trait. Okay. So the print something function can be written in this way. So by using the where clause, the traits to implement will be even clearer. Okay. And other than just making a function that implements a trait, we can also return a type that implements a trait. So we can write a function that returns a struct or enum type that needs to implement a trait. And the return type of the function would indicate the trait on which a struct needs to implement. Only one specific data type can be returned. and no choice of the data type can be made in the function code. It is a bit abstract. And let me use a certain example to illustrate the point of returning a type that implements the trait. I have a shape trait that is used to find out the area of a shape, and I have also a circle struct, and the circle struct has a field called radius. So if I want to tell the circle to find out the area, I can implement the shape trait on the circle struct. And of course, I have to define the area method here. Here you see in the trait that the area method is not yet defined. And now I just implement the area method in the implementation block for the circle struct, okay. And you can see that I have another function called createCircle that returns a type that implements the shape trait. So this is the return type, and the return type has to really be able to implement the shape trait, okay. So I can return a circle here that actually implements the shape trait. Circle is allowed because we can see that the shape trait has already been implemented by this struct, okay. And when we go to the main function, I can use the createCircle function immediately after providing a certain radius value, because when I provide the radius value, I can make a circle as the return value, which is already able to implement the shape trait. That's why for this circle instance, the area can be found immediately by calling the area method. Let us try to play with the code. So you can see some error here because I haven't commented the describe more method out. So let me go to 138 here, okay. Also, the printable trait isn't yet commented out. Now I've got no errors, so let me play with the program again. So you can see that the area of a circle can be found by inputting 5 units of the radius, okay. So the createCircle function would create a circle for me, and that circle is able to implement the shape trait because I've already set up the implementation block of the shape trait for the circle already. And you can see that the return value is a circle, and for that circle it can do the area method because this circle instance already implements the shape trait, which has a certain area function to be handled already, okay. Another topic of trait is called the conditional implementation of some traits. What does it mean by this part? Let us see. When we write implementation blocks for a struct or an enum made up of generic data types, we can add a trait bound to the entire implementation block. So to use the functions in the implementation block, the implementation block needs to check that the generic data types can really implement some traits. So it is a bit abstract. Let us see an example to see what the meaning of it. So in this example, both the generic data types have to implement the display trait. Since both string and i32 can implement the display trait, they can be put into the implementation block. And this display trait is actually a built-in trait for Rust. And we can use the display trait to show the result of a string and of an i32 quantity. Okay. So I just import the display trait first, and then I make a certain struct called person, and for this struct there are 2 generic types T and U. So the first field would correspond to type T and the second field would correspond to type U. And I want to implement something for the person struct. I want to provide a new function so that I can make a new person. So you can see that the return type is self, okay, and I just put info1 and info2 into the field value when I want to create a person, which is a new one, of course. And you can see that I can implement another method called print, okay? And the print method has to rely on the display trait. That's why I have to say that the generic type T has to be bound by the display trait, and the generic type U is also bound by the display trait, okay? So I have to make sure that both pieces of information coming from info1 and info2 from two different types would be able to use the display trait, okay? So you can see that I'm able to create a person, and the person : new method would store a string followed by an integer. Both of these types can implement the display trait. That's why they can be put into the person struct, and this P can really use the print method. If any one of them cannot really implement the display trait, the print method cannot be executed, okay? What does it mean by that? We can see another example. If I don't put an integer for U here, instead I put a vector which doesn't implement the display trait, you will see that the implementation block for the print method cannot be used because the second parameter here isn't able to implement the display trait for the case here, okay? So let us try to play with the code now. Okay, you can see that when I run the program, you can have the print function being called. Actually, it is a method, and for this method, I can show the information from info1 and info2 respectively, because the string here and the integer here are able to use the display trait. Okay, how about the case if info2 is a vector? Let us try. The vector is in this format. When I save it, you can see that the method print cannot be used because the trait bounds are not satisfied. Okay, because this vector isn't able to implement the display trait. So you can see that the print method cannot be used, and you will have an error coming out. Okay. So it is just the meaning of this part. Okay. I cannot use a vector here because a vector doesn't implement the display trait required by the code. Okay. And we can see that checking the requirements of the traits at compile time can reduce the possible errors that may happen at runtime. So you can see that the previous error would just make the program unable to compile. So in this case, we can already stop the possible runtime error before we really compile the program. So that is the use of the trait bound requirements to avoid the possible runtime error. Now let's talk about lifetime of references. Lifetime can help us to make sure that the references used are valid as long as we need to use them at runtime. So every reference has a lifetime. If more than one lifetime is possible for a reference, we need to really annotate the lifetime that we want to use. So the use of lifetime has some purposes. The first one is to prevent dangling references. A dangling reference is something like this. It is a reference that points to some memory that is already gone. So what does it mean by this one? Let us see the example shown here. I have a main function, and the main function has a variable p declared first, and inside the main function we have a block, and the block has a certain variable called answer, which is obtained by the result of the function called add, shown here. Okay, so I just add x and y, and I return set, and p here is going to store the address of this answer variable. And the next step is to print out the value stored in p after executing this block. So P here is already after the block here, okay. But we can understand that the answer variable will be gone after going through this block. So when I want to print the value of P, which points to the address of a certain variable that is already gone, I would have a dangling reference in P. So it means that I'm not able to really show the print line statement macro here, because the value of P that it really refers to is already gone after the end of the block. So let us see how I can execute the program and see if it is possible to run it or not. So you see, answer does not live long enough. The borrowed value doesn't live long enough. So you see that P is actually a borrowed value because P is just accessing the address of the variable called answer, and the answer here will be gone after this block, and I'm not able to really print out that address any longer because that variable including the address is gone. So that is the problem with the code. That's why I'm not able to even compile it. Let us see. You can see that I'm not even able to compile the program because of the dangling reference. Okay, so how about realizing the dangling reference in more detail? We can make use of the borrow checker to understand it. The borrow checker is responsible for finding out the lifetime of each reference, and we can use an apostrophe together with a lifetime name to denote a lifetime. So let us go back to the previous example that we talked about. The lifetime of P here is actually called apostrophe A, which is this long, and the lifetime of answer variable is just this long, called apostrophe B. And we can see that the lifetime of answer, which is called B, is shorter than the lifetime of P that is called A. So in this case, for the print line macro here, it is not possible to really obtain the answer variable because the lifetime of the answer variable is gone when the variable P really wants to refer to that non-existent variable. Okay, so that is called a dangling reference. Now let's talk about the way to annotate the lifetime. The lifetime annotation is really similar to the generic type annotation. We can give the generic lifetime to a reference. So when we have a lifetime indicated by the apostrophe followed by the lifetime name, we can add the data type. So when we add F64 here, it means that I'm going to make a reference with generic lifetime A, and that reference would be referring to a value in F64 type. On the other hand, if that reference is a mutable one, I just add MUT in the middle, so that I would have a mutable reference with generic lifetime A. Okay, so we will see these examples later. And let us talk about the lifetime annotation in functions and structures and so on. When we pass some references as function arguments, the function doesn't know whether the lifetime of the references are gone or not. If the references are already gone before the function uses them, we would have the situation of dangling references. Therefore, the function needs to annotate the generic lifetime in the function parameters in order to make sure that the past references are valid at the time we want to use the reference from a function. Okay, so we will see this meaning by using a simple example very soon. And the same lifetime A here would apply to all the parameters and functions and structs together with the fields of a certain struct, meaning that the parameters would have to be valid for the same lifetime called A. So we have such a program here. I want to pass two string slices into the function, and the two string slices have to have the same lifetime as the function. So we can see that the function has a lifetime called A, shown here, and the parameters of the function would also have the same lifetime called A here and called A here. And I also expect the return value of the function would have the same lifetime called A as well. Okay. That's why I have two ampersands shown here, okay, to represent the references that I want to pass, okay. So the function is just showing the string size that has the lower dictionary order, so I use smaller than operator to compare the two string sizes. And let us go to the structure here. The structure here also needs to have the same lifetime called apostrophe A. Okay, so we can see that the structure, the function parameters, and the return value would have the same lifetime, so that I'm able to ensure that the function is really able to use all the function parameters, and the return value would live as long as the function itself, okay. So let us see the main function here. The main function has two person instances. One is called Joanna, and the other one is called John. And I'm going to pass the Joanna.name and John.name into the function called earlier name. So I'm able to get the fields from the instances, and I'm going to pass the fields into the function. Okay, so the function name, earlier name here, would have the same lifetime as the function parameters Joanna.name and John.name. And of course, the return value called shorter is also having the same lifetime as the function and the function parameters. Okay, so I'm able to print the shorter value here. Okay, so let us play with this example. So I have a variable that is not yet used, so I can really ignore this warning if I want to show the meaning of the code to you. Okay, you can see that the shorter name is Joanna because Joanna is placed before John in the dictionary order. Okay, so you can see that the lifetime of Joanna and the lifetime of John would be the same as that of person. Okay, so if person is A, Joanna's lifetime and John's lifetime would also be A. Okay, and of course we have to make sure that the fields would have the same lifetime. That's why I have to really specify the lifetime for the field called age, because I really want to use this field in the function called earlier name. Okay, so in this case, the function earlier name is able to make sure that both the name of Joanna and the name of John would be still living. Okay, so if any one of the generic lifetimes is missing, the lifetime issue is not clear to the called function. So the function is called here, and we have to really indicate all the lifetimes explicitly. Otherwise, the lifetime is not really clear to the function, and the function isn't so sure that it can use both the names. Okay. Let us talk about a topic of lifetime annotation in method definition. So we can declare the lifetime of an implementation block after the impl keyword, as well as after the structure name. We will see this example pretty soon. And the same lifetime apostrophe A can apply to all the parameters, meaning that all the parameters would have to be valid for the same lifetime. So let us see this program. In our program, the first string, which is this one, would have a longer lifetime than the second string. When they are both passed to the function, the lifetime of the returned reference will be the shorter of the two brand and model references. So the brand name here and the model name here would be represented by the two string sizes that will be passed to the new function. Okay, and also the concrete lifetime passed to the function is the shorter of the brand and model references. So you can see that both brand and model initially would have the same lifetime called A. Of course, the structure also needs to have the same lifetime called A. And of course, when I want to return a value from the new function, I also need to specify the lifetime of that instance, okay? And then I want to do the display info method to show the brand and the model of a certain car, okay? So let us see this example in the main function. The main function has two strings. One is called brand and one is called model. And I have also a year, which is an integer, or I32 by default. And then let us see this one. I want to pass the address of the brand string and the address of the model string to the function called new, which is implemented by the car structure. And of course, I also want to pass the year into the new function so that this thing will be called. When the function new is to be used, the parameters would have the same lifetime, okay? And when the display info method is going to be called, the self.brand and the self.model will be obtained. So we can see that the brand variable would have a longer lifetime than the model variable, because the model variable is declared after the brand variable. It means that the lifetime of A here would be the lifetime of model, because model is declared later than brand, okay? And we can see that the main function would go to the end. That means the model lifetime would be across these lines, and the brand lifetime would be across these lines. So we can see that the model variable would have a shorter lifetime than the brand variable, okay? So the lifetime of A would follow the lifetime of model shown here, okay? So A here would become the lifetime of the model that is put here, okay? Of course, we don't use the lifetime of brand to do the function called new, because we need to use the shorter one, okay? When the brand is present after the first declaration here, the model variable isn't yet present, so it is not possible for the function called new to use the lifetime of the variable called brand. Okay, let us talk about the lifetime edition. We can see that we always need to indicate the lifetime. It will be a bit clumsy or a bit tedious in some situations when the lifetime is very clear to be determined. In that case, we can just ignore the lifetime annotation. When the lifetime can be inferred unambiguously by the Rust compiler, we can ignore the lifetime annotation. And the lifetime of the input parameters is called input lifetime, whereas the lifetime of the function output is called the output lifetime. So for the new function here, this A and that A would refer to the input lifetime, and the output parameter would have the lifetime called output lifetime, okay? And there are 3 edition rules. Let us see all these 3 rules. Number 1, the compiler would assign a lifetime parameter to each of the parameters that are of reference type. For example, when there are 2 references in the parameter list, the lifetime of the first one is called A, while the lifetime of the other one is called B. And we will need to specify both the lifetimes in angle brackets after the function name. So we can see this example later. And for number 2, when there is exactly 1 input lifetime, this lifetime would also become the output lifetime. That is natural. The output would depend on the input. Number 3, if one of the input parameters is %self or %mut self, then the lifetime of self will become the output lifetime. So we will see these examples below. So when we have the elided form here, it is actually having the expanded form shown here. We need to really specify the lifetime of the function in angle brackets, and we also need to specify the lifetime of the input parameter here, and of course the lifetime of the output parameter would also be shown here. They are the same lifetimes, okay, when we have only one input parameter. That means we have used rules 1 and 2. The first one here and the second one here. When we have one input lifetime, we have the same output lifetime as that of the input. Okay, and for number 1, we have to assign the parameter lifetime one by one. Okay, since we have only one input parameter, we just use A to indicate the lifetime. And let us see another example. If I have this elided form with 2 function parameters, then the expanded form would be having 2 lifetimes, A and B. And for parameter X, it will have a lifetime of A, and for parameter Y, it will have a lifetime of B. And here, this is the problem. I'm not sure about the lifetime of the return value. So I can use rule 1 to indicate that we have to handle 2 lifetimes, but I'm not able to determine the lifetime for the return value because I don't know which one is a longer lifetime. A or B is longer, I'm not sure. So we can see this paragraph. The lifetime of the returned reference is not yet determined. Its lifetime will be the shorter of ampersand A and ampersand B. Therefore, even though we just followed the elision rules, we are not always able to determine the function signature completely. The signature has to also include the lifetime of the return value, but I'm not able to do so in this case because I don't know whether A or B will be having a shorter lifetime. Okay. Now let us see the third example. When the elided form is this one, we can see that the expanded one is that thing. So we have self in the parameter list, and the output parameter would have the same lifetime as that of the input parameter because the input parameter is including the keyword self. Okay, and of course the function has to follow the same lifetime as the input parameter and the output parameter. So the input lifetime and the output lifetime would be the same. This is something about rule 3 shown here. Okay, we need to check these rules in order. If all these rules cannot help us to solve the lifetime issues, we need to really specify the lifetime explicitly. So this sentence is really referring to the second example shown here. We have to really specify the lifetime that the output parameter needs to follow. Okay. And let us talk about static lifetimes. A static lifetime just means that the reference can live for the whole program, and the value is just put in the binary file, and that's why it can live for the whole program life. And we can use the ampersand apostrophe static to indicate the static lifetime. So this string will live for the whole program. So this string slice will live for the whole program, okay? And we can make a constant for the whole program using static lifetime. So it is accessible anytime we want, okay? This is one of the ways to make a constant in Rust by using the static lifetime, okay? Now let us go to an example that uses the generics and the traits and lifetimes all together. This example is a bit long, so let us try to copy it to the Rust first. And let me explain the meaning of the code first. Now I have a sentence here. This is called my sentence, and my sentence is an instance from the sentence struct. So the sentence struct would have a field called value, and I just say hello world for this sentence value. Okay, and we have also got a container, and the container is going to really wrap the my sentence instance, and I need to pass that instance into the function by using the ampersand symbol so that I can just pick up the reference of that my sentence instance into the new function of the container struct. Okay, and we can see that the new function is here. A container struct is going to really implement the new function, and the new function would just return a new container value with the data being put into the container field. Okay. And I just want to tell the container to do the print data method. The method is also defined in the implementation block of the container struct. And you can see that I want to do self.data.print. So it means that I want to use the print function declared in the printable trait shown here. So it means that the container struct isn't able to directly print the data by itself. The container struct has to really use the trait called printable, okay? And this printable trait is implemented by the sentence struct, but not the container struct. So for the container struct to use the printing action in the sentence struct indirectly, the container struct has to use the print method that is implemented by the sentence struct, okay? So let us see the comment here. The container struct accepts a generic type T, and the lifetime of the generic data type T has to be at least as long as that of the container. So I have to say that the container struct has a lifetime A, and the generic data type that will be passed to the container's new method would have the trait bound printable and the same lifetime as that of the struct, okay? And of course the data would have the same lifetime called A, okay? And the implementation block for the container struct would also need to specify the lifetime as well as the trait bound, okay? And of course the new function here has to use the same lifetime called A. Otherwise, the new function isn't able to make sure that the data that will be passed to the new function would live as long as the function needs to use it, okay? The sentence structure has to follow the same lifetime called A. And of course, when it wants to implement the printable trait, the trait would have the same lifetime, okay? Let us see the explanation further. The container instance of the container struct really needs to use the mySentence instance of the sentence struct. Therefore, both the container and the sentence structs need to have the same lifetime. So the container is something like wrapping the sentence instance. That's why both the container structure and the sentence structure would need to have the same lifetime, indicated by the name A, okay? Here and here, okay? And the container struct has the print data method, and this print data method needs to process the data in the container instance, which is a reference to the sentence type, okay? So the print data method here is a method of container instance, and the container instance would have the print data method shown here, and it is going to use the print method implemented by the sentence structure, okay? And the sentence struct doesn't have its own print method, but it can implement the print method from the printable trait, of course. So the sentence structure doesn't have the print method, but it can implement the printable trait to get the print method for the sentence struct to use. And since the container struct uses the print method from the printable trait indirectly, the container struct really needs to include the printable trait as the trait bound, okay? So I'm going to show here. That is the trait bound of the container struct, so that the container instance can really use the printable trait. Especially, I mean the print method here contained in the printable trait. Because of the trait bound here, the container struct can use the printable trait, okay? So let us play with the program. Okay, you can see hello world coming here. Okay, hello world is just a value inside the sentence instance called by sentence, and the container instance is obtained by passing the reference to a sentence instance into the new function. Okay, so we can see that the inferred data type is sentence and container respectively, but the lifetime is elided because the lifetime would follow those for the sentence instance shown here. Okay, so we have already learned a lot of things about the lifetimes. We have to really make sure that the lifetime is included in functions when we want to pass some references into the function parameters or structs. Now let's take a look at the following example about the generic data types, trait, and lifetimes. So we have this situation. There are two types of items in a shop: grocery item and household items. Given a shopping list that consists of these two types of items, find the total price of the shopping list. And we also want to show the items bought and their listed prices as well. So you can expect that I need to create a library that stores the information of the two types of items in the shop: grocery item and the household item respectively. I also want to include the price of these two particular types of items. So the shopping list will be made in the main function later on, and I'm also able to use the corresponding methods or functions from the library to help me solve the problem. So let us make a library file first. So now I want to add something to the library file first. First, I want to make a trait called item. So the item can be grocery items or household items. So these two types of goods would also implement the trait called item. And for this trait, I'm going to put the name of a particular item, the price of a particular item, be it a grocery item or a household item. And I'm also going to describe each type of the items. Okay. So now let me create the structure for the grocery item first. Okay, I made a structure called grocery item, and the structure has a lifetime called A. So the name also needs a lifetime of A because this is a string size, and for string size we have to make sure that the lifetime of the fields in string size format has to have the same lifetime as the structure. Okay, and the price here is another field of the structure. So the price is in F64 data type. So I have to use a comma instead of a semicolon. Okay, so let me try to implement the item trait on the grocery item structure now. So I made the implementation of item trait on the grocery item structure. So I just define the detail of the name method, price method, and the describe method provided by the item trait. So if an item is a grocery item, the name would be just the name of the structure instance. The price is also the one mentioned in the structure instance, And for the describe method, I just say it is a certain grocery item, okay. Then actually I can do similar things for the household item. And for illustration purpose, I do the household item similarly to the grocery item. But in reality, we may have other approaches to make the code simpler. So for illustration purpose, I made the code a bit repeated in some sense. Okay, you can see that for household item structure, we have a name and the price of a certain household item. And I just implement the item trait for the household item. So I just implement the 3 functions coming from the item trait again. The difference comes from the describe method. So I say that it is a household item instead of saying that it is a grocery item. So the name and the price are obtained from the instance coming from the household item structure. So you can see that some codes are really repeated, but for the demonstration purpose, I can see how I can use the same function name for different structures to do the corresponding task for different structures, okay. So now let me create an enumeration of the shop item. So a shop item can be a grocery item or a household item. So for this enumeration, I have 2 variants. One is called the grocery type, and the other one is the household type. And for the grocery type, I can put a certain instance from the grocery item structure. And for the household item structure, I also make a certain instance that will be put to the household variant, okay. So you can see that I have to make sure that all the enumeration together with the items from different structures would also have the same lifetime A, okay. So you see that all the things will be put into the heap allocated memory. If that's the case, we have to make sure that all the heap allocated memory items would have the same lifetime. Same for the implementation block for the household item and for the grocery item as well, okay. So when we want to implement these functions or methods, we have to make sure that the grocery item or the household item would really have the same lifetime, okay. After I have got the shop item enumeration, I can really implement the item trait on this enumeration. So for the name method, if the element comes from the grocery variant, I just pick up the name of that item, which is of grocery item type, okay. And if the element is of household item type, the name would just come from the implementation block for the household item structure, okay. Same for the price method. I just make sure that the instance to be put into the grocery variant would be of the grocery item type, and I can pick up the price method coming from the grocery item type. Same for the household item type. The price here would come from the household item structure. I mean the implementation block of the household item structure, okay? So we can use the same function name here to correspond to different structures, okay? So we can do the same approach on the describe method. So I can check for the instance type, and if the instance type is of the grocery item type, I can just use the corresponding method from the grocery item type that is already implementing the item trait, okay? So same for the household item. I can use the corresponding describe method from the household item type, okay? So the describe method would come from the implementation block that uses the item trait, okay? And then I can really make up my shopping list. Okay, the shopping list structure is like this. I have to make sure that the lifetime is the same as other parts of the program, so that the instance have to live as long as other instances. And we have to make sure that the trait bound is item. And for this item trait, I also need to make sure that this item trait has to live as long as the lifetime of other parts of the program, okay? And for the field inside this structure, I have a field called items, which is really a vector. And the content of the vector would be implementing the trait called T, okay, which is just the item trait. And the vector element would also have to live for as long as the lifetime A, which will be consistent with all other parts of the program, okay? And then I can make the implementation block for the shopping list structure. So for the shopping list structure, I can have a new method, which is just giving me a new vector as the value of the items field, okay? Of course, for the implementation block, I have to make sure that the lifetime and the trait bound will be the same as the shopping list, because I really use the shopping list content to help me do the implementation of the new function, okay? So the lifetime and the trait bound have to match each other. I mean, the implementation block also has the same lifetime and the trait bound as the shopping list, okay? So if I want to add something to the shopping list, I can use the push method for vectors. Okay, so the vector here can be mutated. That's why I have to do the mutable self here, so that the thing to put into the add items method would help me vary the content of the items field, okay? And for the item field here, it has to live the same lifetime, and the trait bound of it is the item's trait, okay? This ampersand here means that I want to get the reference to the item, okay? Same for here. This vector is storing the references, okay? Now the total cost method is quite easy to understand. I have to make a variable which is mutable to store the intermediate result of each of the summation coming from the item. Okay, so for the item here, it comes from the items field of the shopping list structure. Okay, and for each item, be it the grocery item or the household item, I can use the corresponding price method for each type of the items. Okay, and then I add the price of each item from the array in the items field, and then I just return the total as my return value of the function called total cost. Okay. Okay, for the display items method, I just go over the items vector, and then in each of the elements of the items vector, I get the item and I get the name from that item, be it a grocery item or a household item. I also get the price of that particular item, depending on the type, be it a grocery item or a household item. Okay, and then for that item, I can use the corresponding describe function to show the information of that particular item. Is it a grocery item or a household item? It can be told by using this method. Okay, so let me go back to the main function. So I have to recall the project name, and I'm going to use all the modules coming from the project. Okay, it means that all the things in the library.rs file will be used. So now I have item 1, which is from the shop item enum, and in this enum I take the grocery variant, and in this grocery variant I really store a certain instance of grocery item type, and the fields of that grocery item type are shown here. Okay, I have the name and the price. And then I do similar things for item 2, which is another item called bread with a different price than the apples shown above. Okay. Okay, the third item is a pillow of household item type. Okay, so I use the shop item enum, and then I pick up the variant called household, and I put the particular household item instance into the household item placeholder. Okay, so the content of the household item is shown here, the name and the price of that particular item. And then I can make a shopping list now. So I use the new method that we described here to really make an empty shopping list by putting a new vector into the items field. And then I've put the 3 items into the shopping list by using the add item function. Okay, the add item function is here. I do the pushing of the individual references of the items into the vector. Okay, so the pushing is going to put the references to all these 3 items into the shopping list variable, okay? Then I can call the display items method for my particular shopping list, which is this one, okay? We have the function here. I can put the reference to the shopping list into the display items so that I can pick up the item from the shopping list and I get the name and the price of each item in the shopping list, okay? Okay, I can use the total cost method to find the total amount of the things in the shopping list. The total cost function is here, okay? I can loop over all the elements in the vector stored in the items field, and then I can get the corresponding price of each of the items in the shopping list, and then I can get the total, okay? So let me try to play with the program. Okay, you can see that I can print the elements one by one. So item 1 is the apples, okay, and the price is $2.99, okay. So it is a grocery item. Why? Because when I do the display items function, you can see that I really call the describe method of each particular item, and the describe method would depend on the item type. Is it a household item type or is it a grocery item type? They will have different ways to describe the item, okay? So we can do the repetition on the second item and the third item. And you can see that for the total cost here, it is just the sum of these 3 values to get this amount. $14.97, okay? So you can see that I can use the generic data type, the trade, and the lifetimes quite completely to demonstrate this example. So we have to make sure that the heap allocated memory would have the same lifetime before we want to use them together. Otherwise, we cannot make sure that they all live at the same lifetime. Otherwise, we cannot use some of the references to the values in the heap allocated memory, okay? So remember to use the command here to bring all the library items to the current scope indicated by the main.rs file. Now let's talk about the display trait, which is an advanced trait in Rust. We can really implement the display trait in the format standard library manually to print the content of the data type, be it primitives or user-defined types. We don't always need to rely on deriving the debug trait to do the printing of the content in some user-defined types or primitive types. In the following code, f is a formatter which returns the format result type to indicate whether the writing is successful or not. The string will be mutated, so we need to have a mutable reference to the f here, okay? And the write macro would help us to write the values from an instance into a formatter called f. And the formatter struct here would provide a number of functions to help us format a string. So let me try to see some of the other functions to do the formatting. Okay. We can see that there are pad methods, write string methods, write format methods, and so on. So we have many ways to do the formatting of a string by really using these functions. So we are just talking about one of them to really do the display of some struct fields without using the debug trait. So let us see this example. The placetime lifeholder called apostrophe underscore would mean that the lifetime can be elided. That means we don't need to really specify the lifetime. So I have to use the fmt standard library, and now I have a person struct here, and I want to implement the display trait for the person struct. So my way is to really design the fmt function, which is one of the functions for the display trait, okay? And for this display trait, we have one function called fmt, which is this one. So how can we use this fmt function to display the person fields? I need to make a formatter here, and the formatter has to be a mutable one. And I use the formatter struct here with a lifetime that can be elided to indicate the type of the formatter, f, okay? And the return type would be a result type, and if the writing action is successful, the value can be printed out. Otherwise, you will have an error coming out. So I just make a person instance, and I have to include the name and age. And when I say something like print line person here, I'm able to show the result coming from the fmt function, which is obtained by implementing the display trait. Okay, so let us see this example. Okay, you can see that the name and age of a certain instance can be printed out by using the display trait. So when I have set up the fmt function included in the display trait, I'm able to show the entire sentence to the formatter, and the formatter is able to show the whole string into the monitor. That's why I have the name together with the age. So that is the meaning of the fmt function obtained by implementing the display trait for a certain user-defined struct. Okay, and the formatter would have the type called formatter shown here. Okay. Now let's talk about automated tests. In the Rust book, it already states the actions that are required in testing a program. We have the following 3 major steps. First, we set up any needed data or the state, and then we need to run the code that we want to test, and we also need to assert the result that we really expect and see if it is the case or not when we run the test. So how can we run automated tests in Rust? We can see the following example that is already provided by Rust. So we have a test template to use already. When we make a library project, a testing template is already written for us, and it is already stored in the lib.rs file. So how can we make the library? We can make use of the following syntax: cargo new, and you give the project name, which is my project, for example, and you give a space, and then you put 2 hyphens, and then you type lib to make a library project. And I have already set up the library, which is this one. So you can see that I have already used the name called automated tests to replace my project here. And then when I type the library as well, I'm able to set up a library project. So let me go to the library.rs file. So you can see that we have been already given which is also the same as that shown on my notes. Okay. So how can we run the test? We just follow the following command. When I say cargo test, then I'm able to run this template. Okay, you can see that the test is passed. So I have a test called it works shown here, and the test is passed because I can really say that the assert equal macro can return true. So my result, which is obtained by adding 2 and 2 together, I'm able to get 4. That's why the left hand side is 4, the right hand side is also 4. That means these two values are equal and the test is just passed. Okay. So how can we really run the test when we type the command shown here? First, we can see the code on my notes. I have an attribute shown here. When I add this attribute to the Rust code, I'm able to run the test when I input the cargo test command, okay? And I have a module here, and the module is a test. And the test code would have this statement shown here. Use super : asterisk. What does it mean by this statement? It means that we want to bring all the modules into the current scope. Okay, and after adding this one, we go to the important part of the testing process. I have this annotation called test. And this annotation is meaning that we are having a test function instead of a main function that we want to really run. But I just want to do the test on this following function. So before the test function, I need to say test, okay? And I want to see if the function really works or not. I have to use the assert equal macro to see that if the result is equal to 4 or not. If the result from the add function here is really equal to 4, then the test will pass when I type the cargo test command, just like what we did previously, okay? So that is the major idea of doing a test by using the appropriate macro to test whether a certain function can get your desired result. That is a major principle of making a test, okay? And we can also make our own test that would fail the test by panicking. So we saw a certain example that would make the test pass. So if I want to make a test fail, we can make our own panic statement as follows. I use the panic macro to do it. So let me try to run this test to really fail the test. So you can see that I just paste my code into the lib.rs file, okay? And let me try to run the test. Okay, you can see that the test failed shown here because you can see that the panicking really comes out, okay? You see, the test really panicked, okay? That's why we are not able to pass the test and you have a failed test coming out, okay? So we can make the test fail by showing a panic statement, okay? Another topic to discuss is the assert macro shown here. If the test result turns true, then the test is passed, else the test fails. So when we use the assert macro, we have to see whether the value on the left-hand side is equal to the value on the right-hand side if I use the equality check. Okay, so here I have two assert macro statements. First, I want to make a multiply function, which is quite straightforward. I want to multiply A by B to get the result of the product. And then I want to say that the left-hand side obtained by the function is equal to 6. And the second macro wants to say that the result on the left-hand side, which is coming from the multiply function, is equal to the value on the right-hand side, which is minus 10. So you can see that the first statement can pass the test, while the second one would fail the test. What would happen when I run the test? When there is one false result returned from the assert macro, the whole test would fail. So we can see which of the macro would fail from the standard output. So let us try to play with the program. Okay, I pasted the code into the lib.rs file. And of course, I want to indicate that I want to run a test. That's why I have to say test attribute here. Okay. What will come out when I run the test? Okay, you can see that the test failed because I have one assert statement that failed the test. So I have test failed. Okay, it means that the entire test multiply function would fail the test. Okay, even if the first assert macro is correct, when the second assert macro isn't correct, the whole test would also fail. Okay, and you can see that the problem comes from the second assertion shown here. Okay, 5 multiplied by -4, it should be -20 instead of -10. So you can see that the failed assertion would come out and the correct assertion would not be shown on the standard output. Okay. And let us go to another macro called assert equal. The assert equals macro is similar to the assert macro. When there is one macro failed, the whole test would fail. So it is just equivalent to the assert macro. So let us try the program. I have to add the EQ after assert. Also, I have to use comma instead of the equality check. Okay, so I'm going to check whether the left-hand side is equal to the right-hand side, and the two values are separated by a comma instead of the equality check symbol. Okay, so this is the way to use assert equal macro. Okay, we have EQ here, and for the previous case without EQ, it is just checking the equality. Okay, or we check the logical statement inside the assert macro. Okay, but when we use the assert equal macro, we have to put two values separated by the comma. Okay. Okay, you can see that the second assertion fails because the left-hand side is -20, but the right-hand side is -10. So this assertion would fail. I want to see that whether the left-hand side is equal to the right-hand side, but you can see that the second assertion fails. Okay, so the left-hand side is not equal to the right-hand side. And of course, when one of the assertion fails, the whole test would fail as well. Okay. And similarly, we have assert not equal macro. NE here means not equal. When we are not sure that a function must not be some value, we can use the assert not equal macro. The NE here means not equal, of course, and the left-hand side and the right-hand side are also printed for clear comparison, so we can run this following code. The code is similar to the previous one, except that the assertion becomes non-equal rather than equal. And let me try to run the test. Okay, you can see that the test failed, of course, because the second assertion is correct, but the first assertion would fail. Why it fails? Because you can see the first assertion would give the left-hand side as 6 and also the right-hand side as 6. So the two sides are equal. That means this assertion of checking the non-equality would fail. When one of the assertions fails, the whole test also fails. That's why the whole test failed. Okay. We can also write some custom failure messages. In the assert macro, we can include the failure message after the testing of a Boolean expression. Then the failure message will appear in the standard output. What does it mean by this one? We want to assert that the multiplication of 2 by 3 is equal to 8. So I have a certain Boolean statement here. If this assertion fails, I will just print out the following string shown here. Okay. The multiplication result doesn't match. So if the assertion is correct, I don't print this one. But if it fails, I'll just print out the whole line shown here, okay? So let me play with the code. And let me check the result. Okay, you can see that the test failed. The reason is that the left-hand side of the expression isn't equal to the right-hand side of the expression. So you can see that 2 times 3 isn't equal to 8. Then I'm going to print out the string shown here, okay, instead of doing nothing, okay. We also have the should panic annotation. If the test really panics, then the test is passed, else the test is failed. What does it mean by this one? I have some panic statements shown here. If the function really gives me the panic statement, then I would say that the test is passed. If I just go to the else part, which doesn't show the panic statement, then I would say that the test really fails. That is the meaning of this annotation called should panic shown here, okay? So let me try to play with the code. Now let me try to play with the code. Okay, you can see that the test fails when a is equal to 1. Because when a is equal to 1, I would go to the else part, rather than doing all the panic macros just above the else statement, okay? So you can see that the program doesn't really panic. That's why the test would fail when I have used the should panic annotation. So I can also try a equals 0 and a equals 2 to see the result. So let me try to do it. And before I do it, I want to say something like this. The print line statement is also shown up here. A is 1, and note the test didn't panic as expected. Okay, that is the message coming from the standard output. And we can see that the test really fails because it doesn't panic. Okay, you can see that it doesn't really panic, then the test would fail. Okay, so let me try to change the value of a to 0 first and see the result after running the test again. Okay, you can see that the test is passed because I really make the program panic. Why? Because when a is equal to 0, it is going to the branch here, okay? So you can see that I'm able to see a is less than 1. Since the panic statement shown here will go to the standard error, we cannot see the sentence in the standard output, okay? Now, how about the case when a is 2? We can also expect that the test can be passed. Okay, the test is passed because I can go to the panic statement shown in the first branch, okay? And we can also add a parameter to the should panic attribute to show the expected substring of the error message. So if I want to show the expected substring, I can do something like this in the attribute part. Should panic, and then expected equals something, which is part of the error message that we expect to have. So the larger than substring is shown in a larger than 1 case, okay? So when I have a situation that needs to go through this branch, the program would panic. Okay, so let us see the result by running the code. Now a is equal to 1, so I would go to the final part, okay? When the program goes to the final part, of course the test would fail because the statement can be printed out and the program doesn't really panic, okay? So if I use 0 or 2, let us see the result when a is equal to 0. you can see that the test will still fail. The reason is like this. The panic statement doesn't really contain the expected string, which is larger than. So when a is equal to 0, I would go to the second branch shown here. And you can see the panic statement doesn't really contain the substring called larger than. Instead, I have less than. Okay, that means the program would still panic. But I'm not able to pass the test because the expected substring doesn't match. Okay. So how about the situation when a is equal to 2? Let us see. Okay, the test can pass. Okay, the reason is like this. When the panic statement has a part of the string that is equal to the expected value shown here, the test really passed. So we can be sure that the test is passed because the expected substring can be found in the panic statement. Okay. And different outputs will appear on the standard output when a is varied. So that is already something we tested. So let us go to another part of this section. We can have the result enum in testing. So an variant can be used in place of panic macro. What does it mean by that? You can see that if the test function can return a result variant, then I can use it to act as the function that is used by the panic macro. So if the result is true, then I would go to the OK variant. Otherwise, I would have a certain variant with the string inside, okay, to indicate that the problem has come out. Okay, so let us try to play with this part. Now I have 5 times 8 equals 50, so I want to check whether this Boolean statement is true or not. Of course, it is true. Then you will expect that I'm going to have the OK variant as the answer. Let us see the result, if it is the case or not. Okay, you can see that the test is passed because this statement is really correct. Okay. And when I have OK coming out, I do nothing. Okay, that's why I don't have any other thing on the standard output. How about the case when I try 5 times 7 equals 40? You will expect that I will have the variant to come out. Okay, you can see that the test really failed. The reason is like this. I really get the error message shown here. Okay, the error message would come from the variant of the function result. Okay, so you can see that we can also use the result enum type to act as the function of doing the panic macro. Okay, and let us see how we can run the tests concurrently or consecutively. By default, when there are more than one test, they will be run concurrently for faster results. If a test needs to start after another test is finished, we may need consecutive execution of the tests by doing only one thread at a time. So if I want to do so, I just use this command to say the number of test threads to use is just 1. So let us try this program. We have 2 tests, you see, test 1 and test 2 here. So each of the functions to test is annotated by the test attribute, okay? And since we have 2 tests, if I want to run the tests one by one, we can use this command instead. So let us see the result. Remember, the command to use is this one. You can have 2 hyphens followed by a space followed by 2 hyphens and then test hyphen threads equals 1. That means that I use 1 thread instead. So the 2 tests will be done consecutively. Okay, you can see that we have two tests. The first one is passed, while the second one would fail. Okay. The reason is like this. When I multiply 2 by 3, it gives me 6. When I multiply -5 by -4, I don't get 20 back. So you can see that the left-hand side of the second assertion is equal to 20, but the right assertion is just 10. That's why I have one failed test, but one passed, because the first assertion is true. Okay. The test is 20 for the second assertion shown here. Okay. But the right hand side fails. That's why I have one failed test. Okay. And I just use one thread to do so, because I have already used the test thread equals 1 command. Okay. And you can see that this particular test failed. Test multiply negative numbers instead of the first function. Okay. And you can also see that we have the positive 1 passed. And you can see the standard output is able to show which test is passed and which test is failed. Okay. And we can also show the test function outputs. By default, the function outputs are not shown when the test is passed. The function output will be shown on the standard output when the test fails. That is something we already experienced a lot. When the test fails, we see some error messages. But when the test is passed, we have nothing to see. To show the test function result even if it is passed, we can do the following command to show it out. I just use show output here when I do the cargo test. So let us see the result again by running the code. And we have to use show output. Okay, you can see that I have one test passed and one test failed, which is actually the same result as before, because I just used the same code, but with different command in the testing. Okay. So let us see the result. I did 2 tests. The second one called negative numbers is failed, but the first one called positive numbers is passed. And you can see that the positive one is successful, and for the failed one, the assertion here would fail as before. The left hand side is 20 when I multiply -4 by -5, but the right hand side is 10. So the left hand side isn't equal to the right hand side. And you can see that I have to do something here. I want to print the result of the function. So that's why I need to show the A times B into the printline statement. So let me try to run the test. Now you can see that one test is passed, but one test is failed. Which is passed? Of course, it is the multiplication with positive numbers, and the failed one would be the multiplication with negative numbers. Okay, and we can see the statement. We see the answer is 6, and it is successful. I mean, for the first test, it is successful. So we can see the successful one, and the answer is 6, of course. And the failed one would have the answer as 20, because that is something we need to print out in the multiply function. And the left hand side isn't equal to the right hand side. That's why the function result isn't equal to the right hand side. It means that this assertion would fail. Okay, so you can see that the successful one and the failed one are also mentioned in the standard output. successful one and the failed one, okay? And we can also just do particular test functions. So we don't need to do all the functions listed in the library.rs file. We can just choose some of the functions to do. If I want to do so, I just need to mention the function name. Okay. So if I do cargo test multiply negative numbers, then I will just do the tests shown here, and this test will be ignored. So let us see the result. Okay, you can see that I have one failed test, which is the second test shown here, okay? Of course, I didn't really execute the first test. And the first test that is already ignored is called a filtered test, okay? So the filtered test would be just the one that I didn't really execute, okay? That is the meaning of the filtered out shown here, okay? So the tests that are not executed are called the filtered tests, okay? We can also use the ignore attribute to skip some functions so that we can ignore some tests. So how can we do it? We just use the ignore attribute here so that I don't really need to run this one. So I can still use cargo test as the command, but I can also ignore the first function test, okay, because that function is already having the ignore annotation shown here, okay. So let us see the result of this test. Of course, I want to print out the result. Okay, let us see the result. If I use cargo test only, is it able to skip the ignored test? It is possible. So you can see that I have one test failed and only one test was done. The ignored one was really forgotten by the Rust compiler, okay? So you can see that I have only one test executed. This one is ignored. So you can see that the first one is really ignored. And that's why I have only one failed one. And now I have one ignored function test, okay? So if we want to just run the ignored ones instead, I can use cargo test ignored shown here, okay? Then it is possible to skip the other one, but run the ignored one annotated in the program, okay? If we want to run all the tests, including the ones with the ignore attribute, we can use the include ignored command after using the cargo test command, okay? So you have many ways to handle the ignored test indicated by the ignore annotation, okay? Let us talk about test organization. We can do both the unit test and the integration test on Rust programs. So how can we do the unit test? We can test each of the functions in an isolated manner, and we can also test private functions. The idea is to use this attribute, cfg test, to test the function and its required private functions. The test will be executed if we use cargo test, and the test will not be executed when we are building a binary. So we have already done a lot of unit tests. If we include the cfg test attribute, we are already doing the unit tests. So how about integration test? An integration test is done outside the library, and only the public functions can be called during a certain integration test. And we can see whether the separate functions in the library can work together correctly. So let us see the following example to see how we can do the integration tests. Suppose our project is named as automated tests. We have already done so here. And we need the library file first, which is the library.rs file. So I'm going to copy the following code into the library.rs file. And after that, we can make a new directory called tests at the same level as the source folder to perform the integration test. And in this test folder, I want to add a file called integration test.rs. And then I can paste the code here. Okay, so the integration test would try to play with the two functions together. The functions to play are the subtract function and add function. So this test function is going to do the two functions together. So that's why I have to import the two functions from the library first. Okay. And this is the unit test, which is done as usual. So the integration test would be done separately. So we can see the result of running the test by using cargo test. Okay, you can see that the test is passed, which is it works. It works as in the library. So you can see that both the functions are done. That means the unit test shown in the library is passed correctly because both the assertions are true. Okay. And you can see that I've also run the integration test shown in the integration test.rs file. Okay. So this one would fail because you can see that for the two assertions, only the first one would be correct, but the second one would fail. Okay. So when one of the assertions fail, the whole function would fail the test. That is natural. And the reason is like this. The left-hand side is 9 for the second assertion, but the right-hand side is 8 for the second assertion. That's why the assertion that they are equal would fail. Okay. That means the play with two numbers function in the integration test would fail. Okay. And the standard output will show the result of the unit tests, integration tests, and the doc test respectively. The doc tests are about testing the code embedded in the comments. This topic is not included in the video. That's why I can just focus on the unit test and the integration test. Okay. If we want to run the integration test only, we can use the following command to say that I want to just run the integration test, which is in the tests folder. Okay. So this part has already discussed the ways to do automated tests, including the unit tests and the integration tests. And we have already discussed a lot of ways to do the assertion in our tests. Now let's talk about closures and iterators. The first thing to talk about is closures. In Rust, a closure is an anonymous function that can be saved as a variable or passed to another function as an argument. This is a bit abstract. We will see a lot of examples in this video about the meaning of closure. So a closure is a pretty powerful tool than a function in that a closure can capture the values from the scope in which they are defined. We have no need to pass the values into a closure explicitly. That means the closure can capture values and the values can be used directly by the closure without really doing the parsing action. And we also don't need to annotate the input data type for closures, though we can still do so for clarity. That means the input data type doesn't need to be told very clearly, because the input data type can be inferred by the Rust compiler. And let us see some examples of closures. We can assign a closure to a variable, and a closure definition is quite similar to a function. If a closure definition has only one line, the curly brackets can be omitted. So let us see the simple example here. we have an example of a closure without any type annotation of parameters or even the return data type. So x and y here are not yet specified really clearly. So x and y can be integers or floats, it doesn't matter. As long as a person really passes some values into x and y, the data type of x and y can be determined on the spot. Okay, so we have two pipes here and there to really specify the parameters to be captured. And after capturing the two parameters x and y, I do the multiplication here, so that I do x multiplied by y, and this part will become the closure definition. Okay, so I can do this one. Rectangle area, which is 5 times 6, so I'm going to get 30 to be printed by the closure. So let us see this simple example. Okay, you can see that the data type can be inferred. So if I use 5 and 6 for x and y respectively, you can see that x is inferred as I32 and y is also inferred as I32. And we can see that the rectangle area here is really implementing a function trait called fn, capital letter F and small letter n. Okay, and the closure would be defined as x times y. Okay, so let us play with the program. You can see that I can get 30 as the answer, because 5 is responsible for parameter x and 6 is responsible for the parameter y. Okay, so if we do the print line macro here in this format, 5.1 and 6, then the compile time error would occur because we cannot multiply a float by an integer in Rust. So you can see that if we want to really execute the closure correctly, we have to also take care of the types used in the variables in the closure. Okay, so let us see another example of a closure with type annotation of parameters and of the return data type. So you see that I really specified the input parameter types. X is F64 and Y is also F64, and even the return data type is also F64. That is the meaning of explicitly denoting the data type for the closure. Okay, so when I pass two F64 values into the closure, I can find out the product of them. Let us play with this program. Of course, we have already specified the input data types and the output data type. That means the closure has no problem with recognizing the data type for our inputs. Okay, you can see the value coming out, which is the product of 5.8 and 6.1. Okay, we have some rounding issue here because we are handling float numbers, and sometimes floating point numbers may not be represented exactly. We have some ending decimals at the end. Okay, we have the third example of a closure. The inferred data types can no longer be changed after being inferred once. So when I have inferred x and y as both integers, we can no longer infer x and y as float after the first use of the closure. Okay, so let us see the result when I play with this program. Okay, you can see that the arguments to this function, or actually the closure, isn't correct because both input parameters would be expected to be integers, because I have already used the closure once, and x and y would already be inferred as I32 at the first time the closure is used. Okay, so after the first call of the closure, the variable types of x and y are already determined, and we can no longer change it after the first use, okay? And the closure can really capture the environment. What does it mean by this sentence? Let us see. The closure doesn't mention the parameters, but the parameters can be captured in the environment and then passed to the closure definition. And there is no need to pass the concrete values into the closure when we call the closure. What does it mean by that? Let us see. I have a sentence here. Rect area equals a closure, and you can see that the pipes don't include any parameters, right? But the definition of the closure would include x and y. So in this case, the input parameters are not included in the closure definition, but this closure can still be used because these x and y can be captured from the code, so that x and y would be just 5 and 6. So these two values of x and y would be captured by the closure by checking the same variable name. So this x would correspond to this x, of course, and this y in the closure would correspond to the y that is defined already out of the closure. Okay, so the closure is still able to be executed. So let us see the result of this code. So let us play with it. Of course, you can see 30 coming out, because 30 is just the product of 5 and 6. And you can see that even though I don't include the input parameters in the closure definition, I can still use the x and y which are defined outside the closure. Okay. And let's talk about capturing references or borrowing or moving ownership. So a closure can decide on its own the way to handle input parameters. So the input parameters can be handled differently depending on the way you tell the closure to do. So the input parameters can be handled by the closure itself. There are 3 ways for a closure to handle the input parameters. They can be borrowed immutably, or they can be borrowed mutably, or even the closure can take the ownership of the input parameters. So if we want to tell the closure to take ownership explicitly, even though the closure doesn't need to do so, we can use the move keyword before the closure definition. So we will see the example of using the move keyword to allow the closure to take ownership of the input parameters. So first, we take a look at an example of immutable borrow. So immutable borrow is implied when we don't change the content of name in this example. So I have a name here which is a string, and I want to tell a certain closure here to print out the name here. And if the name here doesn't change throughout the program, the greet variable here won't really take ownership of the string called name, which is here, okay? So even after calling the closure, the name can still be printed out because the name doesn't belong to the greet closure. Okay, so let us play with this code. Now you can see that I'm able to print the name. Okay, you can see that the name can still be printed out after calling the greet closure. So it means that the closure doesn't really capture the name string, okay? So if I don't change the name in the closure, I'm able to print the name again after calling the greet closure, because this closure doesn't take ownership of the name string, okay? Now let's see another example of mutable borrow. Mutable borrow is implied when we change the content of a name inside the closure. So in this example, the name string will be changed. And in this case, the name can still be printed out after calling the greet closure, but the name is changed. It is no longer Chris. it will be Christopher. So let us see this example. Okay, of course I have to make the name mutable, and I have to make the closure called greet mutable, because this closure is going to change a certain string. Okay, let me play with the program. Okay, you can see that Christopher has come out, which has already changed the variable called name, because the greet closure is able to push some string into the original string. So I have a push string method in the name here, and the name will be changed. And after calling the greet closure, the name is changed, and the closure just borrows the string. It doesn't take ownership of the string, so the print line macro can still be executed after calling the greet closure. Okay. A closure can sometimes take ownership of the input parameter explicitly. So the following code cannot compile as the name is moved to the closure. That means the closure has taken ownership of name. So when you see that I've used the moved keyword before defining the closure, the name variable will be moved to the closure, and the closure can be executed, of course, but after executing the closure, the name can no longer be printed because that name is part of the greet closure already. It is not able to be printed out. So let us see this result. Okay, when I save it, you can see that the borrow of moved value name has come out, and the value borrowed here after move message is also shown here. That means the greet closure has taken ownership of the name string. That's why the name here cannot be printed out. Okay. Now we can move the captured values out of the closure. So how can we do so? After a closure has captured some values or references from the environment, the closure can decide what to do with those captured values and references. So we have already seen 3 possible cases of handling the captured variables. Okay. And this action will really affect the things that will be moved out of the closure. And we have to consider something more for this topic. The way a closure handles the captured items will affect the traits that the closure implements. Okay. So we have a number of traits to handle the captured item for a closure. So let us see the previous example. We can see that the closure can implement some trait called fn in the third example. And for the second example, the greet closure implements a trait called fn mute. The first example here would have a closure that implements the fn trait. So we are going to talk about these traits. So we have a number of traits for closures. The closure would implement 1, 2, or all of the 3 traits. And we have to notice something. The trait would start with a capital letter F rather than a small letter f, okay? Because fn would refer to the function pointer type. We will use the function pointer type later. And we haven't seen this trait yet, which is called fn once. What does it mean by fn once? If a closure implements this trait, the closures can be called only once. And the closure that moves the captured values out of its body can only implement fn once trait and no others, because it can be called once only. So we can just take a look at the web page about the fn once trait. fn once trait is here. the instances of fn once can be called but might not be callable multiple times. So we have only one chance to call a closure that implements the fn once trait. Okay. So let us see an example. In this example, f is a function that implements fn once with no parameters. So I have a function called greet, and the trait is called f. And func here is also having a trait called f, where the trait is fn once. Okay. So I can use the where clause to figure out the trait of my function. Okay. When we use fn once trait, the function func here, which is this one, the function captured by the greet function here, cannot be called for the second time because the first call of it has forced the closure to take ownership of the value of name. Okay, so I will pass a name string to the introduce closure, and this closure would be passed to the greet function, and this greet function would allow a function or a closure that is implementing the fn once trait. Okay, so for the greet function here, I can only call the func once. That means I can just show introduce closure once, but not for the second time, because for the second time, the introduce closure is already captured by the greet function. Okay. So as the string on the heap is moved to the closure already, we cannot tell the closure to take ownership of the value of name for the second time when we call the func again. So let us see this example. So let me try to play with the program. When I pass the name to the closure is passed to the greet function, and the greet function is just going to execute the closure again. That's why I can see the sentence like, hello, this is John. John is captured by the closure, and the greet function is just going to execute the closure again. And here the trait bound is fn once. It means that the function func can be played once only, because you can see that func would have the trait bound as f, which is fn once. How about playing the function for the second time? Let us see. You can see that there is an error coming out. And the error would say that the function is already moved to the greet function. That means when I want to play the function for the second time, it is not allowed because the func value here is already moved to the greet function. And you can see that the fn once closure can only be called once. So we cannot call the func function for the second time. Okay. And this is the diagram to illustrate the situation. The first function call would allow the function to capture the string called John. And the second call of the function doesn't capture the name called John because that string is already captured by the first function call. Okay. So for the second time to call the function, this call doesn't find the name value already. Okay. And now let's go to the second trait for closures, which is called fn mute. The closure doesn't move the captured values out of its body. It can just mutate the captured values, and it can be called more than once. So if a trait is fn mute for a closure, we have these properties. So let us see the web page content from the documentation. So we can see that the instances of fn mute can be called repeatedly, and we may mutate the states. Okay. So let us see an example. And before we talk about the example, we have to say something more about the fn mute trait. If the f in the previous example is changed to fn mute, That means this part rather than fn once. And the greet parameter is mute func rather than just func. Then the func can be executed more than once. That means if it is mute func here, then the function here can be executed more than once. And with the use of fn mute trait, the closure doesn't take ownership of the value of name, so the John can be used by the function for the second time. So you see, I use mut func here for the function parameter of the greet function, and the trait bound of this greet function is fn mute. Then I'm able to call the function for the second time because the greet function doesn't really take ownership of the string, okay? So even though I change the content of the string, the greet function doesn't really take ownership of the mutated string. So let me play with the program. So you can see that the closure is able to mutate the name string, okay? And the greet function is going to make use of the closure. And the greet function is just going to execute the closure for 2 times. And for the first time, it can be executed certainly. And for the second time, it can still be executed because the trait bound of the greet function would be fn mute. It means the function here that is passed to the greet function, or the introduced closure that we passed into the greet function, can be executed more than once because it has a type called fn mute, okay? So let me play with the program. And you can see that I have really run the function twice, okay? So for the first execution, I just say, hello, this is John Doe. And you can see that the first closure would have the last name attached to John, okay? So this is the first function call. And for the second function call, I would even introduce the last name for the second time to the mutable string called name, okay? And the second function call of func, that means the second function call of the closure would include though for the second time. That's why I have this sentence coming out, okay? So func here refers to the closure that is passed to the greet function, okay? And because of the trait bound of fn mute, this closure can be called more than once, okay? And the situation is like this one. For the 2 function calls, they both can refer to the original string. Initially, the value is called John, but after the first function call, it becomes John Doe. And for the second function call, it would become John Doe Doe, okay? And we have the third trait called fn. If a closure has this trait, the closure doesn't move the captured value out of its body, and the closure doesn't mutate the captured value, and the closure does nothing from the environment. It also allows the closure to be called more than once. So let's see the web page of the fn trait. So fn would take immutable references to the captured variables or don't capture anything at all. So this is consistent with what we said. And let us go to the example below. We have a greet function whose trait bound is fn, okay? And when we use fn here, the function passed to the greet function can be called more than once. So let us see the result. You can see that we have this as John for 2 times, okay? Because the function can be called when the trait bound is fn only rather than fn once, okay? And the situation is like this. Both the two function calls can refer to the same string, which is strong, okay? The Rust book also mentioned unwrap or else function and sort by key method of vectors. We can take a look at these two functions from the documentation. The unwrap or else function has the trait bound of fn once. That means it can be used once only. And it can help us get the value obtained from the environment to see if it is able to capture the value from the option enum or not. If we have some 4 here, we can just unwrap this 4 out to make 4 as the answer. And if it is none, then we are not able to get the value out of the option enum, and we just do the else part. That's why we will be able to get 20 after the closure, shown here. So if it is able to unwrap, we just unwrap it. If it is not able to unwrap, we do the closure. That is the meaning of the unwrap or else function, okay? Let's go to the sort by key method for vectors. So this is shown here. We have an example here. We do the sorting by using the key. So if it is this vector, which is a mutable vector, we do the sorting by using the key shown here. I put the elements from the vector v, and then I take the absolute value of each of the values, and then I use the absolute value to do the sorting. So I will have 4, 5, 1, 3, 2, and I do the sorting according to the absolute value. And after getting the absolute value, I sort the original vector according to the absolute value of the elements, okay? That's why I will have 1, 2, minus 3, which is obtained by taking the absolute value to become 3, and 4 is still the same here. And minus 5 refers to the absolute value of minus 5, that is 5. So we had 1, 2, 3, 4, 5 for the order, but we take back the original vector value to be put into the sorting result, okay? Now let's talk about iterators. An iterator can help us to do some operations on a sequence of items. It can help us handle the logic required in doing iterations, and we have used the iter method to make an iterator. So we can have a vector first, and the vector can have an iterator by using .iter. Okay, so this variable becomes the iterator of the given vector, okay? And there is some interesting thing about iterators. They are lazy. What does it mean by this term lazy? We really need to call the methods and use up the iterator, or we need to consume the iterator. And in using iterators, there's no need to worry about the index of bounds error when we increment the index. So let us see how we can really consume the iterator in this example. So the iterator would go over all the elements of the vector one by one. So when we use the for loop here, the iterator here is actually able to go through all the elements one by one. So let us see the result of this code snippet. We can see that all the numbers in the vector can be printed one by one because of the use of the iterator, okay? The iterator is here, and the iterator is able to go over all the numbers one by one. And of course, the value of the vector would be inferred as f64, okay? And val here is just referring to the address of the value pointed by the iterator, okay? Iterator trait and next method. All the iterators would implement the iterator trait, which is already provided in the standard library. And the iterator trait has a method called next, which is used to show the next item of an iterable. And the iterator trait has an associated type, which can determine the type of the item returned by the next method. So we will see the example later on to illustrate this idea. Since it is possible that the next item is null at the end of the iterable, we need to wrap the item with some or none, where t here is the generic data type. That means we need to use the option enum to indicate that the result can be null when the next item is null. And when we use the next method of an iterator, we have to make the iterator a mutable variable. That means the iterator has to be a mutable one when we use the next method later, okay? And the next method would consume an iterator, so it can change the state of the iterator. That's why the iterator has to be set as mutable, okay? The next method can change the state of an iterator. And let us see this example. I have an iterator here, which is a mutable one. And I can use the while let statement to see whether the value in the vector can be taken out or not. So I can take out 6, 3, 0, and 5 one by one. But when the next method has consumed the last element, the element will become null. Then the value obtained by this expression here will become none. In this situation, I don't need to print out the none result. I just print out the previous 4 values captured by the sum variant, okay? So let us play with the program. Okay, you can see that the while let statement can help us capture the values in the vector one by one. And with the use of the next method, we can do the iteration, okay? So the first value to get is 6, the second one is 3, followed by 0 and 5. And when the next method goes to the end of the vector, it will become none. So in this situation, I don't print out none, I just stop, okay? So the next method of an iterator would return an immutable reference to an item of the iterable, okay? It means that the next method isn't able to really convert the values in the vector to another one, okay? And the next iterator to discuss is the iterator. The iterator can take the ownership of the vector. That's why we cannot print out the vector after the iterator is consumed. So this is an iterator, okay? This iterator would take the ownership of the vector. That's why after finding out the sum here, I'm not able to print out the numbers from the vector back. Let us see the example here. Okay, I can use the iterator to go over all the numbers in the vector, okay? And I can get the sum of the iterated numbers, okay? So I will be able to get 15 from the answer, and sum will become 15. And after getting the sum, I'm not able to get back the numbers vector because that vector is already moved into the iterator, okay? So let us see the result. The sum is now 15. But can I just print out the numbers vector back? You can see that it is not allowed because it has already moved into the iterator, okay? And now we go to another iterator called itermute. By using itermute, we can change the elements of an iterable in the course of using an iterator. So the value of the vector can be changed when we use the iterator. Same as itermute can give us a reference to the element of a vector. That's why we need to dereference the element to get back a number. The element here is that one, which is obtained from the iteration result. And the itermute method would give us a reference. That's why when I want to use the value, I have to really dereference it, okay? So let us play with the program here. Now we can see that the elements of the vector are all multiplied by 2, okay? And I have to do the dereferencing to get the element back, okay? Otherwise I would get the address of each of the numbers in the vector only, okay? Now let us talk about one term called consuming adapters. The methods that can call the next method are called consuming adapters, as these methods would consume the iterator. So if an iterator can be consumed, we call these methods consuming adapters. So we can have an example of a consuming adapter. The sum method is an example of a consuming adapter, because this method would take ownership of the iterator and consumes it to find out the sum of the items in the iterator elements. So the sum method here is called a consuming adapter because it takes ownership of the iterator and consumes the iterator. To use the sum method, we must explicitly give the associated type of this method. That means the return type of the method. So to use the sum method, we have to say I32 here explicitly. Otherwise, we are not able to play with the program. So let us see the result. Now you can see number 14 coming out. I'm able to sum up all the elements to get 14, but I have to really specify the return type of sum method. Otherwise, it cannot work. So let me try to play with it by ignoring the data type of my sum. You see, I cannot compile. You can see the sum method here implements the sum trait, and the sum trait really has to specify the data type. Okay. Now let's talk about another type of adapter called iterating adapter. Adapters that don't consume an iterator are known as the iterating adapters. So this kind of adapter doesn't consume the iterator. We know that iterators are lazy, so when an iterating adapter is present, we must provide another method to really consume the iterator. We have an example of an iterating adapter, which is the map method. Okay, the collect method is a consuming one, but the map method is an iterating one. So let us see the documentation for the collect method and the map method. So the collect method would transform an iterator into a collection. Okay, that is the meaning of the collect method. Okay, and how about the map method? The map method would transform one iterator into another. Okay, it takes a closure and creates an iterator, which calls that closure on each element. That is the meaning of the map method. So let us see our example. In this example, I have a map method, and I also use the collect method after the map method. So the map method is an iterating adapter. It doesn't consume the iterable, and if I want the vector to be really consumed, I have to use a consuming adapter called collect method. Okay. So here I made a certain iterator, and then I use the map method here that includes a closure to turn a certain value in the iterable to the square of it. Okay. And then I just want to pick up all the results from the map method, and I want to get a collection, and this collection is saved in my new vec. Okay, so let us play with the program. Okay, you can see that the element is inferred as I32. That means that my new vec would have I32 as the content, which will be the square of each of the numbers in the original my vec. Okay, let us see the result. Now you can see that I have 36, 9, 0, and 25 as the answer, because I used the map method to return the square of each of the numbers in the vector, and I get the collection by using the collect method to really consume the iterator. Okay, this iterator will be consumed by the collect method, but not the map method. Okay. Now let's take a look at the closures that capture the environment. The filter method is a method that can really capture the environment variable. So I'm going to use the filter method. So we will have an example shown here. In this example, the num variable, which is this one, will capture the numbers vector that is passed to the filtered numbers function. And then the iterator of the numbers calls the filter method. So let us see what it means. I have a vector here, and I want to have a function called filtered numbers, which has a vector as the function parameter, and then the return type is also a vector. And how can I handle the input parameter called v? I make an iterator for the vector v, and then I use the filter method to do the filtering. How can I do the filtering? I want to only get the odd numbers only from the vector. So when I get the number from the vector, I'm able to see whether that number is a multiple of 2 or not. If it is not a multiple of 2, then I will retain them, and I'm going to collect all these odd numbers, and it will become the new vector to be output, because this one is an expression. Okay, so we can see that the filter method can really capture the environment variable. The environment variable for the filter method to capture is the numbers in the vector v. Okay, and of course the numbers here is already moved into the function called filtered numbers. That's why the original vector called numbers can no longer be printed out. So let us play with the program. The filtered numbers would be 1, 3, 5, 7, 9, because the filter method here is going to just pick up the odd numbers, and I do the collect method to really get the collection of those odd numbers, and I will just return the result from the function. Okay, and the numbers vector is already moved into the filtered number function. That's why it cannot be printed out after the movement. So when I want to print out the numbers, you can see that the borrow of moved value numbers is shown here, because the numbers vector is really moved into the function. Okay, so let us take a look at the filter method. So the filter method is something like this. It creates an iterator which uses the closure to determine if an element should be yielded. If we have an element, the closure must return true or false to see whether that element has to be retained or not. We just retain those values that can return true from the closure. And finally, we talk about the performance of iterators compared to loops. Actually, iterators are more or less as fast as loops. Since we don't need to care about whether the index is out of bounds by using the closures, by using the iterators, we can just use iterators to do the looping, and it is actually the conventional way of doing looping in Rust. By using iterators, it is more idiomatic than using loops in Rust. So this part has discussed a lot of things about closures and iterators. Now let's take a look at this exercise. I want to find the sum of the squares of the composite numbers stored in a vector. And I need to pick up the composite numbers in this vector and square each of those picked numbers and find the sum of those squares. How can I do it? I want to use closures and iterators to complete this task. Before I do so, I have to provide the vector first. So I have this vector that stores 1 to 11, okay? And the vector would have the elements of I32 type, okay? Now I want to use iterators to solve this problem. When I use iterators, I want to use closures as well. So let me show my solution step by step. So I want to use an iterator first so that it can loop over all the vector elements one by one, okay? And when I pick up any one of the numbers from the vector, I want to do the filtering so that I can pick up the so-called composite numbers from those elements in the given vector. How can I do so? I can use the filter method. Now, I want to make an idea like this one. I want to pick up the numbers from the vector. I want to do the filtering. So for each number obtained from the iterator, I call it as enum. And for enum, I have to really pick up the reference to each of those elements in the vector. And I want to do the dereferencing of the reference to check that whether the number is larger than or equal to 4. If it is a number that is at least 4, it means that it is possible to be a composite number. So I want to pick up the possible composite numbers from the given vector. So it has to be at least 4. And at the same time, that number has to be a... So how can I check that whether that number is a composite number? I can use the next part. In addition to having a number that is larger than or equal to 4, I also need to do the checking here to see whether that number is a composite or not. So the checking is like this. I want to start with number 2 because 2 is the smallest possible prime number. And we end with a number before the particular number picked up from the array. So this closing bracket means that I don't really reach the num value exactly. I just go 1 before that value, okay? And from these numbers, I would put them into a certain iterator called any here. The any iterator would try to do something like this. For those numbers from this part, I call each of them as I. And I want to check that whether num here is divisible by any I here. So if this division gives me a remainder of 0, it means that our number picked from the array is able to be divisible by a number that is at least 2, and that is also just before my picked number. So if number is 6 here, I need to test whether 2, 3, 4, or 5 can make a division of 6 so that I have no remainder remaining. If that's the case, the number is really a composite number, then I really need to pick it up. Okay, so this filter iterator is trying to filter out the composite numbers, which is checked by these 2 composite logic operations, okay? And after I have picked up the composite numbers, I want to add the squared numbers up. How can I do so? I can use the fold iterator. Okay, the fourth iterator is going to do something like this. It has an initial value of 0. I want to start the sum as 0 first. And how can I handle the sum? I need an accumulator called ACC. And the initial ACC value would be just the initial value put into the fourth iterator. And I want to pick up the filtered numbers obtained by the filter iterator into X. And as we know, all the filtered numbers are composite numbers. That's why I would just square each of the composite numbers that is filtered by the filter iterator. And after the square, I will add it to the previous value called accumulator. Initially, it was 0, but after the first composite number picked up, which is 4 in my case, I will have 0 plus 16, which is 4 times 4. So I will get 16. And after the second composite number to pick up, I will have 6 times 6, which is equal to 36. So 36 plus 16, which is the accumulated value, I would have 52. So on and so forth until I have checked all the squares of the composite numbers in my vector, okay? So you will expect that I will have 4 squared plus 6 squared plus 8 squared plus 9 squared plus 10 squared, and this will be the final answer. So the accumulator is trying to store the intermediate result after each squaring of my composite numbers, okay? So I'm going to print out the result by using a printline macro. So that is the major idea of this program. I want to pick up the composite numbers from the array, and I get the square of those composite numbers by using the fourth iterator here, okay? And the way to pick up the composite numbers is to use the filter iterator that accepts a certain rule here, okay? So let me check the error first. Okay, when I just save it, it is okay. So I don't have any error in this code. So let us play with the program. You can see that the answer is 297. Why? Because it is just equal to 4 squared plus 6 squared plus 8 squared plus 9 squared plus 10 squared. So altogether, I would be able to get this answer by using the filter iterator together with the fourth iterator. Before I use these two iterators, I have to use the iterator iter to really pick up the elements from the vector. Now, in this section, I'm going to discuss the smart pointers in Rust. The first smart pointer to discuss is the box pointer. So, what is a box pointer? A box pointer can wrap a value that is stored on the heap, and then the box pointer is stored on the stack. So the box pointer is on the stack while the value that is pointed by the box pointer is stored on the heap. And the box pointer is helpful in these situations. Let us see each of them. When we don't know the size of an item at compile time, but we want to handle it as if its size is already known, then we can just wrap that content of a known size in a box pointer. And when we want to transfer ownership of a large amount of data, but we don't want to do the copying on the heap, then we can use the box pointer to help us achieve this task. So in this situation, we can do the transfer by using the box pointer without really touching the data stored on the heap. The third situation is like this. When we want to own a type that implements a certain trait, but the data type itself doesn't matter. In this situation, then we can also use a box pointer, and we can use the trait object to help us do so, and we will discuss the trait objects later. Now let us see how we can use a box to store the data on the heap. The idea is to use the new method, which can help us make a box. So we can have a certain example below. The variable x is put on the stack, while the number that is represented by the variable, which is 9.2 here, will be put on the heap. So we can access the value in the box directly. So even though the data is on the heap, we can use the variable to access it directly because a box pointer implements the deref trait. Deref means the reference. So we will discuss this deref trait later. And when the scope of the box pointer ends, the stack variable plus the heap data are both cleaned out. And the box pointer is cleaned up because it implements the drop trait. So when the scope of a box pointer ends, it can be removed immediately because of the drop trait, and we will discuss the drop trait later. So how can we use the new method? We can have an idea like this one. Let the variable be x, and then I use the box package, and in this package we have a new function. So I can put 9.2 into the new function. In this situation, I can have a stack variable which is x, and the data 9.2 will be put on the heap. And I can just use print line macro to get the value of 9.2 easily because of the ref trait shown here, okay? So the box pointer has a name called x, and this box pointer is pointing to a value on the heap, okay? So let me try to play with this simple program. Now you can see that the variable called x has an inferred data type of box pointer type, and the value that is put in the box pointer will be f64, which is just meaning 9.2 shown here, okay? And when I print the value of x directly, I can get 9.2 because of the use of the deref trait. And of course, when the scope of this main function ends, the drop trait is also implemented so that the box pointer together with the value stored on the heap, which is 9.2 in my case, will both be cleaned up, okay? Another situation that we can use the box pointer is the box on recursive data type. So a recursive data type is a type such that part of the data value is of the recursive type itself. We don't really know the exact size of a piece of recursive data at the compile time because we don't know when the recursion will stop. So we have a recursive data type so that the data has a portion that relies on the type itself. So we will have an example which is called a list. So a list can be represented by the recursive data type. A list can have another list as part of its value, and the other list is also wrapped by a box pointer. And we have a chain of the lists. And the whole chain is stored in a chain of box pointers. So we will have a diagram to visualize the chaining later. So effectively, a number follows a box in which it has a number and a box, and we can do this chaining recursively until a new value is stored finally. The new value here will try to stop the recursion process, and we will have the real end of the chain. The process of storing indefinite amount of data in recursive data type is called indirection. So it means that the box pointer type is able to help us achieve indirection. And we don't need to know the size of the box pointer. We just need to know that the size of it is fixed. So it means that the box pointer has a fixed size. So the box pointer will be treated as usual values stored on the stack. And let us see this example. So I want to show the content of the list easily. That's why I derived the debug trait. And after the derivation, I can have an enum data type. So the enum type is called a list. And the list will store some generic data type t. And the list enum has two variants. One is called the node, and the other one is called new. New means nothing inside. And if we have the first variant has two parts to include the generic data type in the value format, together with a box pointer that stores a list that stores the generic data type t. So you can see that the list here appears again, which is having the same name as the enum shown above, okay? So when we have this kind of relationship, this list will be called based on the enum type. And you can see that when I have list here, the list will incur a node again, and this node will incur another node again until the final value of the list is really a new value, okay? So this is a bit abstract. I can use an example to illustrate the use of the list enum in my case. So now I make a list, and the list is of course of list type, which is storing F64 type, okay? So you can see that I have the first value, which is 2.6, indicated by the node variant, and the second value of the node variant will be a box pointer. So the box pointer is going to help me store another list variant, which is another list. So the value of the node is 7.5, I mean for the second node that is linked to the previous node. And the third node will be linked by using the box pointer put on the second node, okay? So the third value would have 4.1, and the second value to be put on the node variant is the box new, list new, okay? I have a box pointer, and in this new pointer, I put a new here, which is coming from the list enum. So new here is another variant of the list enum, okay? Which means this variant of the list enum, okay? So when I have the new variant here, the list really ends. I don't include another box pointer to store another node, okay? So when I want to show the list content by using the printline macro, I will be able to see the chain, which is represented by this diagram. So the first element is having a number of 2.6, and the second part of the node will be a box pointer that points to another node that has a value of 7.5, and the second node will have a part that joins the third node whose value is 4.1, and for the second part of the node, I have a box pointer represented by the arrow to link to the new value as my list variant, okay? So when I have the new value here, it means that the list ends. I don't have to join another new node, okay? So let us see what we will get by playing with this code. Now let us play with the program. So if I ignore the warning, which is talking about the box pointer that is not really used in the main program, I can see that the node is like this one. You see 2.6 is the first value in the list, and 7.5 will be stored in the node that is joined to the first node. And the third node here will join to the second node. And finally, we have a new variant that is put in the second value of the node, okay? So in this situation, we can end the list that is done by joining all the nodes together until we see the new variant, which ends the joining, okay? Now let us talk about the deref trait. By implementing the deref trait on box pointers, we can treat the smart pointer as a regular reference. So what does it mean by this thing? Let us do some simple revision of the regular references. For regular references, we use an ampersand to get the reference to a variable, and we also use an asterisk to dereference a variable and get the value. And for regular references, automatic dereferencing can be done for values on the stack. So let us see the following simple example. we have a value on the stack which is 42. So this is an integer, and integer will be put on the stack. So value is stored on the stack. And the reference here is going to link to the reference to a value that is represented by the previous line. Okay, so reference here is helping us to use the reference to locate the value above. Okay, so value is stored on the stack. That's why I can do the automatic dereferencing so that the value can be printed out easily. And for the reference here, since it is of reference type, I can do manual dereferencing by using an asterisk so that I can get back the value that is pointed by this reference variable. Okay, and for regular references, the reference can undergo dereferencing automatically. That means I don't need to put an asterisk to do the dereferencing. Okay, so let us see the result of this code. Okay, you can see that the value is 42. That is able to be printed because it is a value put on the stack. And you can use an asterisk to really help us do the dereferencing. Or if we can just use the reference variable name directly to do the automatic dereferencing. Okay, so all the three values will be 42. The first one comes from the stack directly, and the remaining two would come from the reference directly. Okay, so all the previous things are about regular references. If we want to wrap a value with a box pointer rather than a regular reference, the heap would have a value that is pointed by the variable on the stack. And automatic dereferencing would take place in Rust to get the value back, although manual dereferencing is also allowed. So we can see an analogy that is shown below. Now the value is not a value that is put on the stack directly. It is wrapped by a box pointer. So this value here is actually a reference to the value of 42 that is wrapped by the smart pointer called box pointer. Okay, and the reference variable here is just the reference to the value shown above. Okay, so I can still do the automatic dereferencing even though the value is wrapped by a box pointer, because the referencing can be done automatically. And for the reference here, I can do manual dereferencing as well as the automatic dereferencing. So you can see that this example will be very, very similar to the previous example. So for stack values or the values that are wrapped by the box pointer, the same treatment would apply. So let us see the result. Okay, you can see that I can still get 42 as the value, and the reference will do the dereferencing immediately so that both the values would be 42, which is a value wrapped by the box pointer. Okay. Now let us talk about the deref trait. We can create our own deref trait rather than just using the default deref trait provided by Rust for our user-defined box pointer. So what does it mean by this one? We can have an example below. Before we discuss this example, let us see the deref trait in Rust. For the deref trait, we have an associated type called target, which has a size that doesn't need to know. So that's why we have a question mark before the sized keyword. Okay, and we have a deref method to implement, and the deref method would try to return the reference of the target type. Okay, so let us see the documentation. Okay, it is the repetition of what I said previously. Okay, so it is used for immutable dereferencing operations. So we can do dereferencing by writing our own deref method after using the public trait called deref, which is already provided in Rust. Okay, so how can we create our own deref function? Let us see this following example. Now I want to write my own deref method before doing so, I have to import the deref trait by using this line of code, standard OPS, and we get the deref trait. So OPS here means the overloadable operators, okay? So we create our own struct called myStruct, which accepts a generic data type, and the generic data type would be corresponding to the value field in this myStruct, okay? And for this myStruct, I implement the deref trait, and I need to write my own deref method. So I have to include the associated type, which is called target, and the target is having the type T, which is just meaning the generic data type that is used in the myStruct structure, okay? And if I want to say deref here, I can return the reference to the value of the instance, okay? So the type is &self target. So I refer to the target type, which is just T, and self here means the data type of the instance, okay? And let us go to the main function. I make a certain instance called myStruct, which has a value of 25. So 25 is the value of my field called value, okay? And I can do myStruct.value to really get the value back by using the deref trait together with the deref method that I write here. So when I want to get the value of the field called value, I can just implement the deref trait and use the deref method that I wrote to really get the value of a certain field, okay? So let us play with the program. Okay, you can see that I can get 25 because when I use the printline macro to include the field name, I'm able to get the value corresponding to this field. That is the purpose of writing the deref function by implementing the deref trait so that a certain structure instance can get the field value easily, okay? The next part to talk about is the deref coercion with functions and methods. According to the Rust book, deref coercion would convert a reference to a type that implements the deref trait into a reference to another type. So this is a bit abstract. There's an example of the deref coercion. For example, the &string type can be converted to a string slice by using deref coercion, as the string type would implement the deref trait. So you can see that the deref coercion would help you change a reference type to another, okay? The original reference type called string will be converted to str, which is meaning a string slice, okay? So doing so can facilitate code writing by ignoring too many explicit referencing and dereferencing. So when we use deref coercion, we can have an easier life by forgetting the rigorous referencing and dereferencing requirements. So the deref method provided by the deref trait is given below. So let us see the following page. So that is the deref function. And for string here, if we have a string, we can have the default deref method that turns the string to a string slice so that we can do the printing more easily by referring to the string slice that is obtained by the deref method, okay? So you can see the associated type would be of str type. Okay, another thing to consider is the deref mute trait. Mute means mutable. If the reference to a value is mutable, we can implement the deref mute trait. There is a method called deref mute for us to implement. So after implementing the deref mute trait, a mutable reference can have its corresponding value changed. So the return type will be self target, but it is a mutable one, okay? So I'm able to get back the associated type as the return value, okay? To implement the deref trait, we have to implement the deref trait first. So when we do deref, we have to include the deref trait as well. We cannot just include the deref trait without mentioning the deref trait. Okay. So let us see the following example. I want to overload the operators from the deref trait and the deref trait. And I have the same structure called my struct, and it has a field called value, and this value will be of generic data type T. Okay. And for this structure, I want to implement the deref trait so that I can write my own deref method. And of course, I have to include the associated type, which is called target, and the target would have a type depending on the generic data type. And for this deref method, I want to get the value of the value key. Okay. And now I want to implement the deref trait for my structure. And the deref trait is something similar. I want to return the value of the mutable reference of the value field. So here I use &mut to indicate that the value pointed by this reference can be altered. Okay, so let us see the main function. I create my instance called my struct, and I can dereference my struct, and I can change the value of it to 10. So it means that the field value would have a new value of 10 rather than 25 initially. I can use the myStruct.value statement to really get the field value back. Okay, so this part is for the deref trait shown here, and the second line here refers to the deref trait. Okay, in this deref function, it means that the value can be changed. Okay, that's why when I do the dereferencing of the instance, I'm able to do the assignment again to change the field called value to have a value of 10 rather than 25. So let us see the result of these lines of code. Okay, you can see that the value can be changed to 10 because of the use of the deref method coming from the deref trait. Okay, and of course the printing would come from the deref trait together with the deref method. Okay, so here the target would mean the generic data type T. Of course, we can take a look at the documentation to see the meaning of the deref method in the deref trait. Okay, you can see that I can use the deref method to really mutably dereferences the value. That means I can do something like here. If I write my own deref method, I'm able to handle the dereferencing manually. Okay. Another trait to discuss is the drop trait. The drop trait would decide how a variable would do when it is about to leave the scope. And we need to release the memory resources so that a value won't leak memory. And if a box pointer is to leave the scope, we need to implement the drop trait. So it is about the way to really release the memory after the box pointer has served its purpose and we want to quit the program. So there is a method called drop, which is the usual one. The drop trait has a drop method to implement, which takes a mutable reference to self and the instance that calls the drop method. Okay, what does it mean by this one? Let us see the simple example below. I have a structure, I have a field called data, and the data will be of string type. Okay, and we can implement the drop trait, and in this drop trait I have a drop function to handle. So when the variable is dropped, it means that it ends its scope, and when the scope is ended, I want to do a print line macro shown here. Okay, and of course I want to show the statement including the data that is held by the instance. Okay, self.data means the data contained in a given instance. Okay, so let us see the main program. I have a mutable reference whose data is called example data1 in the form of a string, and I also have another mutable reference, and the data is example data2, which is put in the form of a string. So I have two mutable references, and each of the mutable references would have a field called data. Of course, the data would have some value inside. And here I can do the reassignment of the data field. So the data field will have another new string to replace the original string that is stored in the instance. Okay, same for the my struct2 instance. Okay, so the data field will be changed to another string. Okay, and the program would end after these two reassignment, and we can see the dropping effect, so that the drop method will help you release the memory of the instances. So let us play with the program. So let us go to the main function. The main function would do the first print line macro, do something with my struct, and after the reassignment of the data field of the instances, I would say the program ends. So after the program ends, you can see that the drop method will come out. So it will say dropping my struct with data called new data2. Why is it new data2? Because this is the value obtained by reassigning the my struct2 dot data. Okay, since my struct2 comes later than the my struct1, it will be cleaned first. So that's why my struct2 will be cleaned first here, and you can see that during the cleaning, you can get the new data that is reassigned before the whole program ends. So originally the string was example data2, but now you can see that the reassignment works so that the cleaning action or the dropping action would give the new data coming out. Okay, and the second instance to drop is my struct. So you can see that the final sentence is dropping my struct with data, new data1. It means that the variable that comes earlier would be cleaned later. Okay, so you can see that the assignment really works. So the assignment works, and the dropping action would demonstrate the successful reassignment. Okay, so you see new data1 here. That means the assignment here is successful. Okay, so you can see that the dropping action would usually start after the end of the entire program, but we can drop the variables early with the use of the package here, std mem drop. Mem here means memory, so we have some libraries to help us handle the memory. And Rust would disallow early call of the drop method in fear that it would cause double free error. So if we do the dropping in the middle, after the program ends, the variable will try to be dropped for the second time. So we will have the double free error in this case. However, we can make some variables to drop before it goes out of scope naturally. How can we do so? Let us see. We use the drop function from the standard library directly, which is in the prelude already. So we can have the drop function shown here. So the drop function is provided in the prelude, and we can just use it directly. Actually, we have the similar piece of code as before, but the different thing is that I really drop the first instance before I print out the final string shown here. So let us see what will happen if we really drop the first instance before the end of the program. So the difference here is that I have a drop function to call explicitly. So you see the order of the printing will be a bit different. So the first printline macro is done here, and before I do the second printline macro, I already do the dropping of the first instance. So when the dropping action is really achieved, I will just do the printline macro here to do the description of the dropping. Okay, so I dropped the first instance, so you can see that the assignment is really working before I call the drop function. Okay, so after the assignment, you can see that the string here becomes new data 1. So you can see that the drop function can be achieved before the end of the program. Okay, and of course, after the final macro is executed, I will do the dropping of my remaining instances. So I have one instance to do the dropping after the program ends. That's why I will have new data 2 coming out, which is obtained by calling the drop function again for the second time when the program really ends, to clean my remaining instance. Okay. Another smart pointer is called RC pointer. RC here means the reference counted smart pointer. A single variable might have more than one owner. To enable multiple ownership, we use RCT, known as the reference counting. Okay, so RC here means the reference counting type, which is a smart pointer. An RC smart pointer would store the number of references to a value. If there is no references, then the variable can be deleted. So we will have some illustration of this point later. So we can see that an RC pointer would remember the number of references to a certain variable. That is something we have to remember. An RC pointer is useful when at compile time we don't know which variable will be the final holder of the reference to a value on the heap. So it is possible that there are multiple variables that would point to the same value on the heap, and we don't know which of these variables would be the final one to hold the data. That's why we can rely on the reference counted pointer to help us remember the final holder. Okay, if we knew the final holder, we would just have told this variable to hold the reference, but we don't know the final holder all the time. That's why we have to rely on the reference counted pointer to help us find out the final holder. And remember, RC pointer is for single-threaded processing only. Okay, we cannot use concurrency to handle reference counted pointers. Okay, so let us see the following example. I want to use an RC pointer to share data. What does it mean by the sharing here? We can have an example to illustrate the sharing. For example, we have two immutable references that point to the same list node, which links to a chain of nodes. Since the two references can own the same list node, we can use the RC smart pointer to achieve the idea of two immutable references pointing to the same list node. Okay, so we can use a smart pointer to represent the recursive data type that is part of a list variant. We can do the cloning by using the RC pointer. So I can use this syntax to make another reference on a certain piece of data on the heap. So this method doesn't really make a deep copy. When we use the RC pointer, it is just able to increase the reference count by 1. Okay, we don't really make a new thing on the heap. We want to use an RC pointer to point to the same part on the heap. Okay, in doing so, we can have a faster processing than making a deep copy by using the list1.clone. Okay, so we will see the following example that uses the RC pointer instead of doing the deep copy. Okay, so I have a list here. The list enum will have two variants, node or new. So the node here includes two parts: the generic type that is passed to the list, together with the RC pointer that stores the list here. So the list is a recursive data type because you can see that I use the same enum name in the variant. Okay, so I have to import the enumeration, and I have to include this line to really import the RC pointer, okay, because it is not in the prelude. And let us take a look at the main function. We can use the node and new directly in this scope because we have already brought them to the current scope by using the first statement shown here, okay. And now we have a reference counted pointer, and we make a new one by using the new function, okay. And here you can see that I want to store a node. The first value of the node is 2.6, and the other part of the node is another reference counted pointer, which really points to a node whose value is 7.5, and this node also has another value that is an RC pointer, which points to a node having a number of 4.1, and the second part of this node is an RC pointer that stores the new value, okay. So the chain ends when we include the new variant, okay. So when I make another list called list2, I can use this one to help me do so. And you can see that I can use the RC clone function so that the reference count of list1 will be increased by 1. So list1 and list2 would use the same memory content on the heap, which is represented by this long chain, okay. And for list3, you can see that I also use list1. So the reference counting of list1 will be increased to 3. You can just understand the use of the RC pointer to do the linking in this case. So for list 2, the first value is 6.8, and for list 3, the first value will be 3.7. So let us see what will happen if we print out the list contents. Oh, I forgot to get rid of this part. Okay, you can see that the error is gone. Now you can see that when I want to print out list 1, you can see the chain coming out. 2.6, 7.5, 4.1, and new. So that is the natural list. Okay, how about list 2? List 2 would start with 6.8 and it would join list 1. So you can see that it is 6.8 at the beginning, and this part is just the list 1 shown here, okay. And for list 3, it would start with 3.7, and the remaining portion would be just the repetition of list 1 shown here, okay. So you can see the similarity of these three lists, okay. And we mentioned that the reference counting of list 1 will turn to 3 because we have 3 variables, list 1, list 2, and list 3 that would rely on the same portion of the heap allocated memory, okay. And we are going to discuss how we can show the reference counting in Rust. And let us try to visualize the chain as follows. So the first chain, which is the first list, it would be having an RC pointer that wraps 2 parts, which is actually storing the node. The node has 2 parts. The value together with another RC pointer. So for the second RC pointer that is wrapped inside, it stores a node. The node will store 7.5, followed by another RC pointer. And for the innermost RC pointer, it will have a node. The first value of the node is 4.1, and the other value of the node is just new. That's why we can see the relationship shown in the first list, okay? And we can clone an RC pointer to increase the reference count. What does it mean by this one? Let us see. We can use the strong count function to see the current reference count of a variable. So we can take a look at the documentation first. So we can use the strong count function to get the number of strong RC pointers to this allocation. Allocation means the memory allocated on the heap. Okay. So we will play the strong count function later. Here we have an example program. I have a structure here, and before declaring my structure, I have to include the RC pointer module. Okay. And in the main function, I use an RC pointer to wrap the instance. Okay. The instance is having a piece of data of 42. So my struct here is really a representation of the RC pointer. Okay. And the strong count means the number of references that is connected to the heap allocated memory. So after the first print macro, I would have 1. And if we do the cloning by using the clone function of my struct instance, the reference counting of the my struct would be turned to 2 because we have another variable that would also point to the same piece of data on the heap that is represented by the my struct variable. Okay, so we will have 2 here after the second print macro. And now we have another inner scope shown here. Okay, this inner scope has another cloned structure 2 to be declared. So this second cloned structure would also need to clone the my struct content. Okay, so you can expect that the strong count would turn to 3 because this name, and this name would point to the same portion of the heap allocated memory. So when the scope here ends, we have really dropped the second cloned structure. So the strong count would be turned to 2 because this reference is dropped already. And if we do the dropping explicitly to remove the first cloned structure, the strong count would turn to 1 because I have only the my struct variable that points to the heap allocated memory. Okay. So let us see the result of these lines of code. You can see that the first print macro gives you 1. The second print macro gives you 2 because the cloned struct 1 would rely on the my struct here. That means the same portion of the heap allocated memory would have 2 references. And after the cloning inside the inner scope, we will have 3 references that point to the same heap allocated memory. And after dropping the second cloned structure, we have only 2 remaining. And even after dropping the first cloned structure explicitly, I have only 1 strong count remaining. Okay, and here we have to notice something more. After the end of the program, the strong count would drop to 0 as the very first variable called my struct is also dropped. Okay, because we are not able to show the effect after the program ends, the strong count of the my struct value cannot turn to 0 before the code really ends. Okay. Now let's talk about another smart pointer called refcell pointer. When we use refcell pointer together with the RC pointer, we can provide interior mutability. It means that we can mutate the data even if we have immutable references to the data. So this one is a bit difficult to understand. We will use some examples to illustrate the interior mutability. So initially for RC pointer, when we use refcell smart pointer instead of a box pointer as before, we can let Rust check the borrowing issue at runtime, and refcell allows multiple borrows checked at runtime, and the value of refcell can be mutated. So that is the advantage of using refcell instead of the box pointer. The value referenced by the refcell smart pointer can be changed. And we can let the program check the borrowing issue at runtime. So we can do the mutable borrows at runtime. If ref cell has borrowing issue at runtime, the program will just panic, okay? So we have to make sure that the borrowing can be done at runtime. On the other hand, the box pointer will stop borrowing errors at compile time already. So we can delay the borrowing issue to runtime. Okay, that is something box pointer cannot do, okay? So the purpose of checking borrowing issue at runtime is that we can have some memory safe scenarios that would be disallowed by the conservative Rust compiler. If the compiler is not sure that an action is memory safe, it just disallows compilation. So we can use the ref cell to make the rules a bit more lenient than before, as long as we know that these actions are memory safe, okay? And ref cell is applicable to single-threaded scenarios only, okay? We cannot use it in the concurrency case, okay? So when we use the ref cell, we have to remember some rules. The first one is that immutable and mutable references cannot appear together. We can make an immutable borrow with the borrow method, and when a value is wrapped by the ref cell, the error will become a runtime error instead of a compile time error, so the compiler can pass the immutable borrow, and the code can compile with the use of cargo build command, but fails with the cargo run command. We will show some demonstration to see why that is the case. So let us see this example. I want to bring ref cell to the current scope, and I have my struct here, and this structure has a field called value, which is wrapped in the ref cell, okay, and the data to be wrapped is of i32 type. So in order to create my instance, I can say value colon ref cell new 42. So I use the new function to make a new ref cell that stores 42 inside, which is of i32 type. And now we want to borrow an immutable reference. We can just do borrow to really borrow the field which is value inside the myStruct instance, okay? I can dereference the borrowed value to get the value, okay? Is it possible to borrow a mutable reference while an immutable reference is active? It is not allowed. At runtime, it will panic since it violates the borrowing rule. We cannot have an mutable reference and an immutable reference together. So if I want to do something like this, it is not allowed at runtime, but it can be allowed at compile time when we use the ref cell pointer, okay? So I make a mutable reference and I want to change the value. That's why I use the borrow mut method. And after making this mutable reference, I want to change its value to 10 by doing the referencing. And I want to show the updated value in the pre9 macro. What will happen when I play with the code? Let us see. Okay, when I do cargo run, you can see that I will have some error coming out. Okay, I have a panicking shown here on line number 183, which is this one. So you can see that I'm not able to do the borrow while activating the mutation feature. I have already got a certain immutable borrow here, and at the same time I can never have another mutable reference to the same value on the heap allocated memory. That's why this line would fail. I can show the borrowed value here because this part works, but when I go to the other part, I'm not able to show the pre9 macro here because the previous lines of code has already failed at runtime. Okay. So how about using the cargo build command? Let us see. You can see that the compilation really works. I can really pass the compilation. So when I use the smart pointer, which is called ref cell, I can allow the program to compile, but when it is executed, the program fails because it violates the rule that we cannot have both immutable and mutable references together. And we have to follow another rule when we use ref cell. When we want a mutable reference, we have to remove the immutable ones first. And we can make a mutable borrow with the borrow mut method after the removal. How can we do so? Let us see. Here we have the similar code as before. But when I want to do the mutable reference, I have to really drop the immutable reference first, so that the value can be changed after eliminating the previous immutable reference, so that I have only one mutable reference remaining. Okay, so I can do the mutable borrow here, and then I can change the value of that borrowed value. So let us play with the program. And let me play with the program. You can see that the borrowed value was 42, and after the dropping, I can do the mutation so that the updated value is now 10. So you can see that when I use cargo run, I don't have any runtime error coming out. That is the purpose of doing dropping here, so that the same heap allocated memory would not have both immutable and mutable references together. Okay. And we have to notice something more when we use the ref cell pointer. There can only be one mutable reference. Okay, so that is something we have to remember, even though we can use ref cell to avoid the compile time error. So I use the ref cell module, and then I make a structure as usual, and I make a certain instance for my structure, and then I make a mutable borrow here, and then I want to make another mutable borrow. But you can see later that the program can compile, but there will be a runtime error because we cannot have two mutable references at the same time. So let us see what would happen. Of course, the program would like to change the borrowed value to 10 rather than using the original value of 42, but it will fail. Let us see. You can see that there is a runtime error already borrowed. At line 219, you can see that we will have the runtime error because the mutable borrow has taken place beforehand. We cannot have multiple mutable borrows. Okay, so I'm even not allowed to change the first borrowed value because the previous line of code has already stopped me from going further. Okay, how about the compilation alone? Let us see. You can see that there is no error, even though we have some warning here. Okay, what does the warning mean here? Let's see. It just says that this variable is not used in the further part of the program. If I don't print it out, I will have this warning, but you can see no error coming out. That means the program can compile basically, except the warning that tells me to use this variable in the future. Okay. So if we want to allow multiple owners to mutate the data, we can have an idea as follows. We can use rc ref cell t to allow a value to mutate due to the ref cell, and to have multiple access due to the rc here. So a reference counted pointer can allow us to have multiple ownership, and ref cell here can help us to allow a value to mutate. Okay. And the outer part of this is immutable. I mean, rc pointer is immutable, but the inner part, which is ref cell, is mutable. Okay. So that is the meaning of interior mutability. The inside can be changed, but the outside cannot be changed. So for example, we can change the value of a list node in a chain of nodes by using interior mutability. Let us see the following example. I have an enumeration called list, and there are two variants for this enumeration, node and new. And for the node, there are two parts. The first part is the rc refcell t, which is going to store a number, and rc list here is the recursive component of the enumeration. So it can help us to join another list to the previous node, okay? So let us go to the other lines. I have to bring the list enum to the scope together with the two variants. And of course, I have to bring the ref cell together with the rc pointers to the scope, because both of them are not in the prelude, okay? So in the main function, we can use the node and new variants directly, because I have already brought them to the current scope. So now I have a list here. The list is quite long here. I use an rc pointer here to wrap the list enum, which has a variant called node, and the node would have an rc cell here, and the rc cell would wrap a ref cell which is having a number of 2.6, and I want to make the other part of the node by including an rc pointer that wraps another node, and the node would have the value as an rc pointer that has wrapped a ref cell value of 7.5. And we do the next part by including a value of 4.1 in the next node, which is wrapped by the rc pointer again. And finally, I would have the new variant in the rc pointer so that the chain would end. And I can get the head, which is having an rc pointer to wrap a ref cell whose value is 1.9. And this two here would clone the head and clone the list 1 as well. So the first part of the node would have the head, which is cloned already, and the second part of the node in list 2 would have a cloned version of the list 1 here, okay? And for list 3, I will have a node that wraps an rc pointer, which wraps another ref cell pointer that stores 3.2. After that, I just link to list 1 again as the second component of the node, okay? So I want to print out list 1 and list 2, and when the head is going to be changed to 8.2, what will happen with list 2 and list 3? Let us see. Now let us play with the code first. Okay, you can see something like this. The first printline macro is here. I want to show list 1. So list 1 is just this long thing. Okay, we have a ref cell that has a value of 2.6, which is this part. And we have another node that has a ref cell of 7.5 as the first component. And the second component would have another node that has a value of 4.1 inside. And we just end the chain with a new variant at the end. And for list 2 here, what will happen? List 2 is just the combination of the head together with the previous list 1. So I will have 1.9 first, which is the head, and after the head, I will just join the entire list 1 to the end. Okay, that is the entire list 1 shown here, okay. And for the third printline macro, you can see that I want to change the head to 8.2. That means the original head was 1.9, but now I can do a mutable borrow to the head because I can do the alteration of the value inside the ref cell. So that is the meaning of interior mutability. The inside can be altered, but the outside cannot be changed. So you can see that 1.9 has turned to 8.2. So I have essentially the same list 2, except the first value of the ref cell is changed. Okay. And how about list 3? List 3 will start with a node whose ref cell value is 3.2, and I join it with list 1 as the tail of it. So 3.2 would be the beginning, and the remaining part would just be the list 1 shown here. Okay. So list 1 will go to the other part of the entire node. So the first component is here, and the second component of the node is just the repetition of the first list. Okay. So it is better to visualize the chain as follows. For list 1 here, we have an RC pointer that includes the node, and the node has 2 components. The RC pointer that has a reference cell to store 2.6 as the first component. The second component would have another RC pointer, and this RC pointer would have a node being stored, and this node will have an RC pointer that wraps a rep cell pointer here, and the second component of this node would have another RC pointer that wraps another node, and of course the inner node here would have an RC pointer that wraps a ref cell pointer, and finally we have a new here that is wrapped in an RC pointer, so that the entire chain would end. And the head is easy. It is just an RC pointer that wraps a ref cell pointer, and the ref cell pointer would have a value of 1.9 here. So I'm talking about this part. Okay, this is the head. And for list 2, it is just the head as the beginning, followed by the cloned list 1. Okay. So let us see list 2. Before changing the value, I mean the first printline macro here. So I just have the original 1.9, which is the head, and after the head, the second component would just be the list 1 here. So you can see that this part is just the repetition of the previous list 1 here. Okay, you can do the comparison yourself. Same idea here. Okay, same note here. Okay. And for list 3, I just changed the head to 3.2. You can see here, the head is 3.2, and after this head, I would go to the cloned list 1 again. So that's why you can see that the second component of the outermost node would be just list 1 here, which is the same as this one. Okay. Now let's talk about reference cycles. What is a reference cycle? We will have an example to show you. If the memory can never be cleaned up, then we will have memory leak. That means some content is still stored in the memory even though the program is already finished. But Rust can allow memory leak to happen. So it is our responsibility to avoid memory leak. Otherwise, our memory will be occupied with used data that will not be used any longer. So let us see an example of the reference cycle. So I'm going to show you some code, and basically this code is the same as the one used in the Rust book. So I just made some simple amendment from the Rust book example to illustrate the meaning of a reference cycle. So I want to make a list enum, and the list enum has 2 variants. One is called the node, and the node will store 2 values. The first one is in I32, and the second one is in the ref cell type, and in the ref cell I put the RC type inside, and the RC type would want to store a certain value of list type. So you can see that I will have a recursive data type called list. And the second variant of the list here is new. Okay. So if I want to use this list enum, I have to import it to the current scope. I have to include both the variants of the list. And of course, I have to use the ref cell and the RC pointers. Okay. So for this enum called list, I want to implement something which is called a tail method. So the meaning of the tail is like this. The tail can be node or nil, so we have to use the option enum to indicate that the value of the tail can have something or can have nothing. So the method called tail wants to recognize the node and get the second part. So we have the node here. So if we have the node variant, we can have the second part, which is represented by the ref cell pointer. So if this ref cell pointer really exists, then the tail function would just return the ref cell part. Okay. So that's why I have to use the option enum, so that it is possible that I will get nil as the value in the node. Okay. I have to do the matching to see if the second element really exists. I just return that particular item stored in the second part of the node. Otherwise, I just return none here. Okay. And let's go to the main function. So I have a certain variable called a, which links to an RC pointer, which stores a node. Okay. And the node will have two parts. The first is an I32 number, and the second one is the ref cell pointer. Okay. And in the ref cell pointer, I have a certain reference counted pointer that stores the variant nil. Okay. And then I can print the variable of a out, which would help me return the entire reference counted pointer. Okay. And I can show the initial count, which is just the strong count of the reference to a. And I can use the tail method to get the tail, which is about the second part of the node. Okay. And then I will make another reference counted pointer with a number 15 followed by a ref cell pointer that stores a reference counted pointer which stores the cloned reference to a, which is the original reference shown here. Okay. So I will show the value of b, and I will show the strong count of a after the use of a in reference b. Okay. Same for the strong count of b. I will try to see the strong count of b, and I'm also able to get the tail of b. Okay. Which is actually the second part here, including the reference to a. So I will show the result later to you. And then I will try to get the tail of a. If that tail really exists, I call it as a link. And for the link, I will try to link it to the cloned reference to b. So you can see that a joins b and b joins a. A joins b here, and b joins a comes here. It means that there will be a reference cycle, and I'm going to see the strong count of both the reference to b and the reference to a. So the idea of the reference cycle can be visualized according to the Rust book. So if I have a reference to a certain RC pointer that is responsible for a node, then a would have to link to b, which is represented by the second node here, and b is going to link back to a. So you can see that we have a cycle here. A and b can both help us to get this cycle forever. Okay, so that's the meaning of the reference cycle. So we will see the result by running the program. So the code is copied already, so let us try to play with the code by running it. Okay, you can see the thing has come out as follows. A is just the node here, okay, which is the content of the RC pointer, and A would have a strong count of 1 because this variable really joins the RC pointer here, okay. So let us see the other thing to print out. The next item of A is just the tail, which is just the ref cell part indicated inside the node, okay. So I can get this result, which is the same as that part, okay. And for B, I link it to A at the tail of the node. So when I print out B, you can see that B would have 15 first, followed by the ref cell, which is linked to A. So you can see 89 coming out, and also nil has come out for here. That means the linking to the reference to A is successful. That means B would also use the reference to A, okay? And for the strong count of A, it would become 2 because B uses A and A also uses the reference counted pointer here, okay? And for initial count of B, it is 1 because this is the first time for B to really link to a smart pointer, okay? And for B, the tail is just something like here, the second part of the node variant, okay? So you can see that this second part really exists. So you can see that I can get the sum variant coming out, okay? And then you can see that the tail of A really exists, which is the ref cell part here that links to node A, okay? So here I do the linking because the tail of A really exists. So the tail of A links to B. So you can see that for B here, I can have the next item for B as follows, which is just repeating the A here. Okay, you can see the repetition of A again. So it means that the next item of B, which means the tail of B, would join A. I mean the reference to A. Okay. So after this joining, the strong count of B would become 2 because there are 2 times that we use B. The first time to use B and the second time to use B. So the strong count of B would become 2. And also the strong count of A would still remain at 2, okay? So that is the meaning of the strong count obtained after the reference cycle is produced, okay? So the problem with the reference cycle is that after the program is complete, the strong reference count of both A and B would not become 0. That means both of the variables will still retain in the memory. Remember that for a memory to be cleaned out, the strong count of it has to be 0. But even though we end the program here, the strong count would just be 1 less than before. So for both A and B, the strong count is still 1. So it is impossible for us to really clean both A and B together with the content stored on the heap, okay? So let us see this part. If we want to run these 2 lines of code, we will overflow the stack. Let us see the meaning here. You can expect that when I want to print A links to B, and that B links to A, and that A links to B again. So we will have a reference cycle. Same for B. B links to A links to B, and B links to A, and so on. So we will see the result of the so-called reference cycle. So let me try to run the last 2 lines of code that will overflow the stack. You see we have the stack overflow here. So for A, let us see. It is even impossible for me to go back to the beginning of the ref cell that is represented by A, or the ref cell that is represented by B, because you can see the reference cycle would not end, okay? We will have a loop like this one, okay? So in order for us to really avoid the reference cycle, we can use the weak pointer instead of the RC pointer, okay? So we can make weak references to the value within the RC instance so that it can be cleaned up as long as the corresponding strong count instance of RC is 0, even though the weak count is still larger than 0. So we can use the weak count value to check the number of weak references to a variable. And a weak reference made by the weak pointer doesn't have ownership relationship, but a strong reference made by the RC pointer would have the ownership relationship. That means the RC pointer owns the value, but for the weak pointer doesn't own a value inside the weak pointer. The value in a weak reference might have been dropped, so we have to make sure that the value still exists before we want to change the value. So if we want to really change the value, we have to make sure that the value still exists. So we can use the upgrade method on the weak pointer instance to get back the option RC instance. So we can see if the method returns some RC or none as the option variant. So we can take a look at the documentation. So you can see that when we upgrade the weak pointer, we will get the RC pointer type, if it is possible to get it. For an option enum here, it means that we can have some or none. So it is sometimes impossible for me to really upgrade that to the RC pointer. So we attempt to upgrade the weak pointer to an RC pointer, delaying dropping of the inner value if successful. Return none if the inner value has been already dropped. So if that is dropped, it means that I'm not able to get back the sum value. I would just get the none value instead. So we can also use the RC downgrade method to make a weak reference by passing a reference to an RC instance as an argument. So we can do the other way around. If I want to get the weak reference, I can use the downgrade method. So the downgrade method inputs an RC pointer, which helps me to get a weak pointer. Okay. That means we can really visualize the relationship between the RC pointer and the weak pointer as follows. When we have only one of the smart pointers, we can convert it to the other counterpart. So we can do the upgrade to turn a weak pointer into an RC pointer, or we can do the downgrading to make an RC pointer to become a weak pointer. So I'm going to show you another example that is basically this one coming from the Rust book. Okay. So the Rust book uses the relationship between a parent and the children to discuss the use of weak pointers. Why is it able to discuss the use of weak pointers? Let us see. A parent node should own its children. So if a parent node is dropped, the children of that parent node should also be dropped as well. That is natural. When a parent is gone, the children corresponding to that parent is also gone. On the other hand, a child should not own its parent. If a child is dropped, the parent can still exist, and the node can use refcell weak type to really link it to its parent. So we can use a weak pointer to link a node to its parent so that when the node is dropped, the parent doesn't really own the children node. So the dropping of the node can be done without considering the ownership of the parent. Okay. Accordingly, a node links to its parent but does not own its parent. Okay. So we can explain the result of the code together with the code. So we will run this program later, and I'm going to explain the meaning of some of the codes first. I have to import the refcell pointer. I have to also include the RC pointer and the weak pointer that we will use later. And now I have a node structure. The node structure has a value together with the parent link and the children link. Since a parent can be ignored if I drop a node, the parent uses a weak pointer to do the linking. And for the children, since the node owns the children would just belong to the particular node. That's why we can use the RC pointer to help us do so. And since a node can have children or even grandchildren, it means that we can use a vector to really store all the references to the children and grandchildren as well. And let us go to the main function. We have a leaf, and we can get the leaf parent and the leaf parent borrow downgrade. It means that I want to upgrade my parent to the RC pointer from the weak pointer. We can get this part, but I want to upgrade it to the RC pointer, which is an ordinary pointer that owns the data. Okay. And now I have another branch. The branch would try to own the leaf. Okay. So that means the branch would have a children called leaf. So I can just do the referencing here to put that particular leaf into the children of the branch. Okay. And then I can make a weak reference to the branch. So I use the downgrade method to downgrade the branch so that I can do some borrow here. So the leaf would have a parent here, which is just the branch. In order for the branch to be put as the parent of the leaf, the branch has to be downgraded so that it can become a weak pointer that will be stored in the parent field of the leaf instance, okay? So when I want to print it out, I can upgrade the parent of the leaf so that I can make it an ordinary RC pointer later. And of course I can show the children of the leaf, which is nothing because for the leaf it is already the lowest possible portion of the entire tree, okay? So let us go to the leaf 2 here. I have another leaf and I can do the strong count and the weak count of the leaf, which is the second leaf here. And below I have a certain inner scope indicated by this pair of curly brackets. And in this inner scope, I have another branch, and I want to link this branch in the inner part of the code to the leaf that is defined before entering the inner scope. So we can see what will happen for this kind of connection, especially the situation when the inner scope ends. If the inner scope ends, the branch would be lost. It means that the linkage of leaf 2 to branch 2 would have some problem. So we will see the result later. So let us try to run the program first. Okay, let us see. The leaf parent is none at the beginning, which is referring to the first tree9 macro, which is given here, okay? So the leaf has no parent. And if I want to find out the second tree9 macro, it is here. So I link the branch to the leaf. That means the leaf would have a parent called branch. And after the linking, you can see that the branch has come out, which acts as the parent of the leaf, okay? And you can see that we have the parent in this format, which is just the branch content. So the value is 5. The parent is this one, which is the same as the one shown here. And the children is just this one. And of course, the children is linked to the leaf. That means I'm able to show the leaf content at the end of the children part, okay? So the second line here is discussing the use of the variable of leaf that is going to become the children of the branch, okay? So you can see all the contents of the leaf will be shown up in the children part, okay? Note, value of 3, weak pointer, and the vector shown here, okay? And for the pre-9 macro here, I want to show the leaf children here. I want to get the children of the leaf, which is just nothing, okay? Because the leaf is already the lowest level already. Let us see another pre-9 macro here, leaf 2. So leaf 2 is another leaf. So of course we have a strong count of 1 for leaf 2 because I really link the variable called leaf 2 to a certain RC pointer in the heap allocated memory. And of course I have no weak count because the linkage of leaf 2 is done by means of the reference counted pointer. Okay. And for branch 2 here, which is inside the inner scope, I can show the content of the branch 2. We have 1 strong count because I used the branch 2 once here, okay? And since I link the branch 2 to become leaf 2's parent, and in order to be successful in this linkage, I have to do the downgrading of the branch so that branch 2 can be linked to the parent of leaf 2, which requires a weak pointer. Branch 2 would have 1 weak count, okay? This weak count comes from the downgrading, okay? And let us see. Of course, I can show the leaf 2 strong count and weak count. The leaf 2 has 2 strong counts because the first strong count comes from the definition, and the second strong count comes from the linkage here, okay, which links the branch to the leaf. And the leaf too would have no weak count. That is natural because there is nothing about downgrading a leaf to join to other stuff, okay? And for leaf 2 parent, which is something outside the inner scope, in this situation, branch 2 has already been cleaned out. So leaf 2 would have virtually no parent. And then I can see the parent is none because the parent, which is branch 2, is already gone after ending the inner scope, okay? So we have no parent for leaf 2 after the end of the inner scope. And for leaf 2, we can print a strong count as 1 and 0. Why 0 for the weak count? Because we haven't done any downgrading of the RC pointer represented by the branch to the linkage. And when leaf 2 has no linkage to branch 2, the strong count would become 2 minus 1, which is 1. So the decrease by 1 here is due to the loss of branch 2, which originally linked to leaf 2, okay? So we can use the following diagram to explain the relationship between the branch and the leaf. So for a given node, we have a parent, we have a children, and we have a value inside. So when the branch joins a leaf, the branch would have a certain value together with the parent and the children. And for the leaf, the parent of the leaf would just become the children of the branch, okay? And of course, the leaf would have its own children. So the linkage comes here. The leaf has a parent that is just the children of the branch, okay? If we do this connection here, then we can see that the node and the children of this node will all be gone. So we have just the parent remaining, and the children are all gone. That is the connection between the branch and the leaf. If a leaf is gone, all its corresponding children are all gone, but the parents will still exist. Okay, let us talk about another topic called trait objects. Trait objects are really the values that store a value of any type that implements some trait. That is a bit abstract. I will use an example to tell you the meaning of the trait objects. So in order to make a trait object, we can use vector, which stores a box pointer, and the box pointer is storing some type of dynamic nature. So we can use this notation to make trait objects. T here means the trait. So we can use vector that stores a box pointer that stores a dynamic trait bound to make a trait object. So T here means a trait bound. So we have to make sure that the box contains some values that implement the same trait bound. So here dyn means dynamic. The type stored in the box pointer can be varied for each vector element. So this is a vector, and the vector can have different elements that stores different types, okay? But all the types stored in the box pointer would implement the same trait called T. So the type of the thing put in the box can be different, but we have to make sure that all the types would implement the same dynamic trait bound, okay? And when we tell the vector element to execute a given method, Rust would tell each of the elements to execute the method corresponding to its own type, and their own type will be evaluated at runtime. So we leave the runtime operations to indicate the type of the element put in the box pointer. It means that we don't need to restrict the implementation block to a single type only. So we will see a simple example to understand the meaning of the trait objects. So I have a shape trait. I need to find out the area of a shape together with showing some information of that particular shape. So I have to implement these two functions when I implement the shape trait. And then I have a circle structure that has a radius as the field. And I want to implement the shape trait for the circle. Here I define the area method and the display method, which are both contained in the shape trait, okay? So I also have a rectangle structure, and I implement the shape trait on the rectangle structure, so I include the definition of the area and the display functions for the rectangle instances, okay? And then I go to the main function. I make a circle instance and a rectangle instance, and then I want to make a trait object. I call it a shapes. So this shapes variable will try to store a vector that contains box pointers that stores values that implement the shape trait. So you can see that I have a vector here, and the vector would have some content stored in box pointers one by one. So for the first box pointer, I put a circle instance, and for the second box pointer, I've put a rectangle instance. And we already know that both the circle and rectangle structures would implement the same trait called shape. So this setting is really allowed. And for picking up each of the things in the trait objects, I can do the display function and the area function according to the particular type that is put into the box pointers. So for the circle area, I can use the area function for the circle. And if I am able to get a rectangle, the corresponding area function would be obtained from the implementation block for rectangle, okay? So the use of the trait object would force the compiler to erase the knowledge of a specific pointer type. Therefore, the trait objects are also known as the type erasure. That means we don't really remember the pointer type of the value stored in a vector. So the trait objects are a way to achieve dynamic dispatch in Rust. So we will talk about the dynamic dispatch in Rust very soon. Before I tell you the meaning of dynamic dispatch, I want to run the program first. So let me run the program. Okay, you can see that I can run the display function for each of the possible shapes. For a circle, I say the radius of the circle. For a rectangle, I say the width and the height of the rectangle, okay? And for the area, I can use the corresponding formulas for different shapes. That means I call the different area methods from corresponding structures, okay? So you can see that when I use trait objects, I just need to make sure that all the instances that are put into the box pointers would be able to implement some trait that is called shape trait, okay? As long as all the instances can implement the shape trait, I can put them into the vector, okay, in the form of a trait object, okay? So let us talk about the meaning of dynamic dispatch. In dynamic dispatch, the compiler doesn't know the method we want to run at compile time, but at runtime, Rust can use the pointer in the trait object to know the method to call. That means at compile time, Rust doesn't know which area method or display method to execute. The particular area method and the display method to use would be evaluated at runtime to find out the particular method from the particular structure, okay? So that one is called dynamic dispatch. The area and the display methods are evaluated at runtime so that at runtime, Rust can find out which method to use, okay? And we have one more term to consider that is called static dispatch. The compiler really knows the method to call at compile time. That is something we already use a lot. That is something called static dispatch. That is the ordinary approach of the compiler to get the method to use at compile time. So for example, if the previous example is changed to the one below here, we need to specify the instance in which we execute the corresponding method. So I have to say circle.area and rectangle.area so that I can pick up the area method for the circle instance coming from the circle structure. And for this area method, I go to the rectangle structure to find it out. Okay, same for the display method here. I get the display method from the rectangle that is coming from the rectangle structure. Same for the circle instance, I have to pick up the display method coming from the circle structure, okay? So when we use trait objects, we don't need to specify the particular instance here and here, also here and here. We can just use shape.area instead and shape.display instead to pick up the corresponding structure type at runtime. Now let's take a look at an example of using trait objects. We have a pack of chocolate that has 3 chocolate dice. They are in different shapes, 1 sphere, 1 cube, and 1 tetrahedron. Each type of the dice has its own dimension, chocolate syrup density, and the cost per gram. And given the dimension of the dice, the density of the dice, and the cost per gram of particular dice, we can find the weight of each die and the cost of each die. And we can also find the total cost of the whole pack of chocolate that consists of the 3 chocolate dice. So in order to do it, I have to make use of the library to store a lot of functions and traits and structures to help me demonstrate the use of them to solve this problem. So the first step is to open a library file first. Okay, I have a library file, and then I can try to make my trait structures and methods. Okay, I have to use the constant, which is the pi value, to calculate the volume involving the spheres. That's why I have to use the pi value from the library first. And then I can make my calculate trait. So for this calculate trait, I have a number of things to calculate later. The volume of a die, the name of a die, the density of the die, and the cost per gram of a die. And then I'm going to make up the structures for different shapes. Okay, for a sphere, we have to use the diameter. And of course, for a sphere, the chocolate would have some density for that particular sphere. And the cost per gram of that sphere will also be included. And for the diameter, the unit is in cm. And for the density, the unit is in gram per cm cube. And the cost per gram is in pennies, okay? Then I can make the structure for the cube, which has similar fields. Of course, for a cube, I don't have a diameter. Instead, I just need to indicate the side length, okay? And then I can make a similar structure for the tetrahedron. We also need the side density and the cost per gram for the tetrahedron. Of course, you can see that the cube and the tetrahedron would have the same fields. I admit that the program can be further refactored to make it simpler, but for illustration purpose, I just want to see the effect of calling the side density and cost per gram values from different structures. So that is the aim of making the things a bit more complex to see the power of Rust to handle different structures. Now I implement the calculate trait for all these 3 types of shape. So for the volume of a sphere, it is just 4/3 times pi times radius cube. So the radius is found by dividing the diameter by 2, okay? And then I take the power of 3 to the radius that I obtained here, okay? So for the name, I just return a string slice saying that it is a sphere. The density function is just picking the density value from the given instance, okay? So I just use the same idea as the density function to do the cost per gram function. I just pick up the field values from the instance, okay? Then I can do similar things for the cube structure. That means I implement the calculate trait on the cube structure. So for the volume of a cube, it is just the side to the power of 3. That means I just pick up the side from the instance. That's why I have to use the keyword self before the side, and then I take the power of 3 to the side. And the name is just a cube, okay? So I just return a string slice saying that it is a cube, and the density and the cost per gram would remain the same. I just pick up these two values from the instance directly. Then I make the implementation of the calculate trait on the tetrahedron. And for the tetrahedron, the volume is a bit more complicated. The side cube times 2 times the square root of 2, and the value is times the square root of 2, and the product is divided by 12, okay? And the name is just the tetrahedron, so I return the string slice, which is tetrahedron, okay? Density and cost per gram are just obtained from the instance directly. And then I can use these things to help me get the weight of a die. How can I do so? I can have an idea like the following one. So to get the weight, I just multiply the volume by the density. But different shapes would have different volumes and different density. So I have to use the function called weight that accepts a reference to the box pointer. And in the box pointer, all the elements would need to implement the calculate trait. So the sphere, the tetrahedron, and the cube would all implement the calculate trait. That's why I can put all these types of instances into the box pointer so that I can get the volume and density of each particular element that implements the calculate trait, and then I do the product to get the weight of a particular die, okay? So if we want to use methods to calculate the weight, it is of course allowed, but this demonstration wants to show that we can use a function that accepts a reference to the box pointer that contains an element whose type implements the calculate trait. So I can also use the function to help me do the task. And similarly, I can calculate the cost in this way. So the cost is easy. The cost per gram multiplied by the weight. then we are able to get the cost of a particular chocolate die. Okay. So let me go back to the main function. Of course, I have to bring all the things in the library file to the current scope in the main.rs file. And then in the main function, I can set up my 3 chocolate dies. So for the first die, it is a sphere with a diameter, density, and cost per gram as these 3 values. The second chocolate die would be a cube with the side, density, and the cost per gram as these 3 numbers. The third instance is die 3 of tetrahedron type, with the side as 4.1, density as 1.6, and the cost per gram as 0.7. And then I can make a trait object to store all these 3 instances, which come from different types. Okay, I have a chocolate pack, which is a trait object. So I use a vector that stores the box pointer, and for each element in the box, it has to implement the calculate trait. So die 1 is a sphere, die 2 is a cube, and die 3 is a tetrahedron. All these 3 shapes must implement the calculate trait. That's why I can put all these 3 items into a vector. Okay, so this vector here is created by using the vec macro. Okay, and then I can really do the calculation. Now let us see what it means for the for loop here. The for loop would just pick up a chocolate from the chocolate pack as mentioned above, and in each chocolate there is a name method to call the name of that particular chocolate, and we have also a volume method for each chocolate type, be it the tetrahedron, sphere, or cube. Okay. And the chocolate would be put in the box pointer. Okay, so you can see the inferred type is the address of the box pointer. So the chocolate variable here is the address of each box pointer. Okay, and with the box pointer address, I can get the chocolate here to use the name and volume method for each type of chocolate mentioned in the library. So for the sphere, I use this name method and this volume method, so on and so forth for different kinds of chocolate. Okay. And here I also use the weight function mentioned in the library here. Okay. So for different types of the chocolate, I can still pick its box pointer, and then I use the volume method and the density method for different kinds of chocolate. So we see that it is a dynamic pointer. As long as the thing inside the box implements the calculate trait, I can put it in the box pointer, okay, and the box pointer would be able to refer to any kind of chocolate that implements the calculate trait, okay. So if I pick up a tetrahedron, I use the tetrahedron volume and the tetrahedron density, so on and so forth. And we do the same thing for the cost function here. The cost function here would take a chocolate box pointer, and this chocolate box pointer will help us get the cost per gram method, and then I just multiply the cost per gram from each type of chocolate by the weight of the chocolate. This weight function here is just that weight function, okay? So I can get the cost by using the previous function that I defined already, okay? And after that, I want to show the total cost of the chocolate dies in the chocolate pack. So how can I do so? I can use the closure approach. So let us see how we can do it. So I let the total cost as follows. I pick up the chocolate pack, and then I use the iterator, and then I use the map iterator, so that when I put an item into the closure, I can get the cost of that particular chocolate that is put into the closure, okay? And then I've just pick up each cost of the chocolates and chocolate die, and then I pick up the sum of all the chocolate die cost obtained by each element obtained from the iterator, okay? So that is the major idea. And then I can just print out the result. So I can pick up each chocolate die in the chocolate pack, and then I can get the cost by using the closure together with the map iterator, and then I can just sum all the costs from the chocolate dies, okay? So let us try to play with the program to see the result. Okay, before I play with it, I have to really specify the data type of the total cost. For the sum method here, we have to really specify the return type explicitly. Otherwise, the sum method cannot be used. So we can take a look. So the sum method would accept a generic data type. So we have to really specify that particular generic data type when we use the sum function, okay? So let us try to play with the program now. Also, before I do so, I have to change the content to print out a little bit. The first one is the volume, the second one is the weight. And the third one is the cost. So let me try to play with the program now. Okay, you can see that I can get the volume, the weight, and the cost of the sphere die, okay? Same for the cube die and the tetrahedron die. And of course, I can get the total cost of all the dies by adding the cost here, the cost here, and the cost here. Okay, so we can see that we can use the function instead of using the method to handle the weight and the cost of the particular chocolate die, okay? So we can also get the total cost by using the closure method, okay, to get the sum. And we have to really specify the return data type, because for the sum method here, we have to really specify the data type to handle, okay? Now, let's talk about concurrency in Rust. We can achieve concurrency by using threads. So how can we use threads? We can indeed run many threads at the same time, but it can result in many problems. So in order to do the concurrency properly, we have to realize some problems that can happen. As the threads can run at the same time, there can be something to consider. there can be race condition, meaning that the threads are accessing the data or the resources in an inconsistent order. Or there is a possible situation of deadlock. It means that two threads are waiting for each other, and so both threads are stopping. So nobody is able to access a piece of data because both of the threads are waiting. So how can we handle the concurrency in Rust? First, we have to spawn some thread. We can use thread spawn function to make a new thread and pass the thread to a closure. If the main thread is finished, then the spawned threads would also stop working. The main thread here means the main function actually. And if the main function is stopped, the spawned threads would also stop. To wait for all the spawned threads to finish, we can wait for some more time after the end of the main thread. So when the main function is complete, we can wait for some more time so that all the spawned threads can also stop. So the order of executing the threads is determined by the CPU scheduling mechanism. Each program execution can result in different order, so we don't know the order of the threads to execute. And we can use the thread sleep function to force a thread to stop the execution for some time or duration. So we have the following example code. We have to import the thread and the duration functions from the standard library. And this is the main function, and the main function is called the main thread. And in the main thread, we have a spawned thread. So we have only one spawned thread here because I do the thread spawn action once only, okay? And this for loop belongs to the so-called main thread. So the main thread has this operation to handle, and this spawned thread is also going to execute. And when we finish the main thread, which is this for loop, we can make the main thread sleep for some duration, which is 1 second in this case, to wait for the spawned thread to finish, so that the spawned thread will not stop when the main thread is finished. So let us see the execution of this program. Now let us run the program as usual. Now, I don't make the main thread sleep for now. What would happen? Let us see. So you can see that I can use the main thread to print 1 and the spawned thread to print 1 as well. So you can see that the main thread can print 1 to 4 only. So you can see that the main thread can stop at the 4th execution of the for loop, okay? And you can see that the spawned thread can execute for 19 times because the for loop for the spawned thread will start from 1 and end before 20. So I would have 19 operations for the spawned thread to execute, okay? And you can see that for the spawned thread, each execution of the for loop would wait for 1 millisecond. So after 1 millisecond, the spawned thread would continue to execute the rest of the for loop, okay? So you can see that when the main thread has finished, the main thread doesn't wait for the spawned thread to go to 19. So you can see that when the main thread is finished at 4, the spawned thread can no longer go to the 19th printing of the statement shown here, okay? Because I didn't allow the main thread to sleep for a longer time, say 1 second, to allow for all other printing from the spawned thread. So let us see the result if I allow the main thread to sleep for 1 second. It should be possible for me to print out 1 to 19 from the spawned thread. So you can see that now I can allow the spawned thread here to print out 1 up to 19. So even though the main thread is already finished, the spawned thread can still continue. So the main thread is finished at the fourth printing of the statement from the main thread. But after the finishing of the main thread, the spawned thread can still continue to do the rest until the spawned thread has printed 19 out. Okay. So we can use the join handle to wait for all the threads to finish. In order to make sure that all the spawned threads will be executed, there is another method other than the sleep method here. We can save the return value of the thread spawn function, and this value has a type of join handle. Then we can call the join method on this value in join handle type, and the program will wait for other threads to finish their execution. So let us see the code here. I have a spawned thread, and the spawned thread will try to print out 1 to 19, and I save this spawned thread into the handle. And after that, I can tell the handle to use the join method as well as the unwrap method. So the join method here is going to wait for all the spawned threads to finish before running the main thread. So I would execute the spawned thread first, and after that I can do the main thread. And we have to use the unwrap method after the join method. The reason is like this. We need to use the unwrap method because the return type of the join method is the result enum. And we have to use unwrap to get OK or variant. So that's why we may need to unwrap the joined threads, okay? So let us see the documentation. So we can see that the join method here would have a type of result. So that's why it is possible for the result value to be OK or an variant, okay? That's why we need to do the unwrapping. So let us play with this program. Now let us see the result of playing this program. Okay, you can see that all the spawned threads, which is just one here, would be handled first. After handling the spawned thread, I need to use the join method together with the unwrap method to wait for all the spawned threads to execute. Since I have only one thread here, the joining action would just wait for that particular thread to finish. And since I'm able to really execute something out from the spawned thread, the unwrap function would just give me an OK variant. Okay, and then after handling the spawned thread, I'm able to go back to the main thread. So you can see that the main thread will be executed after the spawned thread is executed. Okay. And we can have some way to move the threads into the closure explicitly. If a spawned thread wants to use the data in the main thread, we have to move the data from the main thread to the spawned thread. That is the meaning of using the move keyword. If we don't use the move keyword in this example, the spawned thread may need some time to run and isn't sure whether the data will be valid at the time of using it. That's why it is necessary to move the data into the spawned thread for memory safety. Let us see this simple example. Now I use the move keyword here so that the data will be moved to the spawned thread, okay? And this spawned thread will undergo the join method together with the unwrap method to wait for this thread to complete, okay? And this closure has nothing as the input parameter, so I move the string into the thread and the thread will be able to use it, okay, to do the printing action shown here. So let us see this example by playing with it. So let me play with the program. okay, you can see that the string can be printed out because this particular string is already moved into the thread, okay. What will happen if I don't use the move keyword? Let us see. You see that we have an error, because if we want the thread to really use the heap allocated memory, we really need to move it into the thread. You see that I'm not able to compile. Yes, we have got an error because I didn't really move the data, which is in the form of a string, into the spawned thread. That's why the move keyword is important in this case. Otherwise, the handle isn't able to use the data, okay? Message passing. There is a method of achieving concurrency, and the threads can communicate themselves by sharing data, and Rust can do it by using channels, so that the data can be passed between two threads. And a channel has a transmitter and a receiver. We can tell the program to control the transmitter to send data down to the channel, and we can control the receiver to get the data, okay? And the channel is closed if either the transmitter or the receiver has been dropped. So we have to make sure that both the transmitter and the receiver are present. And the function here, MPSC, that will be used in the following program, means multiple producer, single consumer. Producer here means we can have more than one transmitter. Single consumer means that we have only one receiver. The variable tx and rx here would mean the transmitter and the receiver respectively. And we tell the transmitter to send the data and the receiver to receive the data. We really need to move the transmitter into the closure so that the spawned thread can use the transmitter. So let us see the following code. We use the MPSC package, which is inside the sync package from the standard library. And of course, we also need to use the thread package. So we can use MPSC and then channel to produce the transmitter and the receiver respectively. So I save the two things into a tuple, and then I can make a spawned thread, and I use the move keyword to move the transmitter, which is here, into the thread. Okay. So I have a string here, and I tell the transmitter to send the string, and then I need to unwrap it. The send action would have a result enum type to come out. That's why I need to use the unwrap method, okay? And we cannot print it, which is the print line statement shown here, because it is already moved into the send method, okay? So this send method has already taken ownership of the string. That's why I'm not able to print it out after the send method, okay? And after the spawned thread has transmitted the string here, I can use the receiver to receive it. So I use the receiver here, Rx, and I use the receive method, and I also use the unwrap method to get the result enum coming from the receive method, and I save it as the received variable. And of course I can print it out because the receiver has already helped me to get the string back. And we used recv here, which is this method, to receive the data. And this method will block the execution of the main thread and wait for the data to finish the transmission. That means the main thread will stop working until the transmission has finished. On the other hand, if we don't want to block the main thread at the time of receiving the string, we can use try receive instead of receive only, okay? And the result of the spawned thread will come out immediately, okay? So let us try to play with this part first. Okay, let me play with it. Now you can see that I can get hello world, which is received by the Rx receiver, okay? So that is the way of using the transmitter and the receiver to pass some data. Okay. The receiver would understand the corresponding transmitter to use because I already make a certain assignment here. So the channel would use this TX as the transmitter and this RX as the receiver. So you can see that TX and RX would refer to the same channel. That's why the RX variable here would correspond to this TX transmitter used previously, okay, because they come from the same channel, okay. And we can also send multiple data and wait for each of them before sending another one. So what does it mean by that? Let us see. Now we have the multiple producers single consumer function coming from the sync package. And of course, we have to use the thread package as well as the time package. That helps us to get the duration type, okay. So I make up a channel first, and then I move the transmitter into the spawned thread, and I want to send some numbers into the transmitter. And after each sending, I wait for some time, say 1 second here, so that I would transmit 0, 1, 2, 3, and 4 to the transmitter. And the receiver here would be able to receive 0 to 4. And I'm able to print the received values in this for loop. So let us see the result of running this part. Now let us play with the program. So this empty space is what I created by pressing the enter. So by ignoring this blank line, I'm able to print out 0, 1, 2, 3, and 4, one by one. So each of the numbers was received by the receiver. Okay, this transmitter sent these numbers one by one, and I need to wait for 1 second before each of the numbers are presented from the receiver. Okay, so the receiver is able to get the numbers immediately after it has been received. So you can see that they come out one by one after each of them is separated by 1 second duration. Okay. So you can see that the transmitter can send multiple values into the same receiver. We can also clone the transmitter and send data from both transmitters. So in this case, we can use the clone method to produce the cloned version of the original transmitter. Okay. And I can tell the original transmitter and the cloned one to send different numbers. And let us see the result from the receiver. So you can see that the spawned thread for the first part would loop over 0 to 4, and each of them will be separated by 2 seconds. And for the second spawned thread here, I would tell this spawned thread to show 95 up to 99. Each of these numbers is separated by 1 second. So let us see the result by running this program. Okay, let me try to play with it. Now you can see that all the numbers are printed out. And you can see that we need to wait for 2 seconds to make this first spawned thread to print out 0, 1, 2, 3, and 4. And for the second thread here, which is a spawned one here, I can just wait for 1 second to show 95 up to 99. Okay. So that I have got 2 spawned threads to do the printing one by one. So this cloned one here is able to use the same receiver. Okay. Because this transmitter is a copy of the original transmitter. they would just refer to the same channel. So these two transmitters would use the same channel, and that's why the same receiver can be used by these two transmitters, okay? Now, let us talk about shared state concurrency. We have another way to make concurrency happen by means of the shared state concurrency. Multiple threads can access the same piece of data in the memory at the same time, without any kind of data race situation. The idea is to use some mechanism that we will discuss later. First, we need a mechanism that allows only one thread to get the data at one time. And this mechanism is called mutex. Mutex here means mutual exclusion. There's only one thread that can access a piece of data at one time. To get the data, the thread needs to get a mutex's lock. And this lock would remember the thread that has exclusive access to the data. And the mutex mechanism is just guarding the data so that other threads cannot access it while a particular thread is using it. And the thread needs to get the lock first. After the use is finished, the thread has to unlock the data so that other threads can use the data back. So in order to use the mutex feature, we have to import the sync package first. And you see, I have a mutex new here, so that I want to use a mutex mechanism to guard this string. Okay, so this string is called my string here, and this my string is guarded by the mutex mechanism. So I have a new inner scope here, and this inner scope would try to lock the my string variable here, and then I need to unwrap the result because the lock would result in the result enum. And I need to make it mutable because the locking action would change the state of my particular string here, okay? And then I can dereference my string value to really change the string content from hello to hello world. And this inner part will be executed before I print the statement of my string shown here, mystr. Okay, so I'm going to show my string content. Let us see the result after running the program. And let me talk about this code a little bit. When the inner scope ends, the lock will be returned automatically, and the printline macro can show the content of the variable. So I can do the printing action here because after the end of the inner scope, my string here will be unlocked. If I want to remove the curly braces in the middle, then the code is in the main thread. I mean, the inner scope would become part of the main thread, and we will see that the variable is locked, and we cannot access it in the main thread. Let us see the result of removing the curly braces when I run it. Now let me try to play the version that has the inner scope first. Okay, you can see that the mutex lock here is present to help me guard the data. So when I print the data inside this locking mechanism, I'm still able to get the hello world string, which is already mutated by the inner scope. Okay, so from this line, I'm able to change the content by accessing the value of this reference. Okay, this part called poisoned is out of the scope of this video, so I don't need to handle it for now. What would happen if I remove the inner scope? Let us see. And when I save it and run it, you can see that my str here is locked. That means I'm not able to get the content inside the locked value. Okay, so the printline macro here is in the main thread, and this main thread would still keep the my str variable locked, so that the mystr variable cannot be printed out, except I keep the inner scope again. Let's talk about multiple ownership with multiple threads. If we want to allow many threads to access the data, we can wrap the mutex data with the ARC smart pointer, and we will discuss the meaning of ARC pointer very soon. And then we can clone the ARC pointer and let many threads access the mutex data inside the ARC pointer. The reference count of the ARC pointer will increase by 1 after each cloning. And ARC here means atomically referenced counted. An atomic type is a primitive type that can be shared across the threads safely. That's why we can use this ARC pointer to communicate with the threads safely. The performance of using atomic type would be lower than using ordinary primitives, so we use this type when we really want to do the concurrent operations. So let us see the documentation for the atomic type. So we can see that atomic types would provide primitive shared memory communication between threads. And that's why we can use this type to communicate between the threads. And atomic variables are safe to share between threads. It is one of the reasons we can do the communication safely. And we need the wrapping to use the ARC pointer because a thread will own the mutex data and other threads cannot access the same piece of mutex data when a thread owns the mutex data. So we need to do some locking so that other threads cannot access the same data once the data is wrapped with the mutex pointer. Okay? And we can get a mutable reference to the value inside a mutex pointer. So the mutex pointer can provide interior mutability. That means we can change the things inside the mutex pointer. And outside the mutex pointer, we wrap it with ARC pointer. So let us see this example. I need to import the ARC pointer and the mutex pointer. And I also need to import the thread package. And then I make up a counter structure, and the counter structure has a field called count, and this count would be of mutex pointer type, and the pointer would refer to a value of U32. And then I implement some functions on the counter structure. I make a new function so that I can create a counter instance with the count being set to 0 at the beginning when I just create a new counter instance. And also I can make a method called increment so that I lock the field from the counter instance, and then I can increase the value of the counter by 1. Here we use the asterisk because the result coming from the lock method, after the unwrapping, it would become a reference to the field value in the counter's instance. That's why I need to do the dereferencing to get the value of that field. Okay. And I can also do the getCount method so that I lock the field value from a counter instance, and then when I unlock it, I can get the count obtained after the increments. Okay. And of course I need to use an asterisk to dereference the count variable. Okay. And in the main method, we do something like these lines. First, I make a counter variable, which is just a wrapping of a counter instance with the ARC pointer. So I use ARC new method to embrace the instance created by the new method of the counter structure. Okay. So I have a counter, and this counter will be manipulated soon. And after setting up the counter instance, I need to make a vector called handles, and I'm going to store the handles of each thread into this vector. And here is the major idea of the program. You see that I do the for loop for 5 times. Since the variable of the looping isn't important in this example, I just use an underscore to ignore the variable. Here you can see that I do the cloning of the ARC pointer, and this cloning is going to clone the counter reference. This counter refers to that counter which is already set up by using the ARC pointer, okay? And for each cloning, the reference count of the counter would be increased by 1. That is the meaning of the ARC pointer. ARC here means reference counting, so when there is one more reference to the same memory location, the reference count would increase by 1. So this statement is something like this. We want to create a new reference to the shared counter instance. So this is a shared counter instance, which is shared for 5 times due to the for loop. So we will have to repeat these lines for 5 times. And for one iteration, it refers to the production of one thread. So the next line is going to make one thread. So for all the 5 iterations, I'm going to make 5 threads, okay? And I have a handle here. The handle is coming from the spawned thread. So I want to move the counter ref variable into the closure, and after the movement, I want to increase the count value in the instance referred by this counter reference by 1. That's why I do the increment method for the reference to the counter instance, okay? And of course, I do the increment for 100 times, and that's why the variable in this inner for loop is not relevant to our operation. That's why I can just ignore this symbol. And when the counter instance is involved, the mutex uses the lock to gain control. What does it mean by this sentence? It means something like this. When we go back to the methods from the counter implementation, you can see that when I do the increment, I need to lock the variable obtained by the counter reference. Okay, so when I do the locking, other threads cannot access the same reference indicated by the self here. The self here would refer to the counter reference, okay? So this counter reference is actually referring to the one and only one counter instance that we created before we entered the for loop, okay? So when I use the lock method, other threads cannot access the same piece of data, okay? That's why we can achieve memory safety. And even if we have multiple references and multiple threads, only one single thread can do the function called increment or get count, okay? And then for each of the handles done by the outer for loop, I'm going to push them into the handles vector, and then I'm going to process this handles vector here. I want to pick up each of the elements in the handles vector, and then I join them. It means that I want all the threads to wait for each other so that all the threads will be finished. And we notice something here. The join method would return a result type, so that we have to use unwrap method to get the generic type T or the error type. Okay, so if the join is successful, we can get the generic type. So when the counter is involved here, the mutex would lock the thread to gain control. This is for the getCount method. So the getCount method would also require the locking of the data into a thread to do the operation, okay? So let us try to play with the program. Okay, you can see that I have already copied the code into the editor. And then you can see that the count variable in the increment method would have a type called mutex guard. The number being guarded is in U32 data type, okay. Same for the getCount method here, okay. And the handles variable would be a vector, of course, and the thing to put into the vector is of the type join handle. Okay, a join handle would detach the associated thread when it is dropped, which means that there's no longer any handle to the thread and no way to join it. From the illustration here, we can join the threads by using the join method when we have all the join handles. Okay, so let us try to play with the program. Okay, you can see that the final count is 500. The reason is like this. I make 5 threads, and for each thread I make the increment for 100 times, shown here. Okay, so for each thread we access the same counter reference called counter. Okay, so when I make a thread to make the increment for 100 times, I make another thread by using the outer for loop to do the increment again and again. So I do the increment for 500 times altogether. Since I concentrate on the same counter reference, these 5 threads would act on the same counter variable, shown here. Okay, which is inside the ARC pointer. Okay, so the reference count of this variable will be 5. Okay, so after doing all the things, I will get 500 as the count, because I always just refer to only one reference, even though I have 5 threads to handle. Okay, so this section has discussed a lot of things about concurrency, and I hope you can understand the mechanism of making concurrency possible in Rust language. Now let's talk about attributes. An attribute is a metadata that is put on some module or item. An attribute can allow for conditional compilation of the program. That means if some condition is met, the module can compile. Otherwise, I don't allow the program to compile. And an attribute can also disable warnings. An attribute can also mark a function as a unit test, so we can see the use of attributes in Rust. We can put attributes on top of some module or item so that we can have additional features. There are actually 2 formats of attributes. The first one is called an outer attribute, which is a hash followed by the outer attribute name. Okay. What is the use of an outer attribute? An outer attribute is effective to an item immediately following this attribute. An item here can be the function, a module, a constant, a struct, or an enum. So we have a simple example. We have the derive debug attribute. This one is an example of the outer attribute. The derive attribute has a value called debug. Okay. So actually it means that we want to derive the debug attribute so that I can print out the content of a structure instance. That is something we already know, because we have already discussed it in our previous discussion. So this one is an example of the outer attribute. Okay, so let us try to play with this part. Okay, apart from the warnings that I didn't handle properly, you can see that I can use the debug trait to print out the content of my person instance, okay, name and age, okay. So I'm able to use the derive debug attribute to really help me show the content of instance from a certain struct, okay. The other type of attribute is called an inner attribute. So we have a hash followed by an exclamation mark shown here, okay? And we include the inner attribute name after the exclamation mark, okay? An inner attribute is applied to the whole scope. That means to a module or even a crate. For example, the whole crate can allow unused variables without warning. So the allow attribute has a value called unused variables. So this is an example of inner attribute because we have an exclamation mark shown here, and the value of this attribute is called unused variables. So if some variables is not yet used, I can still allow the compiler to disable the warnings. Okay, so let us see this example. So usually when I just make a variable without really using it, you will see that the Rust analyzer would complain about this situation, like this one. When I save it, you can see that I have a certain unused variable called A. But if I include the allow unused variables attribute before I really execute the main function, you can see that that warning is not present right now because of this attribute, which is an inner attribute, okay? So we don't even need to add an underscore before the identifier to make the warning disappear. We can just use the attribute shown here, which is an inner one, to help me do so. So let me try to play with the program. You can see that I can run the program, and of course I have nothing to appear because I haven't printed out any statement to the standard output, okay? But you can see that the warning is gone because of this attribute, okay? So generally, an attribute has the following format: attribute equals value, or attribute key equals value, or attribute value, okay? You can have these three major formats of an attribute. For multiple values of an attribute, we can do something like this: attribute, value, and value 2. So we can include more than one value for a certain attribute if we really want to do it. And there is an attribute to allow that code, that is the code that fails to execute. We can use allow that code across the whole file to do so. So we can have an example. We see that we have some unused function and some unused structures. When the main function is just using the printline macro, the function here and the structure here are both unused. So we have some that code here. If we want to disable the warnings arising from the unused functions or structures, we can use allow that code. So the program can compile and run successfully even though there is that code. So let us see the result of running the code. So let me try to run the code. You can see that I can print out the statement called hello Rust, okay? But how about the situation if I don't include this attribute? What will happen with the unused function and the unused structure? Of course, you will see the compiler warnings. The warning is also shown when I really want to run the program. So you can see that the main function can still be executed, but the warnings are still present. So we can use the allow that code to make these warnings disappear in the standard output, okay? We can also achieve conditional compilation with the CFG attribute. We can use it as an outer attribute so that we don't need to include the exclamation mark. So we can add this attribute CFG with a certain value to the attribute before the start of an item that does conditional compilation. If the value is satisfied, then the item will compile. And this attribute can be used together with the CFG exclamation mark macro, which can return a Boolean expression. So how can we understand these lines of illustration? we can follow the example in the Rust by example web page. This is the code coming from the Rust by example web page. When we play with this example in Visual Studio Code, the failed condition can be faded out, so we are able to be clear about which functions will compile. So this function is about checking the operating system that the program is working on. So this function will be compiled if the target OS is Linux, which is my case right now. And for this part, if the operating system is not Linux, then this part will be executed. So we have a CFG attribute here. The target OS equals Linux. So I want to check whether the OS is Linux or not. If our target OS isn't really equal to Linux, then we can include the not keyword before the key and the value of the attribute, okay? So if the target OS is not Linux, then I'm going to run this part. So you can see the main program. I'm going to use either one of the "Are you on Linux" functions. So which one to use depends on my current operating system. And after that, I can do something following my function here. And I can say something like, "Are you sure?" And if the CFG macro is true here, then I'm able to print out this line of statement saying that I'm really using Linux. If this configuration macro fails, or CFG macro fails, I can print out another statement saying that I'm not using Linux. So let us try to play with the program. Now you can see that the second "Are you on Linux" function is faded out because I'm really using Linux. And the Visual Studio Code environment can really help me understand the function that I'm going to run, okay? So let me try to play with the program. You are running Linux. This statement is coming from the "Are you on Linux" function that is shown on top of the faded one, okay? So, are you really sure? This statement is coming from the main function, and the CFG macro is really able to help me check that my OS is really Linux. That's why I can print out this statement saying that I'm really using Linux. If I'm using other operating systems, I may run the second print line macro, okay? So this part has discussed the use of attributes. There are two types, the outer one and the inner one, and we can use attributes to help us run the code with additional conditions to consider. Now let's talk about the advanced features of Rust. The advanced features of Rust won't be used pretty often, but they are pretty helpful in some specific conditions. So we will talk about these advanced features one by one. The first one to talk about is the unsafe Rust. So Rust compiler is quite conservative. If the code is just possible but not must cause memory safety problems, it cannot compile. So we can use unsafe code to override the strict memory safety issue in Rust. Of course, we must make sure that the program must work at the runtime, okay? So at compile time, we can get rid of some memory safety issue by using the unsafe code, as long as we can make sure that the program can work at runtime. Also, many low-level control of computers would involve unsafe memory control. If Rust is pretty strict enough, we cannot do too much about system programming, okay? And we can use the unsafe keyword on top of the block of our unsafe code, and we will have some examples to demonstrate the use of the unsafe keyword later. So there are actually 5 unsafe superpowers in Rust that won't be checked by the compiler. That means we have 5 unsafe conditions to use the unsafe keyword. When we want to dereference a pointer, we can use the unsafe keyword. When we want to call an unsafe function or method, we can use the unsafe keyword. If we want to access a mutable static variable, we can also use the unsafe keyword. When we want to implement an unsafe trait, we can use the unsafe keyword. If we want to access the fields of the union, which is similar to a structure, we can also use the unsafe keyword. But this property will not be discussed in detail in this video. The borrow checker is still in effect in the unsafe mode. That means we need to abide by the borrow checking rules, okay? And we should keep the unsafe block small so that we can pick up the memory safety issue more easily. That means the unsafe block shouldn't contain too many lines, okay? So that the memory safety issue confined in the unsafe block is easier to handle. And we should also enclose the unsafe block within a safe function or method. In doing so, the memory problem will not be spread to other parts of the program. That means it is like a sandbox. When we have an unsafe block, we can protect other parts of the code from being affected by the unsafe actions. Okay. So let us talk about one of the superpowers in unsafe mode, which is the dereferencing of a raw pointer. So unsafe Rust has immutable raw pointers const t and mutable raw pointers mut t. So before const t we have an asterisk, before mut t we also have an asterisk, okay? And the asterisks are really part of the name. And immutable here would mean that when the pointer is dereferenced, it cannot be assigned again. So that is the meaning of immutable, okay? After dereferencing, it cannot be assigned again. So it can just be used for our current variable. Other than using it for that variable, it cannot be used any longer. And raw pointers are more lenient in many properties. They can ignore the borrowing rule. What does it mean by this sentence? It means that the immutable and mutable raw pointers can come together. And more than one mutable raw pointer can point to the same memory location. That is the meaning of the use of the raw pointers, which can ignore the borrowing rule, okay? Raw pointers can point to the invalid memory. They can become null, and they are not cleaned up automatically. That means we have to clean them up. And we can cast immutable and mutable references into the corresponding raw pointers. That means we can do the casting to make some pointers into the raw pointers. And we use the as keyword to do the typecasting. So let us see the following example. I have a mutable value, and I want to make an immutable raw pointer to the value here, okay? So I pick the address, and I cast the address of the pointer to the value variable to an immutable raw pointer. So I use as keyword followed by asterisk const, and then I put the data type that is for the variable called value, okay? So I have an immutable raw pointer for the value here. And at the same time, I can make a mutable raw pointer by using asterisk mut in the casting process, okay? So v1 is the immutable raw pointer, and v2 is the mutable raw pointer. And then we can dereference the raw pointers in unsafe mode. How can we do so? We can just use an asterisk to do the dereferencing, okay? And we can only do the dereferencing in the unsafe mode, but not in ordinary mode, like in an ordinary main function, okay? So let us see the result of running the dereferencing. Okay, when I run the program, you can see that the dereferencing can be done so that v1 can be dereferenced to get the value of 9.4 back. v2 is also able to get 9.4 back, okay? So that is the dereferencing of the raw pointers, be it immutable or mutable, in the unsafe mode, okay? So how about dereferencing the raw pointers in the safe mode? Let us see. And you can see that I have an error coming out. The reference of raw pointer is unsafe and requires an unsafe function or block to do it. That means I'm not able to really compile the program because the raw pointers cannot be dereferenced in the safe mode, okay? So let us go back to the notes. And another issue about the superpower of unsafe Rust is we can call the unsafe functions. So we can also call the unsafe functions as methods in unsafe code. And we can add the unsafe keyword before declaring such a function. And when we call them, we enclose the unsafe functions and the methods with the unsafe block. So in using the unsafe functions, we bear the responsibility of following the memory safety rules by ourselves. So we have a pretty simple and conceptual example. I have an unsafe function, so I want to use the unsafe keyword before fn to declare such an unsafe function. And I want to really run this unsafe function in the unsafe code. So this function has nothing to do. So when I run this program in the unsafe mode, I'm able to get nothing. But we cannot really call the unsafe function in the safe mode. So you can see that I'm not able to really run this part. So let me play with this little program. You see there's nothing coming out because the unsafe function has done nothing. Okay, but is it possible to call the unsafe functions in the safe code? Let's see. You see I will have an error because I'm not able to call the unsafe function in the safe code. I have to use the unsafe block to do it. Okay. And the other issue about the unsafe Rust is that we can wrap unsafe code with the safe code. What does it mean by this one? We are going to see an example that uses the copy non-overlapping method, which is a method provided in Rust, which is an unsafe method as well. So we don't always need to make the entire function an unsafe one. We can just make safe functions that include unsafe blocks inside the function. So in a safe function, we can have some unsafe block inside this safe function. So we have such a method provided in Rust. The copy non-overlapping method is an unsafe method. The function wants to copy the value referenced by the source pointer to the memory location referenced by the destination pointer. And the length of the values to copy is also specified too. That means we need to specify the destination pointer together with the length of the values to copy. And we can see that the source pointer and the destination pointer. So we will see why it is unsafe later. We can use the sPointer method here to make an immutable raw pointer, and we also use the smutPointer method to make a mutable raw pointer. So we can take a look at these two methods first. So we have a certain pointer and I pass that pointer, and then I will make a mutable raw pointer. So the sPointer function would return a raw pointer to the slices buffer. Okay. And how about the other function? smutPointer function is similar to the sPointer function. It is just that the return value is a mutable raw pointer. And of course, the mutable raw pointer is an unsafe mutable pointer. Okay. And the copy non-overlapping method would do bitwise copy of the generic type, whether or not the generic type implements the copy trait. So even if the generic type doesn't implement the copy trait, the copy non-overlapping method would still do the copying. Okay. So the problem comes here. If the generic type doesn't implement the copy trait, the reference to the source raw pointer will be copied to the destination raw pointer. Both the values at the beginning of the source pointer and the destination pointer would try to access the same memory address. Therefore, memory safety is violated in Rust. We cannot allow the source raw pointer and the destination raw pointer to get the same memory address in the safe code. That's why we have to handle this issue in the unsafe code. So let us take a look at this function called copy non-overlapping. This function has to be executed in the unsafe code, and it has a source pointer, which is an immutable raw pointer, and it has also a destination pointer, which is a mutable raw pointer, and we have to specify the count as well. Okay, so the copy non-overlapping method is actually equivalent to C language's memcopy, but the argument is just reversed in order, okay? So we do the copying in the unsafe code when we want to use it in Rust, okay? So it does the copying from the source pointer to the destination pointer, and these two memory locations must not overlap, okay? That means non-overlapping comes from the meaning that the two pointers, source and destination, don't overlap. And now let us see the following code. I used the ptr module so that I can handle the pointer issue by means of this module. And then I make a function called copy values. I want to put a source pointer and I want to put a destination pointer. Okay, so the source pointer would refer to an array that stores U32 values, and the destination pointer would help us change the content of a certain memory location. That's why it has to be in the form of a mutable array, and the array is in U32 data type, okay? And we have the source pointer here. I make a certain immutable raw pointer for the source pointer, and I also make a destination pointer from the destination pointer passed to the copy values function, and it has to be cast to the mutable raw pointer, okay? And I get the length, so we can see that we have to really satisfy these three things when I want to use the copy non-overlapping function later on, okay? And then I can use the copy non-overlapping function coming from the ptr module. So I pass the source pointer in the form of an immutable raw pointer. I pass the destination pointer in the form of a mutable raw pointer. And I pass the length of the array to copy into the copy non-overlapping function, okay? And in the main function, it is something like this. Source is here. Destination is here. It means that I make 5 zeros in an array. So you can expect that I want to make these zeros to become 1, 2, 3, 4, or 5. Okay, so I call the copy values function, which I wrote here. Okay, and this copy values function would use the source reference and the destination reference. Okay, so this one is the immutable reference, but the destination here is a mutable reference. So I use the copy values function to really change the content in the destination array. Okay, so after that I can just print out the values in the destination pointer, which would be 1, 2, 3, 4, 5, one by one. So if I want to use the copy non-overlapping function, which is a function provided by Rust, we have to use the unsafe mode. Okay, so this is the unsafe code that has to be executed inside my user-defined function. Okay, so it means that an unsafe code can be executed or included in a certain user-defined function. Okay, so let me try to play with this program. Okay, you can see that the destination becomes 1, 2, 3, 4, 5 because I can really use the copy non-overlapping function inside my copy values function. In order to use this unsafe function, I have to use the unsafe code to really include the unsafe method, okay? And in Rust, we can also call some external code by using the unsafe keyword. So the extern keyword, extern here, allows us to use the other languages by using the foreign function interface, FFI. And this interface would allow us to use functions written in other languages. So in the following example, I want to use C language. So let us see what it can be achieved in Rust. So we wrap the foreign language code in the extern block. And the C here would mean the application binary interface, which controls how to call the external code at assembly level. So when I want to call the C code, I can use capital letter C to mean the ABI or the application binary interface for C language. Okay. So if I want to use the unsafe code from other languages, I have to include unsafe extern C. Okay. So C is embraced by a pair of double quotes. Okay. So we can expect that this is a function called pow, which is doing the power of a base, okay? So this is a function provided by C, and I can just use this C language function directly in Rust language. The idea is like this. I can call this unsafe function coming from C language by embracing the function and including the keyword unsafe in the unsafe block, okay? So in the unsafe block, I can return a value coming from C language, and then I can just show the answer to the power coming from the C language. So let me play with this part. So I want to do 1.2 to the power of 2.3. So you will get 1.52 something as the answer. So you can see that I can really use the C function to handle the power issue in Rust. So that is the meaning of using the application binary interface called capital letter C here to use the C language, okay? Another issue about the superpower in Rust is the mutable static variable. So static variables in Rust are actually the global variables. We already learned this in other sections of the video. And if we use static variables to store references, the lifetime of it is static, which means that Rust can find out the lifetime itself, okay? And static variables are in screaming snake case, so we can use this kind of naming convention for static variables. And the differences between a constant and a static variable is like this. Static variables can have their fixed memory locations. They can be accessed at the same place all the time. But constants can be copied when they are required in the code. And static variables can be mutated in an unsafe way, but constants cannot be mutated once it is produced, okay? So we can see that static variables have some advantages in terms of mutating it, okay? So let us see the way to mutate static variables in unsafe code. So now I have a static variable, okay? When we want to make a static variable, we have to annotate the type. That means I have to say I32 here. I want to store a certain integer, okay? So I store the integer as 1, which is a static variable, and it is a mutable one, okay? And I make an unsafe code here so that I can do the assignment of the static variable to another value. And when I want to print this static variable, I have to use the unsafe mode as well, okay? And you can see that it is unable for us to mutate the static variable in the safe code. So this assignment is not allowed when it is done outside the unsafe code, even though it is done in the main function. So let me try to play with the code. Okay, you can see that I'm able to change the value of counter into number 8, okay? So even though creating a shared reference to mutable static variable is not encouraged, we can still do so. So you can see that we can change the static variable content, but it is not encouraged to do so, okay? So is it possible to change the static variable in the safe code? Let us see. So you can see that I'm not able to really execute the code because you can see that the use of mutable static variable is unsafe, and it requires an unsafe function to do it. That means I have to use the safe block or the safe function to do the change of my static variable. So you can see that the static variable needs the unsafe block to do so, okay? So different threads can access the static variable, which can result in data race. That means 2 or more threads are trying to access the same static variable. That's why mutating a static variable is regarded as unsafe. So it is better to use concurrency treatment so that the data can be accessed by the different threads safely. So this is the reason why we discourage the use of static variables, okay? We'd rather use concurrency treatment instead. And in unsafe mode, we can create unsafe traits. What does it mean by this one? Let us see. If the implementation of a trait requires unsafe code, then the trait needs the unsafe keyword at the beginning of the trait and implementation block declarations. So if a trait has unsafe code, we have to embrace the unsafe code inside the trait. Okay, and we have to declare the trait as an unsafe trait, and the implementation block that uses the trait has to be declared as unsafe as well. So for demonstration purpose, I have the following code that shows the use of the unsafe keyword. The more effective version of it doesn't really need to use the unsafe code. So I'm going to show you the use of the unsafe traits, even though it is not really necessary to do so in reality. Okay, we have such a function in Rust called FromRawPathsMute. So this function would create a slice reference that wraps around the given pointer and length. So I can just use a pointer and its length to make a slice reference. Okay, and accordingly, both the mutable reference that is passed to this function and the return value of this function, which is also a mutable reference, would access the same memory location. So the mutable reference that is passed to the FromRawPathsMute function, together with the return value of this function, would access the same memory location. This action is unsafe in Rust because the mutable reference that is passed to this function is not guaranteed to be valid when the function is called. Okay, so let us see the meaning of the FromRawPathsMute function by also seeing the FromRawPaths function, which involves the use of the immutable reference. So if we want to make an immutable reference from a raw pointer, we can pass the raw pointer, which is an immutable raw pointer, into the function, and I have to include the size of the array as well. So you can see that we can make a slice from a pointer and a length. Okay, and len here, which is the second parameter here, is the number of elements. Okay, so the FromRawPaths function here is unsafe, as there is no guarantee that the given pointer is valid for the len elements, nor whether the lifetime inferred is a suitable lifetime for the returned slice. So we don't know whether this thing, which is a raw pointer passed to the function, would live as long as our current function uses it. Okay, so this action is unsafe. And we can take a look at the corresponding mutable counterpart of this function. So FromRawPathsMute would perform the same functionality as FromRawPaths, except that the mutable slice is returned. So I pass a mutable raw pointer and I get a mutable slice. Okay, so this function is unsafe. So we can take a look at the mutable counterpart of the function called FromRawPathsMute. So this function can perform the same functionality as FromRawPaths, except that a mutable slice is returned. So you can see the mutable reference is returned. And we need a mutable raw pointer to be passed to the function instead of using an immutable raw pointer as the FromRawPaths needs. Okay, and this function is unsafe for the same reason as the FromRawPaths. Okay, we have no way to really ensure that this reference passed to the function is already valid or not. Okay, so let us see the code. So I want to import the FromRawPathsMute function, and I can make my own trait called operate, and I have a certain function inside called double elements. So in this double elements function that I'm going to implement, I need to use the FromRawPathsMute pointer that is provided by Rust. Okay, so I have a structure here, and I can make an instance of that structure, and that structure has a field called data, which is of vector type. Okay, and the vector would store some integers in U32 type. Okay, and then I want to implement the unsafe trait. That's why I have to include the unsafe keyword at the beginning of my implementation block. Okay, and here the trait is unsafe because it is going to make a function that uses the unsafe function. Okay, that's why the trait here must include this unsafe keyword, and the implementation block also needs to use this unsafe keyword here. Okay, and the double elements function is rather simple. I want to pass a certain vector obtained from the structure instance, okay, and I want to return a slice that is accessing the same memory location as this pointer does, okay, and then I will have an unsafe action to come out. That's why I have to do it in the unsafe mode, and then I pick up each of the elements in this from raw part smooth function. And then I pick up one element to multiply it by 2, and then I pick up another element to make it twice of the original value. So it means that I'm doing the dereferencing of the elements. And then I change the value of that dereferenced value to twice of it. Okay. So let us see the main function. In this main function, I have a certain instance, and this instance has a field called data, which really stores a vector. And I make a pointer here, which is a mutable raw pointer called ptr. And of course, I have to include the length of this vector because this is something required by the from raw part mute function, okay? And then I call the double elements function that is implemented in my struct structure, okay? So I get the double elements function from the operate trait, okay? And then I can safely use the modified data because the modification is done in the unsafe code, okay? So I can just pick up any one of the values to do the print9 macro, okay? So let me try to play with the code. So you can see that I'm able to really multiply all the numbers in the vector by 2, okay? So this is achieved by the function here, which is an unsafe function. So I have to do all the things in the unsafe block, okay? So the ptr here, which is a pointer passed to the from raw part smooth pointer, would access the same memory as the return value of itself, okay, which is the slice variable here, okay? That's why two pieces of references are trying to access the same data, and both of them are mutable, okay? That means Rust disallows the access of the same memory location by two mutable references, okay? So we can use the unsafe code to do it, okay? The next issue to talk about for the advanced Rust is the advanced traits. In a trait, we can set up some associated types in it. What is an associated type? Let us see. For many traits, we need to specify the associated type. An associated type is a type placeholder in a trait that the methods can use. And we will see some examples later to understand the meaning of it. And when we call the trait methods, we can provide the concrete type. So we will also see the example of really providing the concrete type. That means a trait method can be applicable to particular types. With the given associated type, we can just implement the trait method once only, and we cannot implement the trait methods for different possible types of data. So once we have fixed the associated type, we can no longer implement the trait for other possible types of data. Okay, so now I have an example like this one. I have a toolbox, and the toolbox is a trait, and this trait has a certain associated type called output. So I'm going to implement a function called process, which is really a method rather than a function, and the return type of this process method would be the output associated type. So when this associated type is a certain concrete type afterwards, that output would just follow the so-called concrete type that is set up in the implementation block. Okay, so now I have a structure called my struct, and it has a value field, okay, and I want to implement the toolbox trait on my structure, okay. So when I want to really implement the toolbox trait, I have to specify the associated type. So the associated type, which is output, is I32 in my case. So here I really specify the concrete type in the implementation block for a certain structure. So this structure here has to implement the toolbox trait that is having a certain associated type of I32, okay. So I can just implement the process method to get something like this one, self.val. Self is meaning the instance, and I want to take the value field of my particular instance, okay? And the type here is self output. It means that I will return an i32 value, okay? Because output here is already set up as i32. So i32 would be the type for this output variable. So the associated type is turned to i32, okay? So I can make up a certain instance, and I want to do the processing to get the value field of my structure instance. And this value will be stored in the result variable, and of course I can print it out, okay? So let us try to play with this part of the code. Now you can see that the result is 1, okay? That means I'm able to use the process function. And when I implement the toolbox trait on my structure here, the associated type would become i32, okay? So it means that the process method here would try to handle the value in i32 data type, okay? So I can implement the toolbox trait on different structures by really specifying the associated type corresponding to the structure, okay? And the next topic about advanced trait is the default generic parameter and operator overloading. Rust would disallow the explicit way of operator overloading like C++ does. However, we can overload the traits and operations in this particular module called OPS by really implementing our own traits. So what is OPS here? Let us see the documentation. OPS means the overloadable operators. So I'm going to overload some operators which are in function form. Like when we do the addition, we can use the add trait, and in the add trait we have some functions corresponding to adding, okay? So we can overload the functions by using the advanced trait that we will discuss very soon. And let us see the following example. We can make a function structure, and then we can do addition on 2 fraction instances without really simplifying the final answer. We need to use the add trait to overload the add method for this trait. So we already saw that this add trait is coming from this overloadable operators. And when I just import this trait, I can overload the add method, okay? So let us see the add trait here. The add trait would have an add method, which is the required method. So we have to really implement the add method to get the output corresponding to the output associated type, okay? So you can see the associated type again. So let us see how we can implement the addition of 2 fractions. First, I import the add trait here, and then I make a fraction structure. It has a numerator and a denominator. And then I implement the add trait for my current structure called fraction. I denote the associated type as fraction. That means the answer to come out is a fraction. And the add trait has a method to override, which is this add method, add method, okay? And self output here means just the fraction that we want to output. So I override the add function here. I put one fraction and the other fraction of fraction type again, of course, and the return value would be a fraction whose numerator is operated as follows, which is just like taking the common denominator and I handle the numerator part. And of course the denominator is just the product of the 2 denominators from the 2 fractions, okay? And then I make fraction 1, and then I also make fraction 2, and then I can make the addition by calling the overloaded add function, and then add method, and then I will get the result, and I can print the result in the fraction format. So let us try to play with the code now. Okay, you can see that when I use the debug trait, I can show the fields of my instance. Okay, so for this field, it is the numerator, and for the other field, it is the denominator. So when I add 1 over 6 by 1 over 4, I'm able to get 10 over 24 if I don't do any simplification of the final answer. So it means that I've already overloaded the add method, okay? And in the add method, the type to interact with the method is called the right-hand side, which is self by default, okay? So let us see the add trait again. So the other value to handle is called the right-hand side, and self is just the so-called left-hand side, okay? That means when we do addition, we add self to RHS, or just the right-hand side, okay? And we can change this default type parameter so that the add method can interact with another type. We can change the default type to another one. So what does it mean by this one? Let us see. We see that the RHS has a default type of self. That means it just follows the same data type as the self, okay? So we can just change the type of the RHS to other types when we want to do the addition. So let us see what it means in the coming example. We can do the changing of the default data type parameter. So we can see that the associated type output can be changed to other primitive data types as well. So this is an example that I'm going to overload the add function or method in another way, so that the data type of the right-hand side isn't the same as the self type, okay? So I import the add trait first, and then I make two tuple structs. One is called large packet, and it has a value of U32 being stored. And I have another tuple struct called small packet, and I have a number in U32 unit. So actually, a large packet would have a weight of 100 grams, and for a small packet, the weight is 500 grams. So when I have one large packet, I put one inside the tuple struct to mean that I have 1000 grams. On the other hand, when I have one small packet, I put one in the tuple struct of the small packet, and then it means that I have 500 grams, okay? So I want to add the weights of a number of large packets and a number of small packets to see the total weight. So how can I do it? I can implement the add trait for my large packet structure, okay? So the type, which is the associated type, is U32, okay? Which means an ordinary integer. And then I overload the add method. So you can see I put self as the first parameter, and the other parameter is other. And this other has a type of small packet rather than just the large packet. So you can see that the other data type doesn't really follow the data type for the structure, okay? So I can return U32 as the answer to the add method. Self.0 times 1000 plus other.0 times 500. 0 here means the first value in the tuple struct, okay? So I pick up the number of large packets multiplied by 1000 plus the number of small packets multiplied by 500 to get the total weight of all the packets, be it large or small, okay? So here I have 4 large packets, and I have also got 3 small packets, and the total weight of these 2 packs of goods would have a certain weight, okay? So I want to find out the total weight of 4 large packets and 3 small packets. If one packet has a weight of 1000 grams and a small packet has a weight of 500 grams. So let us play with this program. So you can see that I have 5500 grams. Why is this the case? One large packet has a weight of 1000 grams. So 4 large packets would have 4000 grams. And one small packet has a weight of 500 grams. And 3 small packets would have a total weight of 1500 grams. So 4000 plus 1500 is altogether 5500 grams. Okay. So The example wants to show that the add function or method here can handle different units or different data types. We don't always need to make sure that the structure here and the structure here are the same, okay? That means we can handle the addition for different types, okay? And in advanced traits, we can call methods with the same name. What does it mean by this one? Let us see. Given that a struct has implemented a method of a given name, it is also possible that two traits have a method with the same name as that implemented by the structure already. So we will have an example to see that how the name clash issue can be handled in advanced traits. If we use the method implemented by the struct itself, the default method to use is that from the implementation block of the structure. On the other hand, if we use the method from the trait, then we need to specify the trait name as well. So when we use a trait method, we have to really specify the trait to use as well. So let us see the following example. I want to calculate the properties of some shapes. I have an area trait to calculate the area. So the function name is called calculate. I also have a volume trait. I want to calculate the volume of a certain instance. And then I can see that there are two same names from different traits. And in advanced traits, which is a Rust feature, it can handle the same name coming from different traits, okay? And let me continue first. I have a structure, and the structure has a field called radius. So I have a circle. I want to make a circle by inputting the radius, okay? And for this circle, I want to calculate the area. That means I implement the area trait for my circle structure. And you can see that I want to set up the calculate function provided by the area trait. Then I just use pi r square as the area. Okay. I take the radius coming from the structure instance. And then I take the power of 2 of my radius coming from the instance. And then I multiply the result by pi to get the area. So I can print out the area for the circle. And for this calculate function, it is coming from the volume trait. I can handle this calculate function from the volume trait by setting up another formula to return, okay? The volume is just 4/3 times pi times the radius to the power of 3. So we have already handled two calculate functions from two traits. And the circle can implement its own calculate function, okay? So you can see that I have another calculate function to find out the perimeter, okay? 2 times pi times the radius. And then I can show the perimeter to the console, okay? And let us go to the main function. I have a circle instance, and then I can tell the circle to do the calculation. It will just use the calculate function from the implementation block of the circle, okay? So it means that I will get the perimeter. So it is actually equivalent to annotating the calculate method for the circle data type, okay? So if we want to use the calculate function from the area trait, I have to say area : calculate. And if I want to use the calculate function from the volume trait, I have to say volume : calculate. If I don't do so, it is impossible for Rust to select the function to use. Is it the function for the area trait? Is it a function for the volume trait? Or is it a function from the implementation block directly? Okay. So let us try to play with this part of the code. So here we see that the first calculate function would be corresponding to the implementation block of the circle structure directly. Okay, so it means that I will get the perimeter. So when I want to find out the area, I have to say area : calculate. So that I will go to the implementation block that implements the area trait. Okay, so I can get the area. So the volume implementation block would also serve this purpose. I have to say volume : calculate to get the volume coming from the implementation block that implements the volume trait. Okay. If I say circle calculate, it means that I'm going to use the implementation block of the circle. Okay. So it means that I will get the perimeter. So let me try to play with this part. you see, we can make the calculate find the perimeter again, because when I denote the circle type here, I'm going to the implementation block of the circle to run this calculate function. Okay. Another issue about the advanced trait is the fully qualified syntax. If we want to call the associated functions, that means those without using self, then we have to use the fully qualified syntax by really specifying the trait that a structure is implementing. And the trait annotation is included in a pair of angle brackets. So we will see an example to understand the meaning of the fully qualified syntax. In this example, I have a trait called math, and I have a function called strength, which returns a string. Okay. And I have a student structure that has nothing inside, and I can implement the string function by the student structure itself. So the student can just say that I like history subject. And I can also implement the math trait for the student. If I implement the strength function coming from the math trait, the student would just say that I like math subject too. Okay. It means that originally the student likes history, but if I implement the math trait, the student would also like math subject. So let us see how we can do the print9 macro. A student says student strength. If I want to run the first line of code here, I just go to the implementation block of student to say that I like history subject. But if I want to say that the student likes math, I can do something like this. Student as math, angle brackets, followed by the string function. Okay. What does it mean by this part? I want to really specify the fully qualified syntax to get the method coming from a certain implementation block that implements a certain trait. So the student needs to implement the math trait when I want to call the strength function here. Okay. If I don't say math beforehand, I would just use the implementation block for the student alone without implementing any trait. Okay. So that is called the fully qualified syntax to really specify the trait that a certain struct is implementing when I use a certain function. Okay. So let us try to play with this part. Okay, you can see that without the use of the fully qualified syntax, the strength method would come from the implementation block of student alone. Okay. If I want to specify the trait that the student is really using, I have to use student as math, embraced by a pair of angle brackets to really do the fully qualified syntax so that I can get the strength function from the implementation block that implements the math trait. Okay. Another topic to discuss about the advanced trait is called supertraits. We can write a trait that depends on another trait, so a trait can produce another trait. So we will have a supertrait and an ordinary trait. So I have a certain example coming up. So fragile, food, and frozen are the supertraits of the ice cream pie trait. Okay, so let me use a diagram to illustrate my idea of the following code. I have an ice cream pie trait that comes from the fragile trait, frozen trait, and food trait. And the frozen trait is actually coming from the food trait. So I have a trait based on another trait, okay? And these three traits would combine together to produce my new trait, okay? So that is the relationship between the super trait and the ordinary trait, okay? And when we make a structure, we need this structure to implement all the traits, including the super traits. So we will see how to implement all the traits coming from these four traits in my following example. In this way, an instance of the structure can use all the methods from all the traits and the super traits. Okay, so in this way, we can use all the functions from all the traits. And the following example is really adapted from the Rust by example web page. Okay, I have a trait called food, and in this trait there are two functions, name and expiry. And for the frozen trait, it comes from the food trait. So the frozen trait would have a freeze function. So it means that the food trait becomes the super trait of the frozen trait, okay? And we have another trait called fragile that has a function called handle, okay? And here I have an ice cream pie trait which is coming from the fragile trait and the frozen trait, okay? So I can use that addition symbol here to join the two traits to make a new trait, okay? And this trait called ice cream pie has a property function, okay? That is going to show the detail of a certain ice cream pie. And then I have a certain function called introduce. So I want to pass a dynamic type, and the dynamic type is just the ice cream pie type here. I want to show all the information about a certain instance of ice cream pie type, okay? And I just do the formatting to show the expiry date, storing temperature, handling method and property, and the name, and so on and so forth. So I want to call the food.name method, food.expiry method, the freeze method, the handle method, and the property method. All these properties would come from the previous traits. You can see all these names coming out. Okay, so for this function to work, I have to really implement all the traits, okay, so that all the functions in these traits can be defined. And here I have a certain structure called yummy ice cream. Okay, so this is a structure rather than a trait, okay. So this yummy ice cream pie would have a name and the expiry date. And then I want to implement the food trait for the yummy ice cream pie structure. So I define the name function here and the expiry function here, okay. Since I want to pick up a string from the yummy ice cream pie instance, I want to use the clone method so that I can get another string back, so that the name here and expiry date here would not be moved to the name and expiry functions respectively. And then I can implement the frozen trait for yummy ice cream pie. And I want to implement the freeze method. So I return a string saying that we have to store the ice cream pie below 18 degrees Celsius. And then I want to implement the fragile trait for yummy ice cream pie structure. I want to define the handle function to show a string here. So we have to store the yummy ice cream pie in the carton boxes. And after setting up the structure implementation blocks, I want to also implement the ice cream pie trait for my yummy ice cream pie structure. Okay, so that is a property function to handle. So the property of the yummy ice cream pie would be crunchy and sweet. So how can I apply all these implementation blocks to show up the information of a certain ice cream pie? Let us see. I make a certain instance. I declare the name and the expiry date, okay. And I want to use the introduce function. Introduce function is just this function, okay. That is going to show the information of a certain ice cream pie that is passed into the function. So this is an ice cream pie type, but now I want to pass a certain yummy ice cream instance. That is allowed because as long as the food that is passed to the introduce function implements the ice cream pie data type, it is already allowed. That's why a yummy ice cream pie is able to be passed into the introduce function, okay? That is the meaning of the keyword dynamic here, okay? And I pass the reference to the ice cream pie instance into the function, and I can show all the details about the ice cream pie. So let me play with the program. So you can see that I'm able to show all the information about a certain yummy ice cream pie instance. Expiry date, coming from the instance itself, and expiry date, and the name would also come from the instance itself, okay? And other information about the storing temperature, the handling method, and the property can be shown here because when a certain yummy ice cream pie instance is passed to the introduce function, it can be accepted because the yummy ice cream pie really implements the ice cream pie shown here, okay? So you can see that the dynamic type allows yummy ice cream pie instance to be passed, okay? Because that yummy ice cream pie instance is really able to implement the ice cream pie trait, okay? So this diagram is going to show the meaning of the implementation. The ice cream pie structure is going to use all the 4 traits: fragile, frozen, food, and ice cream pie, okay? Now let's take a look at the advanced types in Rust. The first one to talk about is the new type pattern. So the tuple struct has a single field that is of the type on which we implement a trait. So the tuple struct can act as a wrapper, and the effect is just equivalent to making a new type. So we will see a very simple example to illustrate the new type pattern by using the tuple struct. In this example, we have 2 types called Celsius and Fahrenheit. Okay, so how can we make these 2 new types? I can use the tuple struct. So I give a name, and then I just include a data type inside the brackets. Same for the Fahrenheit. I have the name followed by the type. So I have 2 tuple structures here. Okay, so I can treat them as the new type, and I can just implement the function here for the Celsius structure as follows. So for the Celsius structure, which is a tuple structure, I want to change the value inside the Celsius type into the Fahrenheit value. So I make a to Fahrenheit method so that the return type will be of Fahrenheit tuple structure type. And the formula is just like this. I pick up the first value of the tuple structure of the Celsius structure, and the first value is indicated by .0, okay? And .0 just means the first value inside the tuple structure. And I pick up that value to multiply it by 9 and divide it by 5, and then I add the result by 32 to convert a Celsius temperature to the Fahrenheit temperature. And for the Fahrenheit structure, I implement a certain function to convert a Fahrenheit temperature to the Celsius temperature. So I pick up the Fahrenheit temperature and I put it into the function called to Celsius, and then I would return a Celsius data type, which is a tuple structure, okay? And I just put it into the Celsius tuple structure, and the value to put is self.0, which is just the value inside the Fahrenheit tuple structure, okay? And then I subtract 32 from the Fahrenheit value, and then I multiply the result by 5/9, okay? So I can do the conversion from the Fahrenheit temperature to Celsius temperature. So same for here. The return data type would be of Fahrenheit type, okay? So I would put the corresponding Fahrenheit value into the Fahrenheit tuple structure, and I would put the Celsius value coming from the equation to the Celsius tuple structure, okay? And then I do the main function as follows. I create a Celsius instance, and the value to put is 25 degrees, so it means 25 degrees Celsius. And then I want to call the to Fahrenheit method for the Celsius instance. So of course, the variable would be of Fahrenheit type because it is the return type of the to Fahrenheit function, okay? And I can print out the corresponding Celsius value from the Celsius instance, which is just the first value of the tuple structure. And of course, I can also print out the first value of the Fahrenheit instance, which is put into the first element of the corresponding tuple structure. And then I do the same thing for the Fahrenheit temperature of 77 degrees, okay? And then I make this Fahrenheit temperature to its corresponding Celsius temperature by using the same logic, okay? So let us see the program, and let me run it. So let me try to get the result by running the program. So you can see that I can convert 25 degrees Celsius into 77 degrees Fahrenheit. And I can do the other way around by converting 77 degrees Fahrenheit to 25 degrees Celsius by using the corresponding conversion functions to Fahrenheit and to Celsius. Okay. And since the type inside the tuple structure is I32, I would just have the integer value being put into the tuple structure for each of the two conversions. Okay. And then we can talk about another advanced data type called type aliases. So we can give a name to an existing type by using the type keyword. So the alias has the same meaning as the existing type. So we just use a name to represent our commonly used data type name. So we can see the meaning of the type aliases in the following example. So I can call username as the type called string actually. Age here is another type which is in actually U32 data type. So instead of using string and U32, I can use username and age instead to represent the original types. Okay. So I can just do something like this. I can use username to represent the data type instead of saying that it is a string. Okay. Same for the age here. I can use AGE instead of U32. Okay. So the two assignments are allowed. That's why I can do the print line macro successfully. So let us play with this part. And now let us try to play with the program. And you can see that we can really print out the statements here. The username here is the valid assignment because I can use the type alias to represent the string type. Okay, so these are the aliases that are allowed in Rust to change the original type to another name. Okay. Same for the age variable here. It is of U32 type, but it is also of the age type because the age is the alias of U32 here. Okay. So what is the real purpose of making type aliases? Can we just use the original data type names instead? Yes, it is of course possible to use the data type names directly, but the purpose of the type aliases is to reduce repetition and to increase readability. So we will have an example to show that we can create readability by using the type aliases. So let us see this example. I make a hash map, and the hash map has two parts. I32 followed by a vector. Okay, so the first place to put into the hash map is the bus number. Okay, and the second part of the hash map is actually a vector that stores the reaching time of a bus at the station in hours and minutes. So the first element in the tuple is really the hours, and the second element in the tuple is really the minutes. Okay, so the bus type here is actually such a hash map. So we can use the bus instead to represent the entire hash map structure. Okay. So let us see how we can use the bus type, that is the type alias. So I can make a bus1 instance here, which comes from the bus type. Okay, so the bus type is already representing two parts of the hash map, the bus number and the reaching time of a bus at the station. Okay, and the reaching time is represented by a tuple inside a vector. Okay. So I can use bus type here to represent the long thing here. So I can increase readability and I can also reduce repetition. So I don't need to put the whole thing called hash map into the next line. Okay, and I can also increase readability by knowing that, oh, this hash map is really representing a bus number together with the reaching time of it. Okay. and then I make a new hash map, and then I can insert some contents into the hash map. Okay, so bus number 31 would reach a certain station at these 3 times mentioned. Okay, 6:32, 6:58, and 7:23. So these are the hours and minutes for the bus to reach a certain station. We can see that we have 3 reaching times for bus number 31. Okay, so I can print out the bus number together with all the reaching time for the bus. Okay, so I can use the printline macro as follows. Bus number will be indicated by the key of the hash map, and the value of the hash map would be just that whole vector, and I can show all the tuples inside this vector by using the colon question mark notation. Okay, so let us try to play with the program now. Okay, you can see that I can just print out all the tuples inside this vector. Okay, so these tuples are just representing the time of bus number 31 to reach the station. Okay, 6:32, 6:58, and 7:23. Okay, so I can use the bus type more meaningfully than using the hash map notation in the program to improve readability. Okay. Another advanced type is the never type. So some functions don't have any return type. This return type is actually called the never type or the empty type. And the data type called never type can be represented by an exclamation mark. The functions with this return type are called diverging function. It means that it has nothing to really return. The never type can be coerced into any other type. As an example, the panic macro has a return type of never, so we can see the meaning of the exclamation mark, which means we have no return type. Okay, and the result variable can be i32 or never type, as panic macro can return a never type, so it can be i32 or never type, because it depends on the value stored in the result. If there is something to output, the value can be i32 for the output, and if we have nothing to really output, we can have the never type as the return type. Okay. Since the never type can be coerced into other types, the never type can be treated as i32, and the match expression would return i32. We are sure that both match arms can return the same data type by coercion. Okay. So let us see the following example to understand the meaning of coercion in this case. Here we have a divide function. I want to do the division, and the division can be disallowed if the value of b is really 0. Okay, if it is 0, I will return none as the option enum variant, and for the division that is allowed, I can just return a over b, and I would return it as the sum variant, because I use the option type here. Okay, let us go to the main function. In the main function, I want to get the result from the division of 10 by 0, which is not allowed, of course. Then I will go to have the none variant to come out, and I can try to match the result into one of the two cases. If I have really got a value, I just return the value, and this value will be put into the answer variable. If I would get none as the answer to the divide function, I would just get the panic macro. Okay, so the panic macro is actually of never type, and the value, if division is allowed, will be i32. Okay, because this is the result of division value in i32 type mentioned in the option enum. Okay, so when I do the never type, this never type will actually be coerced into the i32, so it means that the result will just be of i32, even though the panic macro is of never type. Okay, and then I can print out the answer as usual. So let us see the result of this program. Okay, you can see that I can go to the arm called none here, and none here would help me get the panic macro, okay? And the panic macro is of never type, but the never type can be coerced into i32 type. That's why the matching is still allowed, because of the coercion of the never type to the corresponding i32 type, okay? So you can see that I can just print the statement here, cannot be divided by 0, and of course I can get the backtrace, which means that the program really fails to execute, because I really make the program to panic, okay? Now let us go to another advanced data type called dynamic sized types and the sized trait. So what is a dynamically sized type? It is also called the unsized types, and in this type we cannot know the size at the compile time. That is called dynamic. We just know the size at runtime. So that is the meaning of the word dynamically in this context, okay? One of the examples is str type, whose length can really vary. That's why we have to use $str to get the address of the str content stored on the heap. And the $str would help us store two values. Which are they? They are the starting point of the str data type and the length of the str data type. In this way, we always know the size of the $str at compile time, which would refer to the starting location in the address format and the length of the str data type. So we have two such values to store, okay? And the size of this kind of variable is twice the size of usize, because we use 1 unit of the usize to store each of the values in the $str data type, okay? In principle, we rely on some metadata to indicate the size of the dynamically sized information. So we just talk about the basic principles of storing the $str type, okay? In the view of a programmer, we just need to know we store two values, okay? Another example is the use of the smart pointers, which can be related to the dynamically sized type. So we can wrap str with the smart pointers like box_str and rc_str, so that for the box pointer and the rc pointer, we have a certain fixed size, but the content of the str data type can be evaluated at runtime. So box and rc are known at runtime, at compile time. I mean, the size of them are known at compile time, but the content that is put into the box pointer or the rc pointer would be known at the runtime, okay? Trait objects are helping us to store dynamically sized types. For example, this type. A box pointer has a dynamic trait type to store, okay? When we want to pass generic data types into a function, the default treatment is that the data being passed is sized. That means it has a long size. So when we pass values to a function, we have to really know the size before it is passed, okay? The following two functions are really the same. The difference between them is just the sized nature of the generic data type that is specified with the sized keyword. So sized keyword here means that we really know the size that is put into a function at compile time already. So the principle is like this. If I have a function that is playing with a generic data type t, I can use this declaration by saying that the value that is being operated on would have a type t, which is a generic type. And it is also equivalent to the following one. The t here has to be of sized type. So it can be a U32, I32, F64, and so on, as long as the value to be put is of a known size at compile time, okay? So this part can be ignored in the generic function declaration, because it is already implicitly known that the value passed to the function would be of size type. That means the data type of x is already known at compile time. If we want to relax the sizing restriction on the type passed to a generic function, we can add the question mark before the sized keyword, so we can have an idea like this one. The generic type is this one, question mark followed by sized keyword. It means that I don't really know the data type at compile time. And here, the function would accept a reference to the generic data type, okay. And the important thing is that the data type of the function parameter is changed to $t as shown here. The meaning is like this. The size of the parameter in pointer form now is known at compile time. So the value passed to the function will be in pointer form. And for the pointer form, we know the reference, which has a fixed size to store. So the function would have a known size to put. And the function would have a variable of the known size, which is in the pointer form. It means that the address is of some fixed size. So we can just put that fixed size into the function, okay? And then we play with the function in the function content. And t here can actually mean some data type that we don't know the exact size at compile time. We can know the size at runtime only, okay? So for illustration purpose, we can make a code as follows, in which the generic type is unsized. In the program, the str type is also unsized, so we can wrap it with a box pointer to give it a fixed size at compile time. So I have a person structure here, and the person structure would have a generic data type to be handled. And for now, I don't know the size of that generic data type at compile time. It depends on what to put at runtime to really understand the data type of the t, okay? And I have a name field here, and the name field is also of str type. And the str type has to be put in the box pointer so that I know the size of the name field at compile time already, which is just the size of the box pointer, okay? Which is just the box pointer type, okay? And the scores here is represented by the generic data type t, whose size is just known at runtime but not the compile time. So let us see the main program. In the main program, I really need to specify the concrete type to make an instance of the person structure, okay? So I have a person structure. I have to indicate the array that is put into the generic data type. So the concrete type here is a certain array. Each value will be of i32 type, and I have a length of 5 for this array, okay? So the name is that one. I use the from function to really make an str, which is representing a string size in Rust, okay? So I want to put an str value as Peter, and this Peter string is really put in the box pointer, okay? So I can use a box pointer to provide a long size at compile time, okay? But the scores array here has to be of a known size at compile time. So when I really execute the program, I will know the meaning of the t type here. Now in my case, the generic data type t will be a certain array of having 5 integers, okay? And then I can take the reference of the Peter instance, okay? And then I can get the name field corresponding to this instance and the scores of that particular reference. And the scores here would be just the array passed to the Peter instance. So let us see the result of the program. Okay, you can see that I can pick up the array and I can just show the content of the array. Okay, so we can see that the name here is put in the box pointer, and the box pointer content can be shown by referring to its reference, okay? And I can also get the scores, which is in the form of an array, by using the reference of the Peter instance, okay? And then we can talk about the advanced functions and closures in Rust. For advanced functions, we have a topic to consider, which is called the function pointers. We can pass regular functions to another function, so a function can be passed to a function. And the function being passed has a type called fn, which is called the function pointer type. And we have to notice the use of lowercase letter fn here. And there is a certain trait called fn trait, but we used uppercase F to mean the trait that can be implemented by closures. But now for small letter f here, it means the function pointer type. That means I want to put function in another function. Okay. And the function declaration accepts an fn type with the input and output parameter types declared too. And we can also pass an argument of function pointer type to a function call. So we can see the following example to understand the meaning of the function pointer. So now I have two functions, add and subtract. So these two functions are quite simple. I do the addition and subtraction. Okay. And I have a new function called execute operation. I put a and b into the first two parameters of the parameter list, and then I want to put two functions. The first function will be of fn type, which is the function pointer type. And this function would have two input parameters and one output parameter. Okay. So this is representing the function pointer that has two input values and one output value. And function 2, I do the same thing. I have to put a function pointer that indicates a function having two input values and one output value. Okay. And the return type of this execute operation function will be of I32. Okay. And how can we handle this function operation? It means I want to multiply the result of func1 and func2. Okay. So func1 will be placed in the third position of the parameter list of the execute operation function, and function 2 will be put into the fourth position of the parameter list of the execute operation function. Okay. So let us see how we can execute this operation. I let a be 10 and b be 3, and then I want to put a and b into the execute operation function. So a will be 10, b will be 3, and the third and fourth arguments will be the add function shown here, followed by the subtract function shown here. So add and subtract will be representing the function 1 and function 2 respectively. Okay. So add here is meaning that I want to add two numbers. That means when I put a and b into the function called add, I will get the sum. And for function 2 here, I do the subtraction. So the values to be put into the subtract function will help me get the difference. So when I run the execute operation function, it means that I pick up the add function and I get the result, and then I multiply the result of the first part with the result obtained by using the subtract function. So let us see the result of the program to see what we will get in the print line macro. The answer is 91. Why is it 91? Let us see the program again. A is 10, B is 3, and func1 will be add. So I put the first value, which is 10, into add, and the second value to be put into the add function will be B, which is 3. So 10 plus 3 is 13. Similarly, for function 2, it means the subtract function. 10 and 3 using the subtract function will give me 7. So 13 times 7 is just 91. So that is the meaning of the execute operation that involves the use of function pointers. Okay. The first function pointer would refer to the add function. The second function pointer would just refer to the subtract function. And A and B are put appropriately into the parameter list of each function, indicated by the function pointer. Okay. Function pointers would implement all the fn trait, fn1 trait, and fn-mute traits, so we can pass a function as an argument of a function that expects a closure. So it means that we can really pass a function into a closure, because a function pointer would implement all these three traits that can be used to indicate the nature of the functions that is used in other functions that are used in the closure. So let us see the following example. I have a function called do something, and I have a value a as the first parameter, and the second parameter of the function is something like this. I want to pass a function pointer that implements the fn trait, so I have to say implement fn trait. impl has to be included, and fn here means the function that implements the fn trait, and this function will have one input parameter and one output value. Okay, so this function and a will be put into the do something function parameters respectively, and the do something function will return an integer of i32 type. And in this function do something, we just execute the function, okay, and the function will be executed according to the value of a that is passed into the parameter list of the function, okay, called func, okay. And let us go to the main function. I have a number 3, and I want to really run the function called do something, so I put 3 into the first parameter, and the second parameter of the do something function is really a closure. You can see that I do a closure, okay. And this closure would implement the fn trait. So I put one value into the function, which is actually p, and the return value would be just an integer indicated by multiplying the variable p by 3 times, okay. So I will get the cube of p, which is passed into the closure, okay. So here p will be effectively replaced by x. X will be put into the closure, so p will become x effectively, and I will get the result of the multiplication by printing the result value out. So let us try to play with this part first. Okay, you can see that I can get 27 because p will be able to capture x into the closure, and 3 times 3 times 3 is 27. So you can see that I will have 27 as the answer. And you can see that the function here is actually a closure, and a closure is allowed to be put into the do something function because that closure can implement the fn trait. So even though I have a function pointer in the form of a closure, it can still be executed in the do something function, okay. So we have to really include the impl keyword because that function has to implement the fn trait, okay. Let us see the meaning of fn in this context. So when we use the fn trait, the closure doesn't move the captured value out of its body, and the closure doesn't mutate the captured value, and the closure does nothing from the environment. It can be called more than once, so that is the meaning of the fn trait. So we can see the fn trait here. The fn trait is actually built upon the fn mute trait, okay. So this is the version of a call operator that takes an immutable receiver. The instance of fn can be called repeatedly without mutating the state. And let us go to another topic called returning closures. In order to return a closure, we need to wrap it with a box pointer because the closure has no definite size in memory. The reason of having no definite size is that the closure isn't a concrete type. Okay, if we want to return a closure, we have to wrap it in a box because the box pointer has a fixed size, but the closure is not a concrete type. That's why we don't know the size at the compile time, okay. So the returns closure function would return a box pointer type, and the content to be put into the box pointer will be like this. I want to include the function inside the box pointer. So the function will be implementing the fn trait, and there is only one input parameter, and I will have one output value for the function that is put into the box pointer. And this function will be of dynamic nature. That means I don't really know the particular function to really put into the box pointer. So I will just return a box pointer that has a closure inside. Okay, so that is my major idea of this box pointer value that is output to the outside world. So a closure is executed to store the result in the closure variable, which will represent the box pointer that contains a certain closure. And I put a as 5, and I put closure a here. That means I want to capture the value of a into the closure enclosed by the box pointer. Then I will see the result of this closure by using the printline macro. So let us try to play with the program. Okay, you can see that I get 10 as the answer. So that when I put a into the closure, I'm able to capture a into the closure, and the closure will be just able to multiply the value obtained by 2. So I will get 5 times 2, which is equal to 10, and the value of 10 will be put into the result variable. And of course, the printline macro is able to print out the result. And here I don't need to do the unboxing explicitly because the printline macro is able to do so for us, because the box pointer would have the deref trait for us to really get the result immediately without really implementing the unboxing by ourselves. Now let's talk about derivable traits. What are the derivable traits? They are actually those traits that can be annotated on a type using the derive attribute. And when we have a derived trait, the default implementation will take place. So what does it mean by this sentence? It is a bit abstract. I'm going to show a number of examples of derivable traits, and we will see the meaning of the derivable traits more clearly after these examples. The first example is called a clone trait. So due to the ownership mechanism, a moved structure instance is gone, and we cannot make a copy of an instance so easily. So we can see this example, which is already understood in the introductory section of Rust in another video. So when I want to show the content of the structure fields, I can use the derive debug attribute, okay. And when I make an instance called point1 from the point structure, I have these two pieces of information included, x equals 1 and y equals 2. And when I make p2, which is another point instance, by doing the simple assignment p2 equals p1, p1 will be moved to p2 and p1 will be gone. So I'm not able to further use the p1 variable because the content referenced by the p1 variable is already moved to p2. Okay, so I'm not able to execute the following code perfectly. So let us see the result. Of course, you can see that it is not possible to print out p1.y or p1.x because the value of p1 is already moved to p2. That's why it is not possible to print out p1 after the movement. And you can see that I moved p1 to another variable called p2 already. Okay, so in order for us to really print out the content of p1 after the assignment, we can have some idea called the clone trait. A structure can implement the clone trait, and we can clone a struct instance as follows using the clone method. The clone method implemented by the clone trait. So if we include a clone trait and we derive the clone method, we can really do the assignment of p2 as usual while retaining the content in p1 so that I can still print out p1 here. So let us see the result first, and then I'm going to discuss the purpose of the clone method implemented by the clone trait. Okay, you can see that I have no error coming from the Rust analyzer. And you can see that I have used the clone method coming from the clone trait, okay? And we have to derive the clone trait so that I can use the clone method, okay? So you can see that the trait is having a capital letter at the beginning, and the method corresponding to the clone trait would start with a small letter, okay? So let me try to play with the program first. Okay, you can see that both the P1 and the P2 contents can be printed out. So P1 here would be cloned and allowed to print. What does it mean by cloning in Rust? Let us see the explanation here. The clone trait would make a new copy of the instance on the heap, as well as a new reference to this newly created instance on the heap. So the two values on the heap are independent of each other. So when I have P1 here, after the cloning, I make it P2 here, and this P2 would have a new value on the stack, which would point to the newly created memory on the heap. So this is the heap memory, and this is the stack memory. The two variables are put on the stack, and you can see that P1 and P2 are separate variables stored on the stack. And each of these two variables on the stack would point to different locations on the heap. So even though the values contained in each of the locations on the heap are the same, they are referring to different locations in memory. So even though you see the data are the same for the two pieces of data on the heap allocated memory, they are actually stored in different memory locations on the heap. That's why these two pieces of data are independent when we use the clone trait, okay? That's why we don't have the problem with movement, okay? And another trait to discuss is the copy trait. Rust has the ownership mechanism to move a value to another variable. The same mechanism would also apply to structures. So let us see the following example. When I do the same thing as before, like the structure implementation and the assignment of P1 into P2, of course I'm not able to print out P1 any longer because P1 is already moved into P2 and P1 is gone. And if we want a structure instance to appear in another identifier while keeping the original struct instance unaffected, we can use the copy trait. So I'm not doing a new instance to be stored on the heap. I just copy the reference stored on the stack. So you can see the following sentence here. The copy trait can make a bitwise copy of the reference stored on the stack, and then stores the copied reference to another identifier. In essence, we just copy the reference, and the two references would point to the same location on the heap. That represents the point instance, okay? So the structures that store primitive types can only implement the copy trait, and variables that have static lifetime can also implement the copy trait. So we have these two conditions to use the copy trait. First is for primitive types, and the other one is for the static lifetime variables, okay? On the other hand, the values in the heap allocated memory, like the vectors and smart pointers, do not implement the copy trait. They are only allowed to use the clone trait rather than the copy trait. So we have to remember the difference between the copy trait and for the clone trait. And since the clone trait is the super trait of copy, we need to derive the clone trait as well to use the copy trait. That means when we want to use the copy trait, we have to include the clone trait as well. And when we use the copy trait, the simple assignment of the instance to another identifier is enough. So you can see that we have two identifiers stored on the stack, and these two reference variables would point to the same location on the heap, so that we have two variables to refer to the same piece of information on the heap, okay? So let us see the result of using the copy trait. So I have to include the copy trait as well as the clone trait when I do the derivation at the very beginning of the point structure, okay? And you can see that after I include the copy trait to derive, I'm able to pass the compiler pretty easily so that the content of P1 can also be printed out, because the P1 data are already copied, in the sense that the P2 here, which is stored on another part of the stack, would point to the same memory location on the heap that refers to the same particular point instance. Okay, so let us play with this program. Now let us see the result. Now you can see that I'm able to print out both P2 and P1 because they can refer to the same memory location, even though P1 and P2 are two different reference variables stored on the stack, because the copy trait is already implemented and derived. Okay. And let us talk about the debug trait that we already used previously. The debug trait can allow us to see the debug formatting in strings. We can use these two ways, one with the hash sign and the other one without the hash sign, to show the information of an instance for debugging purpose. By doing so, we do not need to implement the display trait for our user-defined types. So that is the technique we use pretty frequently to show the content of an instance from a structure. Okay. So let us see this example again, and we have to use the fmt package. Okay, and I have a person structure. I also derived the debug trait first here. Okay, and then I make a person in the main function. The person has these pieces of information: the name, the age, and the city. And when I want to print out the content of that person instance, I can use the pattern here, colon followed by the question mark, to print out the fields of this person instance. So we can see the result pretty easily. Oh, sorry. For just the derivation of the debug trait, we don't need to use the format package. Okay, so this import can be neglected. And let me try to play with the program. I can ignore the warnings because the warnings just say that these fields are not really used, except the printing achieved by using the debug trait. So you can see that the person instance can show the content one by one. The field called name, the field called age, and the field called city can be shown. Okay, so this is already something we know pretty easily. If we want to show the instance content by implementing the display trait, we can do the following. And here the placeholder lifetime means that the lifetime parameter can be elided or can be ignored. So this time I really need to use the fmt package so that I can do the formatting required by the fmt method from the display trait that we want to implement. And you can see that I can use this fmt function to show the content of the fields of a certain instance denoted by the self reference. Okay, and here we have to use the formatter trait. Okay, and the result of this fmt function would be of fmt result type, and I use the write macro to do the display on the standard output. And after doing this function, when I just use a pair of parentheses, I'm able to print out the content of the person instance. Okay, so let us try to play with the code. Let us see the result by running the program. Okay, you can see that after implementing the display trait, I'm able to show the content of the person instance, just like what we showed for the previous example by using the derivable debug trait. Okay, so we can also use the display trait and use the corresponding fmt function to show the content of a certain instance on the standard output. Okay, so something we have to remember is here. We have to use a mutable reference to the formatter because we just changed the content in the formatter by doing these things. We have to really make the formatter mutable. Okay. If we use the assert equal macro, we also need to use the debug trait. If the assertion fails, the debug trait can show the value of the instance. So let us see the following example. I have a person structure, and I need to derive the debug trait and the partial equivalence trait. Because I'm going to compare two instances, I need to derive the partial equivalence trait. Okay. So I make two persons. The first person has these pieces of information, and the second person, called expected person, would have another piece of information corresponding to the name, age, and city. And you can see from the code that these two person instances would just differ with the city. Okay, the name and age would be the same. So if I want to see that whether the two instances are equal to each other, we can do the assert equal macro to compare the person here and the expected person here. Okay, so let us see the result. So the idea is like this. So when I want to use the assert equal macro, we also need to include the debug trait to derive. Okay, let me see the result. You can see that the assertion fails because the left hand side isn't equal to the right hand side by the city content shown here. Okay, that's why the two instances are not equal to each other. Okay, that is the result that we obtain by including the debug trait to derive. Okay. Next, we talk about the derivable traits called partial equivalence trait and equivalence trait. So partial EQ here means the partial equivalence. It can help us to compare two instances of a type, and the equality can be compared by using two equal signs and an exclamation mark followed by an equal sign operator on the instances. So we can check for the equality and inequality of the two instances. So we already saw the partial equivalence trait in the previous example. So now I'm going to elaborate it in more detail. So when we derive the partial equality trait, and the EQ method of this trait will be implemented, and the NE method, meaning not equal, is defined based on the EQ method by default. So let us see the documentation. So when we derive the partial equivalence trait, we have two methods to tackle: the EQ function and the NE function. Okay. Now let's talk about the partial equivalence in more detail. It means that symmetry and transitivity have to be ensured. What does it mean by these two sentences? Let us see. Symmetry is here. If A and B are equal, it is also able to imply that B is equal to A. So the order of the things to compare by using the equality symbol doesn't matter. This is called symmetry. And transitivity. If A equals B and B equals C, we can imply that A also equals C. That is the meaning of transitivity. And if this trait is derived on a struct, two instances are equal if all the values would be the same, okay? And if this trait is derived on an enum type, each variant is equal to itself and it cannot be equal to any other variant. That is the meaning of partial equivalence on a structure instance and an enum instance, okay? This trait is used together with the assert equal macro and the assert not equal macro, okay? And we can use partial equivalence trait for NaN, which is meaning not a number, because NaN doesn't equal NaN in Rust. If a type is possible to have NaN, then this type suits the partial equivalence trait. And how about the EQ trait? The EQ trait has a supertrait called partial EQ trait. That means we have to include partial EQ when we want to use the EQ, okay? We need to put the partial equivalence as well when we want to use the EQ trait. That is the meaning of the relationship between the supertrait called partial EQ and the trait called EQ. EQ here means equivalence relation. In this relation, a value can be equal to itself. That means reflexivity has to be ensured. And the EQ trait has no methods to implement. This trait will be put together with the partial EQ trait when we want to ensure equivalence relation. So when we want to use the EQ trait, we have to include the partial EQ trait so that we can handle reflexivity as well. A equals A, which means the reflexivity condition, okay? And let us see this example. I include the partial EQ trait and the EQ trait, and I put the derivation here on top of the point structure, and in the main method I make 3 point instances, point 1, point 2, and point 3, and you can see that for each of the points the fields are a bit different. If point 1 is equal to point 2, the assertion would be true, and if point 1 is not equal to point 3, the assertion would also be true, because I do not equal here, okay? So let us see the result of this part. So let me play with the program. Now you can see that I have no error message coming out of the standard output. That means that the two assertions are correct. Point 1 is equal to point 2 when I compare the field values of them. And point 1 is not equal to point 3 when I compare the field values of these two instances, okay? This example is the same as the previous one. That's why I can skip this one and I can go to the other part. Of course, we can implement the partial EQ trait explicitly if we don't derive it. So how can we do so? We can do the following code. You see in the structure definition, I don't really derive the partial EQ trait. So I can implement the trait called partial EQ on the structure explicitly, shown here, okay? So I can implement the EQ method for partial EQ trait. So I want to compare the instance with the other instance, okay? So if the name and age of the two instances are equal, I can say that the equality check is true. That's why I can print out return true by using the EQ method, okay? EQ is something here. Okay, we just implement this function explicitly. And for the color enumeration, I can also do similar things. I don't include partial EQ in the derivation above the enum, and I just implement the EQ method coming from the partial EQ trait, okay? I want to compare the colors of two color instances. I have to do the matching. If self here has color red and other also has color red, then I will say true. If the self is green and the other is also green, I also say true. If the self is blue and the other is also blue, I say true. Otherwise, I say false when the self reference and the other reference don't have the same color, okay? So let us see the main function to handle. I make two people here, okay? They have the same name and the same age, okay? And for person 3, the age and name are both different from person 2 and person 1, okay? And when I do the assertion to see whether person 1 is equal to person 2, you will get true because they are really equal to each other. And when I want to see whether person 1 is equal to person 3, you can see that we will make the assertion true because I do assert not equal here, okay? And we can also use the equality check and the inequality check for structures and enums, okay? So I can use the two symbols here instead of using the assert EQ macro or the assert NE macro, okay? I do similar things on colors, okay? I have 3 colors and I do the checking again to see whether color 1 is equal to color 2 and color 3 is also equal to color 1, okay? So let us play with the program. Now let us see the result. Okay, you can see a lot of true coming out here. So we are sure that the assertions are all true. Okay, color 1 is equal to color 3 and color 1 is not equal to color 2. Okay, same for person here. Person 1 is equal to person 2, but person 1 is not equal to person 3. Okay, that's why all the 4 assertions are true. And I can check the print lines macro here. Person 1 is equal to person 2. Is this true? Yes, it is true. Is person 1 not equal to person 3? Yes, it is also true. Is color 1 equal to color 3? Yes, it is true. Is color 1 not equal to color 2? It is also true. Okay, because color 1 is red and color 2 is green. Okay. So they are not equal to each other. And I can say true as the answer to the final print line macro. Okay. Now let's take a look at partial OR trait and OR trait. We can compare the instances for sorting purpose by using these traits. So we use them to do the sorting. That's why we have to consider the order value of your things to compare. When a type implements partial equivalence, this type also implements the partial order. So we can also use these relational operators, smaller than or equal to, larger than or equal to, smaller than or larger than, to compare the instances when we implement the partial order trait. Okay. When we derive the partial order trait, the partial compare method will be implemented. The return type of this method is the option type. If a value is NaN, which means not a number, then the partial compare method would return none, and we have no further comparison to take place. So let us see the content of the documentation about this trait. So you can see that we have to really implement the partial compare method, okay, which has a return type called option, okay, and the thing to be put into the option enum is ordering type, okay. The partial order trait compares two struct instances by comparing the value in each of the fields in their order of appearance. If the values of an earlier field show differences, the comparison is done. And the partial order trait would compare two enum instances by treating an earlier variant as smaller than a later variant. So the order would depend on the order inside your enumeration definition, okay? We use ORD, which means order, when a type also implements the partial order, equivalence, and partial equivalence traits, okay? And we use the ORD traits to make sure that the valid ordering must exist. And the ORD trait would implement the CMP method, whose return type of order is ordering rather than option ordering. So when we implement the CMP method, we don't have the option enum coming out. We just have the ordering type to come out. So let's see the documentation. Okay, you can see that we have the ordering type as the value of the CMP method. Now let us see this example. We include debug, partial equivalence, partial order, equality, and order traits. So you can see I have to derive all these traits on this size enum, okay? And I do the same derivations on the rectangle struct, okay? And let us see the main function. The main function has a lot of sizes and rectangles with different widths and heights, okay? And I can do the assertion to see whether size 1 is smaller than size 2. It is really true because size 1 is small and size 2 is medium. And when we check the definition, small comes first, followed by medium, and followed by large. So small is really smaller than medium, and medium is smaller than large when we do the ordering, okay? So size 3 means large. Large is really larger than the small size. That's why the second assertion here is true, okay? So these two Boolean comparisons are true. And I can also use the larger than or equal to operator to compare the two sizes, okay? Both of them are size 2. So we will see the result later. Same for the structure instances. I can also do the comparison by using the smaller than or equal to or larger than or equal to. What does it mean by this one? When I have rectangle 1 and rectangle 2 as follows, you can see that the width would be the first thing to compare and the height would be the second thing to compare. Why is it the case? Because I put width as the first field in the rectangle structure and height is the second one. That means we check the width first, followed by the height. So rectangle 1 has a width of 10 and rectangle 2 has a width of 15. That's why we can say that we are able to compare the widths of the two rectangles and say that rectangle 1 is smaller than rectangle 2 because the first field to compare would already give me the difference, okay? For rectangle 2, is it larger than rectangle 1? It is of course true because the width, which is the first field to compare, is larger than the field called width in rectangle 1, okay? Of course, I can also use smaller than or equal to do the same comparison. So let me try to play with the program. And let me play the program now. Okay, you can see both true coming out. The first true comes from the first printline macro. The second true comes from the second printline macro. And you can see that all the 4 assertions are correct because I follow the order of comparing the fields or the variants from the structure and the enumeration respectively, okay? And now we talk about the default trait. This trait would help us to make a default value of a given type. And when we derive the default trait, the default function would be implemented too. So let us see the documentation. So when we derive the default trait, we have to provide the detail of the default function here, okay? So when we use the derived default function, the default values for string will be empty. For Boolean, it will be false. For numbers, it will be 0. These default values are those obtained by calling the default function. The first default refers to the trait name. The second default refers to the function name. that is in the default trait. Okay, so let us see this example. I derived the default trait so that I'm able to use the default function inside the default trait. Okay, so I have a person structure here, and I say default for the person here. Okay, so I have to say that this person variable would have the person type. So we have to really specify the structure type explicitly, so that I can use the default function from the default trait to indicate that all the fields corresponding to the person structure would be 0 valued, so that the name would be an empty string, the age would be 0, and the boolean value called is employed will be false. Okay, so I can print out the content of this default person one by one by using the symbol shown here. So let us see the result of playing this program. Now let us play with the program. You can see the default person has come out. Empty string for the name, 0 for age, and false for is employed, which is a boolean value. Okay, so we have to really specify the structure type for this person reference variable. Okay, otherwise Rust compiler doesn't really know the field that you are referring to. Okay, and the default trait is commonly used together with the unwrap or default method. What does it mean by this sentence? Let us see the following example. The name here is an option of type string rather than a pure string. So it means that the name here can be none. So if it is none, I can say the default value. If the name is not none, I just use the value it contains by doing the unwrap action. Okay, so let us see the following code. I have a person structure that has the debug and default traits derived. And then I have a person 1 here in the main function. And I also have person 2 here. And the person 2 here would come from the default function directly. Okay. And you see, I have the person type before I call the default function. That's why the default values would be corresponding to the person structure. Okay. And name1 can use the person1.name.unwrap or default to get it. For this name, I have some variant to include a string here. Okay. And for the name2 here, the name would be actually not present because I used the default value. For the default value of an option enum, it is just none. That's why when I do the unwrap or default method, I will get the default value. So I can print out the values obtained one by one, and let us play with the program now. Let us try to play with the code. Now you'll see name1 is Alice because Alice is really the name in the person 1. Okay, and person 1 has the some variant which contains a string. Okay, that's why I can use the unwrap or default method to really get the some variant for name1 here. Okay, and for age 1 it is 25. That is easy to understand because person1.age doesn't need to do any unwrapping. Okay. For name2, it is just an empty string because the name for person 2 is the default value of none, which comes from the option enum type. Okay. For the option enum, the default value is just none. Okay. And age 2 is also 0 because 0 is the default value for the type called U32. Okay, so for U32, the default value is just 0. So this section has discussed a lot of ways to use the derivable traits. This is the end of the course about intermediate and advanced Rust programming. I hope you have enjoyed learning the more advanced features of Rust language. If you have any questions about the topics discussed in this video, please leave your questions at the comment section below the video. And please subscribe to my channel, share this video, and give me a like as well. Thank you for watching.